Hello and welcome to the world of computer networking. This course is for everyone who wants to understand how computer networks operate and how different hosts communicate with each other. Largest computer network in the world is Internet, and it contains billions of different devices that communicate simultaneously with each other. But who am I and why have decided to create this particular course? My name is bstashchuk, and 8 years I was working as Cisco certified systems instructor, and I was teaching students in person in classes. And I've taught hundreds of students all over the world. Also, more than 10 years ago, I have gained most recognizable Cisco certification in the world, this CCIE, Cisco Certified Internetwork Expert. I know about computer networking a lot, and in this course I'll teach you most important key features of computer networking. I will not give you any obsolete information, and I will not teach you about obsolete protocols and standards. This course on YouTube is part of my large course World of Computer Networking, and in the description under this video you'll find link to full-length course. If you like what I'm doing and want to support me, please enroll to the full-length course. And let's get started with World of Computer Networking. Hi guys. Let me start by defining what is computer network. Computer network is a set of different devices and connections between them. And computer network could be as small as just two different computers connected with each other using cable or wireless connection. And computer network could be as large as Internet. It is the largest computer network in the world. There are different devices that could be connected to computer network, like mobile phones, laptops, routers, switches, firewalls, wireless access points, and so on. But since creation of the very first computer network in late 1960s, Internet has evolved and expanded really much. And now billions of different devices are connected to Internet simultaneously. And you could connect to Internet such devices as, for example, microwave or fridge or even lamp in your smart house. Also, you know that many cars has also connectivity to Internet. And that's why more widely used term nowadays is Internet of Things. You are able to connect to Internet many different things, not just computers. And that's why when we say computer network, we mean actually network of different devices that are capable of connectivity to Internet. Next, let me demonstrate you how you and I use Internet every single day. We have just defined what computer network is. And actually you and I are using computer networks almost every single day. And our mobile phones, for example, are connected to Internet almost always. We are almost always online. And if you are watching this video, you are doing this probably on your laptop or desktop computer or on mobile phone or tablet PC. And in all cases, you are streaming video data from some remote servers. And that's why you are capable of seeing this video on your local devices. And that's thanks to computer networking. Let's, for example, open up your favorite web browser and search for some stuff at google.com, and let's search for computer network term like this. And you'll get some results. And of course, those results were retrieved from remote servers. If I disable connection to computer network now, let's try that actually. Turn Wi-Fi off and try to refresh this page. I'll get response no Internet. And the reason for that is that now I'm not connected to Internet. Let's reconnect back again and let's refresh page once again. And now I see previous result. And that means that you are not able to interact with remote devices without connection to Internet. But of course you are able to browse some local resources on your local device and open up some folders and play some media files if you have them stored locally on your computer. Alright, now somewhere on this page click on the right button of your mouse like that and choose Inspect. Of course, you could follow me along now if you have computer. If you're watching this video on mobile phone, this functionality isn't available there. So let's choose Inspect and move to Network tab. And here click on XHR button, this one. And now let's refresh page. Let's do that by clicking on this Reload this page icon, like that. And you'll see some requests. Let's click on this that has made request to search endpoint, this one. And let me make this window a bit larger. You'll see that my computer has actually made a request to remote URL. Here is this URL. This request was made using HTTPS protocol. And you see host name of the remote server, it is google.com, and afterwards you'll see some search parameters. And for example, here in this section you see query string, computer network. You'll see also here remote address. It is IP version 4 address, and afterwards you'll see TCP port. It is default port for HTTPS protocol. You'll see some response headers, also below you'll see request headers, and actually here you'll see all details related to this single request. That's what happened under the hood when we have simply refreshed page and searched for computer network term. But now question, how our computers are actually able to communicate with remote servers, for example, servers of Google? For that, we need to have some special addresses assigned to our computers or mobile phones or tablet PCs. Let's now verify connectivity settings on our computers. Let me go to this desktop here and click on connection status icon, this one. I am currently connected over wireless network, and I'm more than sure that you are also using wireless network right now if you're using laptop or computer. If you are using mobile phone, you are probably connected either to wireless network same as I on my computer, or you are using some sort of GSM cellular network, like 4G, 5G, LTE or something else. Alright, here I see information about wireless network I am currently connected to. And if I go to Network Preferences, and here go to Advanced, TCP IP, I'll see actually information about addresses that my computer is using right now. Here I see IP version 4 address, here it is. It was assigned to this computer dynamically over DHCP protocol. Also I see here subnet mask in such format 255.255.255.0, and also I see IP address of the router. And it is actually IP address of the wireless router I am currently connected to. And this wireless router also acts as DHCP server. And that's that router, that device that has assigned this IP address to my computer. Also afterwards I see DNS tab. And here is list of DNS servers. In my case, address of the DNS server matches address of the router. That means that in my case, DNS server is actually wireless router I am currently connected to. If I go to hardware section, I'll see information about MAC address. And you see that this information is actually hard-coded. It is not assigned by router or by some other devices, because this address is actually built-in address into the network interface card that is installed in my computer. And that means that my computer has hardware address, this one, and it also has IP address that was assigned dynamically by wireless router. Alright, that is information about wireless connection on my computer. Of course, you could connect multiple devices to the same network. And usually, if you're using, for example, wireless network at home, you have multiple devices connected simultaneously, like your laptop, your TV, your mobile phones, and so on. Now let me grab my phone and quickly show you same information about IP addresses, MAC addresses, and so on, but on my mobile phone. Alright, let me mirror screen of my mobile phone to my computer. Here it is. Let me make it a bit smaller like that. And now let me go to settings of internet connection. Here is this icon, and here you see that I am currently connected to the same network as my laptop. Here it is. But actually this name and the name here in status bar on my computer are different, but they are actually active on the same wireless router. Great. Let me go to details of this connection. Here I see information about signal, about frequency, security, and if I go to advanced, you'll see network details. And again, same as on my computer, I see here MAC address. Here it is hardware address on this phone. Next to it, I see IP address, and notice that IP address starts same as on my computer with 192 and so on, but last section is different. On my computer, this section is 182, and on mobile phone, it is 116. That means that IP addresses are different. MAC addresses are different as well. Here you see this information. Alright, also you see gateway, and gateway is the same here and here. And that means that those two devices, my laptop and my mobile phone, are using same default router for outgoing connections to internet. Subnet mask is the same here and here. DNS server is same here and here. Also below on mobile phone I see information about IP version 6 addresses. Great, that's a quick overview of network details on my laptop and on my mobile phone. And actually main outcome of this lecture, practical lecture, is that each device that is connected to internet must have some special addresses in order to be able to communicate with other devices. And actually I am able to screencast screen from my phone to this computer thanks to computer networking, thanks to those addresses assigned to my computer and this phone. Without internet connection on my phone, I won't be able to do that. That's power of networking. Alright guys, that's all for this practical lecture. I hope you enjoyed it and hope you have also verified network details on your devices you are using right now. And please no worries if you don't understand some sections, we will talk about all those details in this course. And you'll learn what is DHCP, what is DNS, what is MAC address and so on. And you will of course learn how different devices communicate with each other. Great, that's all for this lecture, and next let me talk about TCP/IP model and explain you how it relates to communication between different devices in computer networks. I'll see you guys next. Bye bye. So, network devices communicate between each other, and if they do so, they form actually computer network. And there are many different kinds of devices that could be connected to computer network. And now it's important to understand how devices actually communicate in the computer network. And process is a bit similar to the process how actually people talk to each other. And when you talk to some other person and you are talking different languages, for example, I'm talking English and you are talking Spanish, then we won't be able to understand each other, because we are talking different languages. In the same way, network devices are not able to understand each other if they use different protocols, for example. And there are many different protocols that each device in the computer network utilizes. That's why it is important to understand how those protocols actually are used and how they interact with the protocols on other side. And for that purpose, there are different models that describe actually how computers talk to each other, and such models are TCP/IP model and OSI model. And in this course, we will talk about both models and we will compare them as well. But before diving a bit deeper into the theory, let's do some practice activities in order to make you understand what actually happens when you establish connection with a remote device and which protocols are actually used. And you'll understand that it is really important to clarify what actually happens under the hood using such models as TCP/IP and OSI. Let's dive into it, and next let's install a program called Wireshark, and afterwards we will analyze a couple of different sessions that will be established from our local computer to some remote server, and afterwards we will get back to TCP IP model and I'll explain what it means and why it is actually useful. Let's get started with Wireshark next. Alright, before diving a bit deeper into the theory and explain TCP IP and OSI models, let's now install a program called Wireshark and try to capture some packets that are going from your computer. Please navigate to wireshark.org and click here Download button. Notice that Wireshark is available for Windows, Mac OS, and also you are able to install it using source code. Let's install it in my case for Mac OS. I'll click on this link. It will be downloaded. Let's wait a bit. Alright, installation package was downloaded. Let me go ahead and install it. Opening Wireshark. And now let's simply drag Wireshark into applications folder like that. Copying. And also, in order to be able to capture packets that are going from my computer and back, I need to install this package. Let me click on it. Change mod BPF. Let's click continue here and install. Type my password. Installation was successful. Great. Now I'm ready to capture some data. Let's open up Wireshark. Click open here. Application was opened, and now we are ready to start capturing of the packets. But before doing that, please ensure that Wireshark has selected correct network interface here in this list. In my case, it has chosen wireless adapter with name EN0. And on this small graph, I already see that there is some data sent via this interface. If in your case interface was chosen incorrectly, please choose correct one by simply clicking on it like that. Great. Wireless adapter is selected in my case and I am ready to start capture. In order to do that, simply click on this blue icon. Packet capture was started and now I should see already some data here. And yes, I see some ICMP version 2, MDNS or ARP protocol packets. Let's now generate some additional data. In order to do so, let's go back to Google Chrome and simply refresh this page like that. And now let's go back to Wireshark. Now I see some additional packets like TCP and TLS v1.2. Also I see some ARP requests. Great. Now let's simply stop capture and let me quickly explain you what we actually see here. Wireshark demonstrates now all packets that are sent from your computer and back. And here in this column source you see source IP address. Here is destination IP address. Here is protocol like UDP or TLS. Here is the length of the packet and here is some additional information. For example, I see that this packet was sent from port 443 to port 51513. Great, let's now apply some filtering to the packets and here in this filter field simply enter TCP, like that. And now you'll see only TCP packets. And for example, in this packet, let me select it, I see in this window below that it contains a bunch of additional information. Not just protocol information and not just IP addresses. It has multiple sections. Like TCP section, if you expand it, you'll see those ports that are shown actually here as well, like 443 and 49501. Also, you see some additional data like sequence numbers, acknowledgement number, and so on. If you look at other section, this one for example, Internet Protocol version 4, you'll see data about IP addresses that were used in the packet. And if you'll have a look at source or destination IP address, one of them will be actually IP address of your computer. And in my case, this IP address is IP address of this computer. I can prove that by clicking on the network status icon with Alt key pressed, and I see here IP address of this computer. It ends up with 182. Same address I see here. And that means that this packet was sent from a remote server with this IP address to my computer. Also, there is bunch of other fields in IP version 4 section, like total length, identification, fragment offset, and so on. Also, there is another section called Ethernet 2, and in this section I see source and destination MAC addresses. And destination MAC address is MAC address of my wireless network card. And you see that Wireshark has replaced part of the MAC address with text. In my case, this Apple. Also in source MAC address you see also replacement, and here in my case I see TP-Link T. And it is a sign that the source MAC address is actually MAC address of my wireless router. So this packet was sent from my wireless router. Great. In this last section you see frame information, and that is the actual data that was sent over wireless or wired adapter. In my case, this packet was received via Ethernet 0 interface, and that's why here I see that interface ID EN0. Here it is. If I expand this section, I see interface description Wi-Fi. Also, I see such data as frame number, frame length, and so on. Great. That's an overview of sections that are present in this specific packet. You could, of course, analyze other packets. For example, if you replace TCP with DNS here and press Enter, you'll see DNS requests and responses. And actually, all mentioned before sections like frame, Ethernet 2, IP version 4 are present in this packet as well. But instead of TCP, I see here UDP section. Also, I see additional domain name system section. It is an actual DNS query. And that means that devices in computer network communicate using strictly defined rules and strictly defined protocols. If some device will try to send packet without Ethernet 2 header or without IP version 4 header, it will be simply discarded by the router or by switch. That's why if we want to talk to other devices, again, we need to follow strict rules. Alright guys, that's all for this quick overview, and now we will stop using Wireshark, but no worries, we will get back to it a bit later in this course, and we will analyze each of those headers in greater details. But for now we need to dive into some theory, and using diagrams I'll explain you what is TCP, IP and OSI models, and why we actually need to know about them and how they will help you to understand how different devices communicate in computer network. Alright, let's continue with TCP IP model. I'll see you next. Bye. Let's first answer the question, why do we actually need computer network? We need computer network when we want to receive or send some data. For example, you want to download some video from remote server or watch it online. Or, for example, you want to play a game online or make a call. Or, for example, download email or something else. And in order to communicate with other devices in the computer network, send or receive some data, you need to use some applications. And some applications are installed out of the box in each operating system, some of them need to be installed additionally to that. For example, Google Chrome is the most popular web browser application that allows you to download resources from a remote server and display them in the web browser window. Or, for example, you could install some gaming applications like Call of Duty or World of Tanks and play with other players using computer network. Also, you could use Gmail or Outlook applications in order to receive and send emails. And each application usually uses one or several protocols. Protocol is actually standard of communication that allows to talk same language between different devices. And for example, such applications as Gmail and Outlook could use SMTP protocol, that stands for Simple Mail Transfer Protocol. There are also other protocols that allows you to send and receive emails, for example, POP3 or IMAP. Such applications as Google Chrome, Firefox or Internet Explorer allow you to browse Internet, and they use such protocols as HTTPS or HTTP. HTTPS is actually a secure version of HTTP, and it actually encrypts all communication between two different devices. And it is of course more popular than HTTP protocol. Also, I have added to this list Nginx. Nginx is software that allows actually to serve web pages on server side. It means that Google Chrome could communicate with Nginx remote server, and this server will send some data via HTTPS or HTTP protocol to web browser, Google Chrome or Firefox or Internet Explorer. Also, for example, using such application as FileZilla, you are able to download or upload some files to remote servers using File Transfer Protocol. There is also a secure version called FTPS, File Transfer Protocol Secure. Or another example of the application is Terminal. And inside of the terminal, you could use such protocol as SSH, that stands for Secure Shell, and using such protocol, you could connect to remote servers, running, for example, Ubuntu or Debian operating systems. And via this protocol, using computer network, you could manage remote servers. And for example, via SSH, you could connect and set up some web server that will serve web pages for Google Chrome or other web browsers. That are some examples of applications. But please note that all those applications are so-called top-level applications. And each of such applications actually serves some specific purpose, and it sends valuable for you data. For example, in Outlook or Gmail, you receive or send your emails that are important for you. Or, for example, you download some video from YouTube and watch it online. And of course, such protocols are using some other protocols, underlying protocols, that allow actually to communicate between different devices and transfer actual data. And that's why application is a top level in TCP/IP model that actually allows us to describe how communication between different devices happens in computer network. Let's talk a bit more in details about TCP/IP model after the small pause. See you next. Alright, let's now talk in greater details about TCP/IP model. But first of all, let me explain you difference between model and standard or specification. Model actually only describes how devices communicate in computer network. On other side, there are different standards and specifications that describe actual communication. That's why TCP/IP model is just used for understanding and explaining how different devices communicate between each other, nothing else. And we will start with TCP/IP model, and afterwards we will talk about OSI model. So, TCP/IP model contains 4 different layers. Application, it is the top level, then transport, internet and network access. And name of this model was constructed using 2 different major protocols that are used in computer networking. And such protocols are TCP, that stands for Transmission Control Protocol, and IP, that stands for Internet Protocol. TCP belongs to transport layer. Here you see that. IP belongs to internet layer. But let's start from application layer and talk a bit more about each separate layer. Great. Application layer. We have just talked with you about different applications and different protocols that are utilized by different applications. And here you see some examples of applications like HTTP, FTP, DNS or DHCP. And those protocols are used at the top level of TCP/IP model. And that's actually why we need computer networking. We need to transfer or receive some data using specific protocols and use resulting data in some applications. But underneath application layer, there are 3 other layers called transport, internet and network access. So what is the purpose of transport layer? It establishes end-to-end communication and reliably delivers data between two different endpoints in computer network. And there are two different protocols that are used on transport layer, and they are TCP, again this stands for Transmission Control Protocol, and UDP, User Datagram Protocol. And actually difference between those two protocols is that TCP establishes end-to-end session between two different endpoints, reliably sends data. What does it mean reliably? It means that if some data was lost on the way from one endpoint to another, then TCP will attempt to retransmit such data. And this process will be fully transparent for application layer. And also TCP has teardown process of the connection. When data was sent, then there is no need to have TCP session alive and it is terminated. UDP, on other side, does not establish session, it simply sends data from one endpoint to another. There is no connection setup or connection teardown. That's why we actually can't say that UDP sends data reliably. Only TCP does so. TCP is reliable protocol, UDP is unreliable. Great, that is a transport layer. Next one, internet layer. Responsibility of this layer is to connect different networks, find optimal path between different networks, and send packets from one network to another. And there are several protocols that work on this layer of the TCP/IP model, and they are IP version 4, IP version 6, or ICMP. Also, except those protocols, there are other protocols called routing protocols that are responsible for discovery of different networks, finding optimal path, and afterwards routing of the packets from one network to another. That is the internet layer. Great. And finally, there is network access layer. This one. It is the lowest layer in TCP/IP model. And this layer is responsible for transmission of the data over the physical media. And there are also protocols that are used on this network access layer. An example of such protocol is Ethernet. Also, there are different technologies that are used on network access layer, like Bluetooth, Wi-Fi or CDMA. But main responsibility of network access layer is to send actual data over the physical media. And there could be different types of medias between different endpoints that are connected to the computer network. For example, packet from my computer to some remote server on other side of the ocean goes first via wireless connection from my computer to wireless router. Afterwards, using Ethernet cable, it goes from wireless router to devices on the internet provider side. And afterwards, there are fiber cables that interconnect different internet providers and connect different continents. That's how different medias could be used on the network access layer. That is a TCP/IP model. And main idea here is that layers in TCP/IP model are fully independent. It means that application layer does not care about what happens on transport layer. Same applies to transport and internet layer. Transport layer is independent of the internet layer. Same, internet layer is independent from the network access layer, and so on. Layers are fully independent. Alright, in short, there are 4 layers in TCP/IP model: application, transport, internet, and network access, and computers communicate using different protocols on different layers. Great, let's now proceed, and next let's quickly get back to Wireshark and try to observe whether structure of each packet corresponds to this model or not. I'll see you next. We have just discussed the TCP/IP model. It contains 4 different layers: application, transport, internet, and network access. And now let's quickly get back to Wireshark, program that we have installed before, and let's quickly analyze again several different packets and try to align different protocols to different layers of TCP/IP model. Let's do so. Let's go back to Wireshark and let's again capture some packets. if you see list of the packets here, please simply restart capture by clicking on this blue icon. And also please ensure that there are no display filters applied here in this input. Alright, let's restart capture. I already see some packets like TCP, TLS, v1.2. If you want to generate some additional data, simply open up a connection, for example, to google.com or instagram.com like that. And let's go back to Wireshark and stop capture. Here I see different protocols like UDP, TCP, and let's examine, for example, any TCP packet. For example, this one. In this packet, there are different sections of information here in this window. And basically, now we could try to align different sections from this input to TCP IP model layers. TCP protocol, Transmission Control Protocol. It belongs to transport layer of the TCP IP model, this one. It is responsible for establishment of the end-to-end communication between two different devices in the computer network. Next section, IP version 4. This section belongs to Internet layer, this one, and it is responsible for connection of different networks and routing of the packets between different networks. That is a IP version 4 section, this one. Next section, Ethernet 2. This section belongs to Network Access layer, and it is responsible for transmission of the data over the physical media. And here, this section, frame section, also belongs to Network Access layer. And in my case, I'm using wireless connection. I can prove that by looking at this subsection. That's how different sections in this output correspond to different TCP IP model layers. But you may ask me, where is actually application layer for this packet? This packet, specific packet, doesn't have any application-specific data. Let's now try to examine other packet, for example, let's say this one, UDP. It also has such sections as frame, Ethernet 2, IP version 4, and instead of TCP, you see here section UDP. UDP belongs to transport layer as well, same as TCP protocol. And also here we see additional section called data. And this data actually comes from application layer, this layer. But in this output, we actually don't see which application has received or sent this specific piece of data. But we could guess that it was Google Chrome, because we see here source port 443, and that is a port of HTTPS protocol, and it could use either TCP or UDP protocols. And in such case, this data belongs actually to Google Chrome. Great, let's examine other protocol. For example, let's apply filter and search for DNS again. And here in those sections you see again frame, Ethernet 2 that belong to network access layer. Next you see IP version 4 that belongs to internet layer, this one. Next you see UDP protocol. It is transport layer, and finally you see DNS system query, this one. DNS is application layer protocol. You see here it as an example in this list. And that means that now in this output it becomes clearer why we see actually different sections and why they are actually separated. Great. Notice that those two different sections, frame and Ethernet 2, actually belong to the same network access layer of the TCP IP model. Also, application layer itself could be separated into other layers. That's why there is other model called OSI model, and it has 7 different layers instead of just 4. That's why let's quickly discuss what is OSI model next. We have just mapped different sections from the output in Wireshark capture to different layers in the TCP IP model. And we have found out that there are at least 2 different sections called frame and Ethernet 2 that are mapped to the same layer in TCP IP model. That's why there is other model called OSI model that stands for Open System Interconnection, and this model has 7 different layers. And honestly, this model is better for understanding of what happens actually between two different devices in the computer network, and it is better for educational purposes. That's why let's discuss now this model. I'll talk about each layer separately, and afterwards we will compare OSI model and TCP IP model. Great, let's start from application layer, it is layer 7. At this layer, same as before, there are different applications and different protocols. For example, such applications as Google Chrome or WhatsApp belong to application layer. Next layer is presentation layer, it is layer number 6. And this layer is responsible for translation, encryption or data compression for the application layer. Let me show you an example of presentation layer. Let's go, for example, to next step where I have opened connection to google.com, right button click here and inspect. And afterwards, please scroll up in this elements section and have a look at head subsection. In this section, you see such tag as meta and attribute char set is set to UTF-8. And this tag actually sets encoding for this page. And using such tag that was actually received from remote server, our local browser understands how to display characters on this web page. So, this part of this page actually belongs to presentation layer of the OSI model. In the same way, for example, some video player can interpret different types of files. For example, such video player as VLC could differently play different types of files like MPEG-4 or AV file. That is a presentation layer. Next layer that is located below presentation layer is session layer, it is layer number 5. And this session layer is responsible for session establishment and termination. And we will have a look at some examples of the session layer protocols a bit later. And please note that session layer protocols may be present or not depending on the case. And actually, we have seen that sometimes there is even no application data. So last section in output in Wireshark, we have seen that it was TCP or UDP. It is also possible. That's why I have told you that model is just model. It does not actually set strict rules for communication. And that's why in some cases some protocols may be present on some layers, in some cases not. Great, let's proceed. Next layer is transport layer. And this layer, same as in TCP/IP model, is responsible for data transmission over the network using such protocols, for example, as TCP or UDP. Afterwards, there is network layer, and this layer is responsible for selection of the best path from source to destination and actual routing of the data from source to destination. It is a network layer. Afterwards, there is data link layer, it is layer number 2, and this layer is responsible for communication with physical layer, dealing with some errors that may occur during communication between different devices via some physical media. For example, some errors that may occur due to some interference in wireless network or something else. And this data link layer, in fact, has two different sublayers. And those sublayers are called Media Access Control, shortly MEC, and Logical Link Control, shortly LLC. And basically, MEC sublayer is responsible for physical addressing of the devices on data link layer, and LLC layer is responsible for communication with physical layer. And basically, if we compare such technologies as Bluetooth or Wi-Fi, Media Access Control sublayer is the same for both cases, but LLC sublayer are different, because physical media is different in both cases. And finally, there is physical layer, it is the lowest layer in OSI model, layer number 1, and this layer is responsible for transmission of the data over the physical media, like Ethernet, Wi-Fi, Bluetooth, LTE, 5G or something else. There are 7 different layers in OSI model. And again, this model is better for explanation and educational purposes. Great. Next, let's talk about bits and bytes, and I'll explain you what is bit and what is byte. I'll see you next. Bye-bye. Let's now talk about bits and bytes. Bit is the smallest basic unit of information, and the bit stands for binary digit. And one bit could be represented either with 0 or with 1. And when you transmit binary digits over physical media, different physical medias transmit bits differently. For example, in fiber media optic, 1 stands for presence of light and 0 stands for absence of light. When you transmit data over a wireless network, then different values 0 or 1 could be modulated differently using different types of waves. That's are bits. And actually, when you transmit any data over any media, all data will be finally split into smallest pieces possible, and those pieces are bits. Great. Next piece of information is byte, and byte consists of 8 bits. And here is an example of byte. For example, 10001101. It contains exactly 8 bits. Also, one byte is called octet. And for example, IP version 4 IP address consists of 4 bytes or 4 octets. Great, but why one byte contains exactly 4 bits? Answer is here. When you want to transmit some characters like A, B or C, you also need to encode them somehow. And Unicode is one type of encoding of the characters. And using Unicode, you could encode each character using 8 bits or 1 byte. That's where term byte actually originally came from. And symbol A could be encoded using such 8 bits 011000001. For example, number 4 could be encoded using such sequence of bits. Exclamation mark is encoded like this. Greater than sign is encoded like this. So different Unicode characters are represented using different sequences of bits. And each symbol is exactly 8 bits long. That's bits and bytes. Again, bit is smallest non-dividable piece of information, and it is used not just in computer networking. It is used, for example, when you describe processor architecture. You have heard about terms 64 bits or 32 bits architecture. Alright, that's all about bits and bytes, and next let's talk about PDUs, Protocol Data Units. I'll see you next. We have just discussed what are bits and bytes. And you now know that a bit is actually smallest piece of information that could be sent over physical media, like wireless connection or wired connection. And now let's discuss what are actually PDUs, Protocol Data Units. PDU is smallest piece of information that is related to specific layer in the OSI model. And that's why we could say that bits are PDUs for physical layer of the OSI model. When I say bits, I mean transmission of the data over the physical media, and I am talking about physical layer of the OSI model. Let's discuss other PDUs for other layers. Actually, you see that I have divided all 7 layers of the OSI model to 2 different sections: media layers and host layers. And actually, first 3 layers of the OSI model, physical, data link and network, are media layers. And next layers, starting from transport and ending with application, are host layers. And that means that host, for example, mobile phone or computer, prepares some application data and afterwards sends it to media layers in order to get this data transmitted over the network. Great, let's continue with PDUs. If we are talking about data link layer, then PDU for this layer is frame. Frame is the smallest piece of information on data link layer, for example, Ethernet frame. On the next layer, network layer, PDU is packet. If I say packet, I mean network layer of the OSI model, and I could say IP version 4 packet or IP version 6 packet. Next layer transport has PDU called segment. And there could be TCP segments or UDP segments. Segment is the smallest piece of information on transport layer of the OSI model. And finally, data. Data is PDU that is common for those three layers: application, presentation, and session. If I say data, I mean some data that is sent or received by specific application. And also here in this last column you see some examples of the protocols that are used on different layers of the OSI model. Actually, we have discussed already some of them, and they actually use different PDUs. They work with different PDUs. For example, HTTP, FTP protocols use data, and they transmit or send some data. On the next layer, data representation, we also work with some data. We encode some data, for example, using encoding UTF-8 or something else, or we encode some images using different encodings like JPEG and so on. Next layer, session layer, also works with data. Data is PDU for this layer, and it is responsible for establishment of the session and session control. And examples of the protocols that are used on session layer are L2TP and H245. L2TP stands for Layer 2 Tunneling Protocol, and using such protocol you could establish tunnel between different endpoints in computer network and send some Layer 2 frames over this connection. Using H245 protocol, we could control phone calls established over computer network. On the next transport layer, we work with segments, so segment is PDU for transport layer, and here we use such protocols as TCP and UDP. On the next layer, network layer, such protocols as IP version 4 and IP version 6 work with packets. Packet is PDU for network layer. Next, data link layer is responsible for preparation of the data for physical layer and physical addressing. An example of the protocol that is used on data link layer is Ethernet. And PDUs for data link layer are frames. And finally, bits are sent over the physical media. And we could name here such protocols and technologies as Ethernet, Wi-Fi, and Bluetooth. Great, that's our PDUs, protocol data units that actually describe smallest pieces of information on different layers of the OSI model. And I'll use such terms as bits, frames, packets, and segments a lot in this course. And please remember them, because when I'll say packets, I'll mean network layer of the OSI model, and I'll talk about IP packets, IP version 4 or IP version 6 packets. If I'll say frames, I'll mean that I am talking about data link layer of the OSI model. Great, that's all for this lecture, and next let's compare OSI and TCP IP model. I'll see you next. So far we have talked about TCP IP model and OSI model. And we have mapped some protocols to different layers of the OSI and TCP IP model. And now let's quickly compare those two models. But before doing that, I want to emphasize that those models under no means specify exactly how devices communicate between each other. For example, there are some protocols that couldn't be mapped to one specific layer. Instead, they work on multiple layers. An example of such protocols is IPsec, IP Security Protocol. It actually works on session, transport, and network layers simultaneously. It uses a set of other different technologies and standards. And that's why, again, OSI and TCP/IP are just reference models that could be used for better understanding of what is happening between devices in computer network. Great. Let's now finally compare OSI and TCP IP model and map layers of the TCP IP model to OSI model. So, layer 4 application layer of TCP IP model is actually combined layer, and it combines those three layers of the OSI model: application, presentation, and session layers. Why is that? Because usually application itself, for example web browser, is responsible for all operations that happen on those three layers, like presentation, session, and application. Next layer, transport, is called the same in both models, OSI and TCP IP, and the purpose of this layer is the same in both cases. And TCP and UDP protocols are examples of the protocols that are used on this layer, transport layer. Next layer is called differently here and here, but the purpose of this layer is the same in both models. It is responsible for delivery of the packets from source to destination. And for that we need first actually somehow discover routes and afterwards find optimal paths to destination routes. And that is also responsibility of internet layer in TCP IP model or network layer in OSI model. And finally, network access layer in TCP IP model combines actually two layers of OSI model, data link and physical layer. And sometimes actually you could see that TCP IP model consists of 5 different layers, and you'll see those 2 layers instead of just one network access. Alright, that is the difference between OSI and TCP IP model in terms of naming of different layers, and you see that application layer is present here, and transport layer is present here and here as well. But application layer in TCP IP model combines actually 3 different layers of OSI model. Alright, that's all for comparison of those 2 reference models. And next, let me talk about encapsulation and decapsulation. I'll see you next. We have just compared TCP IP and OSI models. And sometimes OSI model is presented as 5 layers model, and network access layer is splitted to data link and physical layers. And to this diagram, let me show you this version, 5-layer version of the TCP IP model, and using this model explain you what is data encapsulation. Data encapsulation is process of formatting data, and this process adds some additional overhead on each layer. And this overhead is called header. For example, let's say that there is some data that is ready to be transmitted on application layer. For example, let's say we have composed email, and this email is ready to be sent to other devices, to, for example, SMTP server. And this data goes to transport layer. And this transport layer adds its own overhead, own header. And this header is called here segment header, because segment, as you remember, is protocol data unit PDU for transport layer. Afterwards, this modified, let's say expanded data goes to next network layer. And next layer adds to existing data with segment header one more header, packet header. Packet is PDU for network layer. Here is this packet header. Afterwards, data goes to data link layer, this one, and on the data link layer we add one more header, frame header. Frame is PDU for data link layer. And finally, this data, along with all added headers, is transmitted over the physical media. And this data is represented using bits, zeros and ones. That is a process of encapsulation. And notice that previous data and previous headers are not modified when data goes from upper layer to lower layer. It means that transport layer under no means modify this data that it has received from application layer. Same applies to network layer. It does not modify data and doesn't modify segment header. It simply adds its own header, packet header. Same applies to data link layer. It doesn't modify data, segment header or packet header. It adds frame header, and it also adds frame trailer that contains checksum of the frame and is used for error detection, and if this checksum does not match on recipient side, then such frame is simply discarded. And finally again, data is transmitted in bits, and physical layer does not care at all which data it sends. It simply gets some data from data link layer, performs encoding, and sends encoded data over the physical media. That's it. This process is called encapsulation. And again, main idea here is that layers are independent from each other, and each layer adds its own information to existing information received from upper layers. And now let's discuss how this process actually is performed on opposite side. On opposite side, this process is called decapsulation. And when data is received on physical layer on recipient, it goes to ARP layer, data link layer, and data link layer reads only frame header and frame trailer. It does not look into inner headers, packet header or segment header or data. It reads only data that was added at data link layer at the sender, frame header and frame trailer. Afterwards, after processing of the frame on the data link layer on recipient, it goes to network layer, but now without frame header and frame trailer. They are stripped. Network layer reads packet header that was added by network layer of this sender. It removes it and afterwards sends data to transport layer. Transport layer reads segment header that was added by transport layer here on the sender, and afterwards data goes to application. So process is opposite to encapsulation. Sender performs encapsulation and sends data via any physical media, and recipient performs decapsulation. Great. Using such approach, we could combine different protocols on different layers of the model. And we could send different data over different medias. We could use different protocols on the network layer. We could use different physical layer technologies, and so on. Application layer doesn't care about that at all. This application, in my case Google Chrome, does not know which technologies I use on data link or physical layers. That is not its responsibility. Its responsibility is prepare some data and simply send it to lower layers. That's it. Great. So, short summary. Encapsulation is process of adding some additional data on each layer of the model. And afterwards, decapsulation is performed on recipient in opposite way until data is received by application layer on recipient. Great, that's all what I wanted to tell you about TCP/IP and OSI models. Now let's proceed, and next let's talk about data link layer and specifically Ethernet protocol, and discuss what is MAC address and how MAC addresses are used for transmission of data on data link layer. I'll see you next. Alright guys, in the previous section we have discussed why we actually need computer networking, and also we have talked about such models as TCP/IP and OSI. OSI model has 7 different layers and TCP/IP model has originally 4 layers, but afterwards it has extended and now it contains actually 5 different layers, because network access layer was split into 2 different sub-layers, data link and physical, and those layers are named the same as in OSI model. So now we have good enough theoretical knowledge and understanding of how different devices communicate between each other in computer networks, and now we are able to proceed. In this section we will discuss Ethernet, and Ethernet is the most popular protocol that is used on data link and physical layer of the TCP/IP model. Except Ethernet, there are also other protocols that could be used on data link layer, for example PPP, point-to-point protocol, but in this section we will focus on Ethernet because it is again the most popular protocol that is used in computer networking. And using Ethernet you could transfer data either using wired media or wireless media, and we will talk about all that stuff in this section as well. So let's get started. Let's get started with Ethernet. We have discussed before that in TCP/IP model, TCP is the main protocol that is used on transport layer, and IP is protocol that is used on network or internet layer. And Ethernet is the most popular protocol that is used on data link and physical layers. And basically Ethernet isn't just a single protocol, it is a set of different protocols that define communication between different devices on data link and physical layers. And actually there is an organization called IEEE that creates standards, and if some manufacturers want to produce equipment for network communication, they must strictly follow those standards in order to allow their devices successfully communicate with other devices in computer network. Because same as with cards, there could be many different manufacturers, but if they talk different languages, they will not be able to communicate with each other. That's why, again, there are different standards and protocols that must be strictly implemented in hardware. So, Ethernet is a set of standards, and there are such standards, for example, as 802.3. It is actually original Ethernet standard that defines the communication between devices if physical media is wired media, like copper cable or fiber cable. And also there is a set of standards that start with 802.11, like .11a, .11b, .11ac, .11n, that define communication between devices if media is wireless. And let me quickly refer to my network connection and click on details here, and you'll see that in my case physical mode is 802.11ac. And basically it is implementation of the IEEE 802.11ac standard. And this standard covers data link and the physical layer communication between devices if media is wireless. And I'm currently using wireless connection. So that's Ethernet. Again, this set of different protocols that define how devices communicate on data link and physical layer. Wonderful. Next, let's proceed, and I'll explain you what is the difference between copper cables, fiber cables, and wireless connection. I'll see you next. In the previous lecture, we have discussed what is Ethernet, and it is actually a set of different standards that define how devices must communicate in computer network on data link and physical layer. And actually, data link layer is almost the same in all standards. There are just small differences, and we will get back to it a bit later. But physical layer could be different in different cases, and you could use such medias as copper cable, fiber cable, or wireless. And let me now briefly explain you difference between all those medias. Let's first discuss what is copper cable. Copper cable is physical cable, and this copper cable consists of 8 different wires that are actually combined into 4 pairs like that, and those pairs are called twisted pairs. So each pair of wires actually twists. And also every single small wire in this copper cable has a special plastic shield with different colors like blue, white, blue, orange, white, orange, and so on. And those colors are made on purpose in order to allow you to distinguish different small wires on different ends of the same cable. Also, all 4 pairs of this copper cable have a common plastic shield, and additionally to that, there could be additional metal screen between this plastic shield and those pairs of wires. And that's why there are different types of cables called unshielded twisted pair and shielded twisted pair. And also there are different categories of copper cables called category 5, category 5E, category 6, 6A or 7. And depending on the category of the cable, you could transmit data on different speeds. For example, using category 6A or 7 cable, you could transmit data at speeds 10 gigabits per second. It is actually highest speed for copper cables. I'll explain you what is 10 gigabits per second or 100 megabits per second in one of the next lectures. Alright, also copper cable has so-called connectors on two ends, and standard for those connectors is here. It is RJ45. And it looks like that, and I hope that such connectors are familiar to you and you have used such cables to connect your devices to network devices. So, that's our copper cables. Let's now discuss fiber cables, and actually why fiber cables are used more often for long-distance transmissions. So, using fiber cable, you could transmit data using actual light. And 1 stands for presence of light in the wire, and 0 stands for absence of light in the wire. And there are different types of fiber media or fiber optics called single mode and multi-mode. And basically using single mode cables, you could transmit data using fiber cables at higher rates and at longer distances than using multi-mode fiber. And single-mode fiber cables, of course, are more expensive than multi-mode cables. And basically, using fiber optics, you could transmit data at the rates up to 100 gigabits per second. It is much more than with copper cables. And when we are talking about connections between different internet providers or between different continents, of course, single choice there is fiber optic. Copper cables are not used there at all. First reason is that fiber cables have much higher transmission rates than copper cables, and second reason is that the length of a single fiber cable can reach 100 kilometers. That is, of course, much higher than maximum length for copper cable. That is usually 100 meters. But of course, there is a disadvantage of using fiber cables, and there are actually some of them. First disadvantage is actual cost of fiber cables, and second one is cost of transceivers for fiber optics. Here on this picture you see actual example of connector that is used for transmission of data over fiber cable. And also, except those connectors, there are ports on network devices that will be connected to those connectors actually, and the cost of those connectors and ports increases with increase of speed rate of fiber cables. Also here on this picture you see set of different fiber cables, and that's how actual cables look like between different continents, and those cables are actually floating under sea level, and they contain a lot of different fiber cables combined into very large cable. So, that is fiber connection and fiber cables. Again, they are expensive, but of course they allow you to transmit data at high rates. And of course there are almost no physical impacts, external physical impacts on fiber cable, and in comparison with copper cables, of course fiber cable here wins as well. And finally, it is possible to use wireless media in order to transmit Ethernet frames. And there are different IEEE standards, as we have discussed before, like .11a, .11n or .11ac that define actual communication using wireless media. And basically different standards define such details as, for example, transmission over different channels, wireless channels, modulation and demodulation, and usage of multiple channels simultaneously. And of course, wireless connections are more popular at home and in small offices. But of course, it is possible to use the wireless connections in large offices and create so-called mesh networks that will cover even multiple floors of the large building. And you could use your laptop or mobile phone and travel with it between different floors and even don't lose connection to wireless access point or wireless router. So that is a wireless connection. And of course, wireless connectivity has a lot of disadvantages. And the first disadvantage is that wireless media is common for everybody. And of course, different devices could start transmission on the same channel and create so-called interference, when different signals overlap and create actually unrecognizable signal. And that is actually main disadvantage. And second disadvantage is that wireless distances are actually limited, and in Wi-Fi standards you're not able usually to transmit data if you are more than 100 meters far from access point or wireless router. That is a second limitation. But of course, there is a huge advantage of using wireless media, and this advantage is, of course, flexibility. You are not sticked to wired cable, and you could travel with your laptop or mobile phone to different places, and if you're at home, you could work, for example, either at kitchen or in your living room or somewhere else, or take your laptop and go outside, let's say. So that is a huge advantage of using wireless media. And most network devices, even laptops, for example my laptop, don't even have ports for connection of Ethernet cables like that. And if you want to connect cable, you need to buy first some external adapter. And that's why wireless is the most popular choice again for home usage and for small offices and even for large offices. And copper cables and fiber cables are mostly used for connectivity between internet providers and connectivity from your home, let's say, to internet provider. So let's summarize. Copper cables are cheap and they use standardized RJ45 connectors. And there are different types of cables like category 5E, 6 or 7 that allow you to transmit data at different rates, up to 10 gigabits per second. But the maximum length of Ethernet cable, copper cable, is 100 meters. Fiber optic cables are much more expensive, same as fiber connectors. But using fiber optics you could transmit data at much more higher data rates, and maximum length of fiber cable is up to 100 kilometers. And the wireless media is the most popular choice for home usage and in small and even large offices in order to connect devices of end users to computer network. That means that there is no preferable choice of media for Ethernet, and all those medias are actually utilized when you transmit data from your computer, let's say, to any server in the world. But please note that media type does not impact how devices communicate on upper layers of the TCP IP or OSI models. Network layer or transport layer don't know about the media type that is used on physical layer. Alright guys, that's all for overview of copper, fiber and wireless medias, and next let's proceed and let's discuss what is actually network interface card, or shortly NIC. I'll see you next. We have just discussed that Ethernet supports different media types on physical layer of the TCP IP model, such as copper cables, fiber cables and wireless. And basically, if a specific device wants to communicate with other devices using Ethernet, it must have specific controller. And such controllers are called Network Interface Card or Network Interface Controller, shortly NIC. And different devices actually could have different controllers, and usually such devices as mobile phones or laptops have such controllers already pre-installed by manufacturer. And there could be, for example, such kind of NICs that could be installed inside of the desktop computers, and here you see actually RJ45 port, and you could connect to this port some kind of copper cable with RJ45 connector. Here is an example of the internal wireless NIC that is installed inside of the laptop. Another example is external wireless adapter that is connected to laptop or desktop via USB. One more example is of a wireless NIC that is installed inside of the desktop computer. Here you see a pair of antennas. Different network devices like switches or wireless access points may have multiple NICs installed. For example, here in this switch you see 8 different ports, and each port is basically a separate controller, separate NIC. In this example you also see several ports, like 4 ports combined together, and they actually also consist of 4 different NICs. And actually this wireless device and this switch have the same ports, and using copper cables with RJ45 connectors you are able to connect those devices together. Or you are able to connect a desktop computer with such NIC to this switch. That's because of standardized ports or standardized interfaces. All of them are Ethernet interfaces. Again, here in those examples they are wired, and in this example or this example it is wireless connection. Great. Also you see that some devices like this one support wireless NICs and wired NICs. You could connect some end-user devices like desktop computer using copper cable, using wired connection, and utilize those ports on this wireless router or access point. And other devices like mobile phones or TVs could be connected wirelessly using wireless connection. Alright guys, that's all about network interface cards. Again, they are hardware controllers that allow you to utilize actually Ethernet standards. And there are wireless NICs or wired NICs. So, every network interface card has built-in hardware address. And this address is called MAC address. Let's discuss what is MAC address next. In the previous lecture we have discussed what is NIC, and now you know that it is network interface card, and there could be wired NICs or wireless NICs. And every NIC must have unique hardware address called MAC address. MAC stands for Media Access Control. And this MAC address is built into every NIC by manufacturer. And basically, every MAC address must be unique in the world. So why it must be unique? Answer is following. If I'll place 2 devices with the same MAC address in the same network, they won't be able to communicate with each other. However, if I place those 2 devices in different networks and there will be at least one router between those networks, then those devices may have same MAC address. And we will get back to this topic a bit later. But now you should understand that in the same network, let's say I'm talking about my home network where I connect different devices like laptop and mobile phone, devices must have different MAC addresses in order to be able to communicate with each other. And in this example you see different devices like laptop, PC and phone, and all of them have different MAC addresses. Please notice that MAC address is data link address, and such hardware addresses are required for correct communication via physical media like copper cables or fiber cables or wireless. Also please note that every NIC must have MAC address. You are not able to communicate with other devices if your NIC does not have MAC address. And please notice format of MAC addresses in those examples. Each MAC address contains 6 different sections, splitted by colon. And each section contains 2 different characters. And those characters are hexadecimal characters. And next, let me explain you what is hexadecimal character and what is the difference between hexadecimal and binary characters. I'll see you next. Following previous lecture where we have discussed what is MAC address and where we have seen some examples of MAC address, let's discuss difference between binary and hexadecimal characters. As you already know, in binary there are two different characters, 0 or 1. And in hexadecimal representation there could be 16 different characters. And they are here. They are 0, 1, 2 and so on till 9, and afterwards 6 letters. A, B, C, D, E and F. In total 16 different characters. And basically every single hexadecimal character could be represented using 4 different bits. And here below you see examples of representation of some of hexadecimal characters. For example, 0 in hexadecimal could be represented as 4 zeros in binary format. Here you see 4 different bits. 5 in hexadecimal is represented as 0101 in binary format. B is represented as 1011. And last hexadecimal character, F, is represented as 1111 in binary format. So that's how hexadecimal characters could be represented using 4 binary characters, or 4 binary bits. Therefore, every long binary number that has multiple bits could be represented in hexadecimal format. Of course, you could do that only in case quantity of binary digits in binary number is divisible by 4, because every single hexadecimal character is represented using 4 different bits. And the reason for using hexadecimal representation is it is much more shorter than binary representation. For example, if a binary number has, let's say, 120 characters, in hexadecimal format it will have 120 divided by 4, that is equal to 30 characters, much less characters than in original binary representation. Alright, let's summarize. There are 16 hexadecimal characters, and every hex character could be represented using 4 different bits in binary format. And there is just single reason for usage of hex characters. Representation in hex format is much shorter than representation in binary format. And next, let's discuss structure of MAC address, and you'll learn that MAC address contains actually 2 different parts and it has 48 bits. I'll see you guys next. Now you know difference between hexadecimal and binary format. And every hex character, there are 16 such characters, is represented using 4 bits. Now let's discuss structure of every MAC address. Each MAC address consists of 48 bits, or 6 octets, because 8 bits is 1 octet. And actually there are 2 different sections in every MAC address, and such sections are called OUI, that stands for Organizationally Unique Identifier, and NIC, Network Interface Controller Specific, or Network Interface Card Specific. And what is the reason for this splitting to 2 different sections, OUI and NIC? Reason is following. There are different manufacturers of hardware equipment, including network devices. And as we have discussed before, every MAC address must be unique in the world. And that's why somehow we need to distribute all available MAC addresses among different manufacturers. And that's why each manufacturer has its own range of MAC addresses that it could utilize for assignment to different specific devices. And this section, that is organizationally unique, is assigned by the same organization that creates standards. It is IEEE organization. And again, different manufacturers have different such OUI prefixes. For example, here you see some prefixes for Cisco and Google Incorporated. CC46D6 it is Cisco, and 3C5AB4 it is Google. And that's why if we remember section where we have launched Wireshark and captured some packets, you have seen that Wireshark has automatically replaced the first part of MAC address with such names as Apple or TP-Link, in my case. In your case, of course, those prefixes were different. And that's because Wireshark actually knows which prefixes are assigned to different manufacturers. And of course, having unique OUI prefixes, different manufacturers could decide on their own how to distribute remaining part of MAC addresses space. I'm talking about NIC part. But of course, they need to keep in mind that NIC part must be unique in specific OUI space. And please notice that if a specific manufacturer creates, let's say, network switches that have many different NICs on board, let's say 48 or even more ports, every port must have unique MAC address. And usually, in such cases, MAC addresses go one by one. So first port has specific MAC address, next one will have MAC address plus 1 bit, and so on. So that's structure of MAC address. And in total, there could be really a lot of different unique MAC addresses, and the maximum quantity of MAC addresses in the world is actually 2 to power of 48, because every MAC address has 48 bits. And this maximum quantity of MAC addresses in the world is really huge, and that allows every device at the moment have unique MAC address in the world. So that's structure of MAC address, and that's how different manufacturers assign different MAC addresses to different NICs. That's all, guys, for this lecture, and next let's have a look at different notations of MAC addresses. I'll see you just in a moment. In short, every MAC address consists of 48 bits and has actually two different sections. OUI section that contains 24 bits and it is vendor specific, and another 24 bits are assigned by vendor to each NIC it produces, and it is network interface card specific section. Now let's have a look at different representations or notations of MAC address. Here you see most popular representation, and it consists of 6 different sections, and each section has 2 hexadecimal characters. All sections are splitted using colon, like CF colon, 7A colon, and so on. Also, you may see another representation, like this one, where you'll see dashes instead of colons. It is also possible. One more rare representation is here, where we present MAC address using 2 dots as splitters, and there are actually 3 different sections. Each section is 2 octets long, or 4 hexadecimal characters. Of course, you could represent every MAC address using binary format, but in such format, MAC address will be much longer than in hexadecimal format. That's why hex characters were chosen to represent every single MAC address. This address is not really convenient for use. The most popular choice is this one, and if I have a look at network details in my case, I'll see exactly this representation. Please examine format of MAC address in your case for your network interface card. Alright, guys, that's all for MAC addresses notations, and most popular again is this one. It contains 6 sections divided using colons. Great. Let's now finalize discussion about MAC addresses and structure of each MAC address, and also let's pause for a while discussion about Ethernet. And next I want to talk about such terms as bandwidth, jitter, and latency. I'll see you guys next. Now let's pause for a while discussion about Ethernet and the data link layer of the TCP/IP model, and let's now talk about network characteristics. It is very important to understand those characteristics now, because I have already mentioned briefly what is, for example, bandwidth when I was talking about copper cables and fiber cables. And you could remember that capabilities of copper cables go up to 10 gigabits per second. And fiber optics could transmit data up to 100 gigabits per second. That's why now it's a very good time to talk about such terms as bandwidth, throughput, latency, and jitter. And let's start discussion with bandwidth. So what is bandwidth? Bandwidth is the maximum amount of bits that could be transmitted over specific link or connection in specific amount of time. And in this example, you see connection between this laptop and this server. And I have shown that the bandwidth here is 5 megabits per second. It means that it is possible to transmit over this single connection 5 million bits per single second. But please note that it is a maximum capability of specific link, so maximum possible bandwidth. And there are following possible measures or values for bandwidth. 1 kilobit is equal to 1000 bits. For example, if someone says you that bandwidth of specific link is 100 kilobits per second, it means that this link is capable of transfer of 100,000 bits per single second. Next value is megabit, and 1 megabit is equal to 1 million bits. So 1 megabit per second is 1 million bits per single second. Next value is 1 gigabit. It is 1 billion bits. Afterwards comes value 10 gigabits. It is 10 billion bits. And afterwards comes, it is actually final value, and I have not seen links that are capable of transmission of more than 100 gigabits per second. And 100 gigabits per second is actually 100 billion bits. Of course, you could combine multiple links together and achieve higher bandwidth, but a single link is not capable of transmission of more than 100 gigabits per second. So this maximum value. To summarize, bandwidth is measured in bits per second, and possible values are in kilobits, megabits, and gigabits. And basically, using such information, you could calculate bandwidth per minute or per hour. And if bandwidth is, let's say, 1 gigabit per second, then it is equal to 60 gigabits per minute, or 3600 gigabits per hour. That's measure of bandwidth. And now, question to you. What is the maximum available bandwidth between this laptop and this server? Answer is very simple. You need to find minimum value among all values of all links on the way between this laptop and this server. And in this example, here is this link. And bandwidth of this link is 20 megabits per second. That's why let me make it in other color, and that will be actual available bandwidth, maximum possible available bandwidth between this computer and this server. And it doesn't matter that here is 1 gigabit per second link or here is even 10 gigabit per second link. It doesn't matter at all. So we need to find the link with lowest bandwidth available on entire path between two different endpoints. And such link is usually called bottleneck. And when you design any network, you should always take into account that and try to avoid such bottlenecks whenever possible. Alright, that is bandwidth, and again it is measured in bits per second, and possible values are in kilobits per second, megabits per second, or gigabits per second. Okay, that's all about bandwidth, but important note, bandwidth is characteristic of physical media. And when we take, for example, copper cable and say that it is capable of transmission of 100 megabits per second, it is physical characteristic of this cable. Or let's say we talk about wireless connection and we say that maximum bandwidth is, let's say, 200 megabits per second. And it is characteristic of this wireless network on physical layer of TCP/IP model. I'll explain you in next lecture why it is important to mention. So let's next talk about throughput and compare throughput to bandwidth. I'll see you next. Alright, we have just discussed what is bandwidth. And bandwidth is basically physical layer parameter, and it is measured in bits per second. And for example, fiber cables are capable of transmission of data of up to 100 gigabits per second. Copper cables cannot transmit data faster than 10 gigabits per second. And now let's discuss another important parameter and characteristic of each network or each link, let's say. It is throughput. And throughput is actual amount of data that could be transmitted over specific link or specific connection. And let's say that, for example, here is a link between those two devices, laptop and server, and bandwidth of this link is 100 megabits per second. And now question, what is the throughput of this link? This question could be answered differently, depending on which throughput we measure. Let me get back to one of the previous diagrams where we have discussed what is data encapsulation and try to explain you what is throughput here. Notice that on each layer, transport layer, network layer or data link layer, we add some additional overhead to existing data. And for example, let's say that this data is 10 kilobytes in size. On transport layer, we add additional segment header. That is, let's say, several bytes. Afterwards, on network layer, we also add additional header. That is also several bytes in size. Data link also adds its header. And that means that the total amount of data that will be transmitted over physical layer in bits will be larger than initial size of this data on application layer. And that's due to additional headers that are added on the way from application layer to physical layer. And when we say throughput, and when, for example, we want to measure throughput on application layer, then we need to take this data, that is 10 kilobytes in size, for example, and divide it by amount of data that was actually transmitted over physical link. And for example, we have transmitted not 10 kilobytes, let's say we have transmitted 12 kilobytes due to those additional headers. And that means that the resulting throughput will be lower than actual bandwidth of this link. And in this example, it will be, let me open up calculator and divide 10 by 12, and I'll get 83%. And for example, if physical layer bandwidth is 100 megabits per second, actual throughput in this example particular will be 83 megabits per second. It is lower than actual bandwidth. If you want to calculate throughput on network layer of the TCP/IP model, then you need to take this data, including packet header and segment header, as original data, and divide it by actual amount of bits required to transmit this data with those packets over physical media. And of course, for network layer, throughput will be higher than for application layer. That's throughput for different layers of TCP/IP model. And therefore, you could explain how much payload you are able to transfer over specific physical link. And again, if physical characteristic like bandwidth of specific link is 1 gigabit per second, you will be able to transfer 1 gigabit per second, for example, of video files or music. It is not achievable at all, due to all those headers and due to other characteristics of network, like queuing delays, propagation delays, and so on. We will talk about all those parameters a bit later in one of the next lectures. So that is a throughput. Another example of throughput is, for example, network device. Let's say that we are talking about network switch. We will talk about switches in details later in this course, but let's say that we have switch with 24 ports, and each port has bandwidth 1 gigabit per second. It means that total cumulative bandwidth of all ports is 24 gigabits per second. But now question, does switch capable of transmission of 24 gigabits per second simultaneously when all ports are fully loaded? Answer is no. Most switches are not capable of transmission of data when all ports are fully loaded, and real throughput of switch will be much lower than 24 gigabits per second in this example. Same relates to other network devices. Alright, that is throughput, and again it is measured on different layers of TCP/IP model, and also we can talk about throughput of network device in general. Great. Next, let's proceed and let's talk about latency. It is one more important parameter that is taken into account when we talk about network communication. I'll see you next, guys. Alright, guys, we have just discussed what is throughput and what is bandwidth. And you need to remember that throughput will be always lower than actual bandwidth. And if you buy, for example, wireless router and it tells you that speed is 300 megabits per second, it is actual bandwidth of this device. And real throughput will be much lower than this value, especially it is true for wireless connections. Now let's do a quick demo, and actually you could repeat with me, and let's go to speedtest.net and measure speed of your internet connection. Let's simply click go here and see how it will be measured. Now it tests actual download from remote server to my local computer. And you see that values are here in megabits per second. So result in my case is 92.95 megabits per second. It is download. Now it tests upload. And upload is around 94 megabits per second. So here you see my results. Also you see here ping. We will talk about ping just in a moment. But please notice those values. So I have 100 megabit per second connection to internet. And my internet provider has actually sold me such connection. But you see here values lower than 100 megabits per second. And that's what I have just explained to you. Here you see values that actually measure throughput on application layer. And this throughput is much lower than actual bandwidth of the link, and in my case this 92% of entire link. Alright, that's how you could measure throughput of your internet connection. Please notice that it is less than bandwidth, always less. Great, next let's discuss what is latency and what is ping. See you next. We have just successfully measured throughput of our internet connections, and we have seen that it is 8–10% less than actual bandwidth. And now let's discuss one more important characteristic of each network, and it is latency. Latency is very important when we talk, for example, about real-time applications like video transmission or audio transmission. So latency is one-way delay, and it is actually data transfer time from one device to another. And if there are other devices on the way between two devices, like routers, switches, then every such device adds some delay. And actually, latency itself consists of multiple delays. And there are such delays as queuing delay, processing delay, transmission delay, and propagation delay. Let me talk about all those delays a bit deeper. But first, let's answer the question on which layer of the TCP/IP model do we measure latency. Usually, we talk about applications, and it is important for us to make applications work faster with smaller delay. And that's why when, for example, I measure time that takes for video to travel from my computer to another computer, then I talk about application layer. That's why latency is usually applied to application layer of TCP/IP model. And actually I don't care about other layers, but each layer actually adds additional delay, because it takes time to add new headers at transport layer, network layer, or data link layer. It is also delay. So let's talk about different types of delays, and let's start with queuing delay. Let's suppose that I have created email, and the email is ready to be sent over wireless or wired network. And let's suppose that there are other applications that are working in parallel with, let's say, mail application. And other applications produce a lot of data. And my network adapter is busy processing those packets. And it is not capable, for example, of transmission of all packets that have arrived. And in such case, those packets are placed into the queue. And when my email arrives, of course, it will be split to multiple packets. We will talk about that later. But in this case, those packets will be added to the queue. And they will wait until previous packets will be transmitted over the wire. And only afterwards, my packets with email will be sent. So that is a queuing delay. Of course, if you have high-speed connection, let's say 1 gigabit per second connection, then you'll almost never have any queues of packets that are waiting to be transmitted over connection. But if you have low-speed connection, for example on your mobile phone or somewhere else, then you may have some queuing delays. Great. Next one is processing delay. And basically, processing delay consists of multiple processing delays. So let's suppose that there are two different computers and they communicate over internet connection. And there are multiple devices on the way between those two devices, like routers, switches, firewalls, and so on. First of all, sender need to process packet. For example, let's say email. And every layer of the TCP IP model adds its processing delay. So it takes time to generate header and add it to existing data. So processing delay on the sender. Next, switches, routers, firewalls also add their own processing delays. Such devices as switches will add really small delay, because they process frames very fast at wire speed. Routers or firewalls may add additional delay, because they process headers a bit deeper than switches. And so on, until receiver. Receiver will also add some processing delay, because it will perform decapsulation of the data. And that's why we need to sum up all those processing delays in order to get total processing delay. Next delay is transmission delay. And this delay tells how much time takes to transmit actual frame over wireless or wired connection. Because actual connection has its bandwidth, and each frame has certain size. And of course, it takes some time to put frame on the wire, to send data. And finally, propagation delay. This delay tells how much time it takes to travel for a single bit of data from one endpoint to another. And of course, propagation delay is impacted by actual bandwidth of every link and its physical capabilities. For example, if we talk about copper cable, then it will have its own propagation delay. If we talk about fiber cable, then propagation delay will be lower for fiber cable than for copper cable. And finally, we need to sum up all those delays, queuing delay, processing delay, transmission delay, and propagation delay, in order to get total one-way delay. How much time it takes for my email to travel from my computer to, for example, server. And again, that's called latency, or one-way delay. Great, that is latency and delay. And next, let's talk about round-trip time, or ping. See you next. Previously, we have discussed what is latency, or one-way delay. And it is actually time that is required to travel for data from one device to another, and it consists of multiple delays that need to be summed up in order to get total delay. And now let's talk about another term that is called round-trip time. And this term is very simple. It is actual time that is required for data to be sent from one endpoint to another and back. So this description of this term is pretty self-explanatory, round-trip time. Or another term that is very used often interchangeably with RTT is ping. And basically, ping is one of the utilities that is built into almost all operating systems, and using this utility you could measure this round-trip time between your computer and any remote server. But before doing that, let's have a look at this example. In this example, latency for data from this computer to this server is 25 milliseconds, and latency for data that travels back from server to this computer is 30 milliseconds. And that means that in this example, RTT or ping will be 55 milliseconds. 30 plus 25 milliseconds. Why this parameter of the network is important? It is important when we talk about, again, real-time applications, for example. When you have established a voice or video call with some other person on other side of the ocean, let's say, then if RTT will be very large, let's say half second or several seconds, then it will not be really convenient to talk to the person, because you will hear his voice or her voice in several seconds. And same applies to your voice or your video. That's why RTT should be as small as possible. But of course it cannot be smaller than, let's say, 1 millisecond. Because again, there are different network devices, there are propagation delays and so on. So acceptable RTT or ping is around 100 or even 200 milliseconds. So this value is measured usually in milliseconds. If it is seconds, then it is really a huge number. Great, let's now dive into the practice and let's, using built-in terminal on your computer, measure RTT or ping between your device and remote server. But let's do that after the small pause. Alright, now you know that RTT or ping is actually two-way delay. And now let's, using built-in terminal application, measure RTT between our computer and remote server of Google, for example. And let's open up for that built-in terminal. On Mac I'll open iTerm2. It is actually not a pre-installed terminal, it is additional application, but it looks pretty the same as a built-in terminal. On Windows you could open such terminal as PowerShell or, for example, Git Bash, any terminal you like. If you are a Linux user, you could also open any Linux terminal. And here simply type ping like that. And after space type 8.8.8.8 like that. It is IP address of the Google's DNS servers. We will talk about IP address and DNS a bit later in the course. For now we want to measure round-trip time between our computer and remote server. And for that we will use Google's server. Great. Simply press enter. And I'll see some response. I could terminate this process by pressing Ctrl+C. On Windows you don't need to terminate, because on Windows 5 packets or 4 will be sent by default and afterwards process will be stopped. And here in this output let's have a look at those parts. Time equal sign 17.248 milliseconds. It means that travel time, round-trip time actually, for request from my computer to remote server of Google is around 17 milliseconds. So that is a really nice result. And you see that actually several packets were sent, and here you see different RTT times for different packets. But in my case, all those values are from 16 to 20. And different values you see here because of different network conditions for different packets. For example, first packet could travel via one route between all routers. Another packet could take another route. And when, for example, this packet was traveling via network connections, some of the connections were a bit congested and there were some queues. And that's why here you see a bit larger delay. Again, it happens due to dynamic nature of every network. And finally, you see some statistic, round-trip time minimum, average, maximum, and here are actually those values. 16 milliseconds it is minimum time for my case. Here you see average value 18 milliseconds and here is maximum time. I could repeat this process. Let's first clear terminal, Command K, and repeat this action, ping. And again, I see similar results. Now I see even 24 milliseconds. But again, all those values are very nice and very low, I could say. If you see some values that are larger than 100 milliseconds, then you need to talk to your internet provider and ask them why those pings are so large. Great, that's how you could measure RTT or ping on your computer. Next, let's talk about one more parameter of the network, and it is called jitter. So let's talk about it next. We have just tried to measure ping on our computers using ping utility. And basically I have not explained you what this parameter means here, and probably you will get questions about that. So let me explain it now. STD-dev stands for standard deviation. And in my case it is around 2 milliseconds. And it is actually a measure that allows you to estimate how other values differ from average value. And on average, other values are not larger than 2 milliseconds from average value. And actually, all those packets are taken into account, and this STD-dev is measured based on all results. So, in my case, I have achieved really nice results, and RTT in my case is not larger than 24 milliseconds when I ping 8.8.8.8, it is the IP address of the DNS servers of Google. Now let's continue, and actually let's talk about final parameter in network communication, and this parameter is jitter. And jitter happens when different packets have different delays. One-way delays. And of course, two-way delays will differ as well. And basically, in this example output, you see that RTTs vary for different packets. But why jitter is important? Let's have a look at this diagram. Let's say that this computer has prepared again some data, let's say small video file. And this small video file was splitted to different packets before actual transmission over the network. And let's say that there are 3 different packets. And this computer sends those packets one by one. So first goes out packet 1, next goes out packet 2, and finally packet 3 goes out. So order at the sender is 1, 2, 3. Afterwards, those packets actually travel fully independently over all connections in the internet. And it may happen, and it happens very often, that those packets will arrive to receiver, in this case let's say it is streaming server, in different order. And in this example, packet 3 has arrived first, afterwards server has received packet 1, and finally it has received packet 2. It happens so that packet 3 has traveled faster than those 2 packets. Afterwards, we have received with some delay packet 1, and finally we have received packet 2. And that means that order at the receiver is 3, 1, 2. And it is just a simple example with 3 packets. Of course, it may happen that specific data is split to thousands of packets, and those packets may arrive into opposite order even. That's why this server somehow needs to process those packets and place them in the same order as we have sent them here at this computer. And basically it is a responsibility, for example, of TCP protocol. It is capable of reordering of packets that were received in different order than they were sent. And again, it happens due to jitter. Jitter is variable latency for different packets. And if jitter is very high, then sometimes some packets will be simply lost or discarded by receiver. It also may happen. And also, if jitter is very large during any video or voice calls, of course, you'll experience some difficulties in communication. You will hear your opposite partner with some delays, and sometimes voice will be broken or video will be broken. And that's due to jitter, variable latency. Of course, if network conditions are stable, then jitter will be really low, and devices that communicate will not even notice that jitter. But sometimes when, for example, congestion happens on some links or some links simply go down, then jitter will increase. And that could lead to unexpected behavior of some applications. But of course, again, some lower layer protocols, I mean lower than application, are able to recover from some acceptable values of jitter. Great, that's all about jitter, and next let's quickly summarize all parameters that we have discussed before, and afterwards we will continue with Ethernet. I'll see you next. Before making conclusions about main network properties like bandwidth, jitter and so on, let me discuss one more parameter that we have not yet discussed, and it is packet loss rate. And here in this test, you see that in my case I have 0% packet loss. And that means that in this test no packets were lost on the way from my computer to remote server and back. But it is not always the case. Sometimes, due to congestion or link failures or processing failures, some packets may be lost. And we could easily simulate such failure by doing following. Let me clear terminal and start ping again, like that, and now I'll simply disable my network connection. And now I'll see some errors. Request timeout for some ICMP packets. Now I'll connect to network back. Connectivity restored, and now again I see arrival of some responses. Let me now stop this output, Ctrl+C, and now I see packet loss rate. That is, in this example, 47%. And please notice that this could happen and this happens. And when some packets or frames are lost or discarded, then it is a responsibility of higher level protocols, like for example TCP, to retransmit lost packets. If transmission layer protocol is not capable of that, then probably application layer is capable to perform recovery operation. But again, packets could be lost, because every packet is transmitted and sent over the network independently from others. That is a packet loss rate, and of course, if this rate is very high, then you'll get a lot of errors and applications will send data more slowly than without packet loss. Great, that's all for packet loss rate, and next let's do summary about all network characteristics that we have discussed before. For now, we have discussed such important characteristics as bandwidth, throughput, latency, RTT or ping, and jitter. All those characteristics are very important when we talk about any network. And now let me quickly summarize each of those parameters. First one is bandwidth. It is a physical layer property, and it defines how fast specific link is. Or we could talk about bandwidth between two different endpoints that are connected to internet. In such case, bandwidth is minimum bandwidth of all links that connect to different devices. And bandwidth is measured in bits per second, and possible values are, for example, 100 megabits per second or 10 gigabits per second. That's bandwidth. And next comes throughput, and it is actual throughput of payload, and it defines how many real data you could send using specific link with specific bandwidth, or specific links with some minimum bandwidth. And usually throughput is always less than bandwidth, especially it is lower, much lower than bandwidth in wireless networks. And I'll explain you later why. Afterwards comes latency, and it defines one-way delay of data that is sent from sender to receiver. And it consists of multiple delays that are summed up. And here we need to take into account such delays as processing delay, queuing delay, propagation delay, and transmission delay. Next parameter is RTT, round trip time or ping, and it measures how much time it takes for data to travel from one point to another and back. So round trip time. And you could easily measure this value using built into any computer to any operating system utility called ping. And finally, there is one more parameter called jitter that actually describes how latency differs over time for different packets. And if jitter is very high, then some applications may suffer and even stop working. So jitter should not be very high. And if it is high, then we need to redesign network and probably increase the capacity of some links, add additional links, something like that, to make jitter really low at all possible moments of time. Alright guys, altogether that's it for those parameters, and next let's continue our discussion about Ethernet. And next I want to explain you structure of every Ethernet header or Ethernet frame. Let's discuss it next. Previously, we have discussed very important network properties like bandwidth or speed, throughput, latency, RTT or ping, and jitter. And all those network characteristics are very important, and they will be mentioned in this course a lot in next chapters. For now, let's move on and continue our discussion about Ethernet. And now it's time to introduce a new network device called network switch. Network switch operates on physical and data link layers. It does not work on network or transport or application layers. It is very important to learn. And you remember that PDU for data link layer is frame. And that means that switch operates with frames. And of course, because it works on physical layer as well, it works with bits. Switch may have multiple ports, for example 8 ports, 12 ports, 24 ports, 48 ports, or even hundreds of different ports. And please notice that the switch could combine different types of ports, like ports for connections of copper cables or fiber cables. Also, there are so-called end-user facing ports, like those ports in those two sections. And those ports are used for connections of end-user devices like desktop computers, laptops, or some servers. And also, every switch has several uplink ports that are used for connections to other switches. And please notice that cumulative bandwidth of all uplink ports is not usually equal to cumulative bandwidth of all end-user facing ports. And the reason for that is that normally not all ports are fully utilized and not fully loaded by traffic. That's why there is no need to create equal size uplink ports. And usually uplink ports use fiber links and higher speed rates. That is a network switch. Let's have a look at another diagram, and here I'll explain you how different computers actually communicate with each other via switch. But let's discuss it next. So we have just defined what is network switch. And network switches operate on physical and data link layers of the OSI model. And that means that switches don't care about IP addresses, TCP, sessions, and so on. And of course, they don't care which data is transmitted on the application layer of the OSI or TCP IP model. Their single responsibility is to transfer frames between different devices as fast as possible. That is a single goal of every network switch. And here on this diagram you see several computers that are connected to the same switch. And of course, every computer has its own unique MAC address. Recap that MAC address is simply a set of hexadecimal characters, and each MAC address has 6 sections splitted using either colon or dash. And in this example, those 3 computers are connected to the same switch but to different ports. And the ports are shown here in this table, and for this example I have used gigabit ports, and that means that those ports are capable of transfer rates up to 1 gigabit per second. And also notice naming of those ports, like gigabit 0/1, 0/2, 0/3. So what is 0 and what are 1, 2, 3? 0 is number of slot in the switch. Usually switches for home office use or small office use have just single slot, and its ID is 0, like in this example. And every slot has some set of ports, and numbers of ports usually start with 1. And in this example, first port in this slot 0 is 1. And the next port is 0/2, and after it comes port 0/3. Great. If switch has multiple slots, then names of those ports may be, for example, 1/5, 2/6, and so on. Also notice that in this table, MAC address table, there are MAC addresses assigned to every specific port. What does it mean, assign specific MAC address to specific port? Let me explain you how it works without those MAC addresses. Let me first separate them a bit like so. And let's suppose that you install new switch, so take them out of the box or move from other data center and place into your location. And afterwards, several devices like laptops or desktop computers or servers are connected to different ports of this switch. And again, the goal of the switch is to transfer frames between different devices. For example, from this computer to this computer, or from this computer to this computer. And let's suppose that MAC address table that is kept in the memory of the switch is empty at the moment. And let's assume that, for example, this computer sends any frame with destination MAC address equal to this MAC address. So let's suppose that this computer wants to communicate with this computer. In this case, switch receives this frame, and first it adds source MAC address to MAC address table and to the port where this frame was received from. And let's suppose that in this example, this computer is connected to gigabit 0/1. And that means that this switch adds this MAC address to MAC address table, like that. Next, it looks for destination MAC address, this MAC address, in the same MAC address table. And at the moment, this MAC address is absent in this table, correct? In such case, switch forwards such frame to all ports except that port where this frame was received from. And that means that in this example, this first frame will be sent both to this computer and this computer. And afterwards, this computer and this computer will compare their own MAC addresses with destination MAC address in this frame. And if MAC addresses match, in this computer they will match, then computer will strip MAC address header and proceed to upper layer of the TCP IP model to network layer. This computer will simply discard such frame, because destination MAC address in such frame does not match with its own MAC address. So, this computer has received this first frame, and let's suppose that it wants to send some response to this computer. It also constructs some frame. Of course, before that it adds a transport layer header, network layer header, and only afterwards it adds a data link header that contains source and destination MAC addresses, and sends frame back to this computer. So destination MAC address is this one, source MAC address is this one. Same as before, this network switch takes a frame, looks first at source MAC address, this one, and it sees that this MAC address is absent in MAC address table. But this frame was received on port gigabit 0/2, and that's why it's a good time to add the MAC address of this computer to MAC address table like that. And now there are two records in this MAC address table, like so. Afterwards, switch looks at destination MAC address, this one, and looks again in MAC address table. And it finds this MAC address in MAC address table, and it sees that device with such MAC address is located behind port gigabit 0/1. And now switch forwards this frame only to gigabit 0/1. It does not send this frame to this computer or other computers located behind other ports, because now it knows where destination MAC address is located. So, that's how second frame was sent from this computer to this one, and finally let's say that this computer also wants to send some data either to this device or this device, and let's suppose it sends some frames to this MAC address. And first again switch looks into MAC address table and it sees that source MAC address is absent here behind this port gigabit 0/3, and it adds this MAC address to MAC address table like that. Also, it looks next at the destination MAC address in such frame, and it finds that such MAC address is located behind port gigabit 0/2 and forwards such frame directly to this port to this computer. And finally, this MAC address table is complete for this example, and afterwards switch will forward frames only between pair of ports. So it receives some frame, for example, at port gigabit 0/2, looks at destination MAC address in the frame, and afterwards forwards such frame to specific port, either to this computer or to this computer. That's how network switch operates. Again, it works only with MAC addresses. And secondly, it does not modify frame header or network layer header or some other headers. It simply processes every frame and looks only at the header of the frame. Also, by the way, it verifies frame check sequence, and if it is incorrect, switch can simply discard frames. And now it's a good time to talk about the structure of the header in frame, because it contains not just source and destination MAC addresses like I have described you in this example, but it also contains a bunch of other sections. And let's discuss structure of the Ethernet frame in the next lecture. I'll see you just in a moment. So far we have discussed what is network switch and what is MAC address. And basically now you know that every switch operates on physical and data link layers, and its single purpose is to forward frames between different ports. Every switch has also MAC address table that is filled dynamically during operation. Now it's a good time to talk about Ethernet frame format. And now I'll explain you format that is defined by standard IEEE 802.3, and that is an Ethernet standard that defines communication between devices on data link and the physical layer, when on physical layer we use either copper cables or fiber optic cables. So here is this header. Actually, I have split this header into two rows. Actually, VLAN tag goes after source MAC address, but let's start from the very first section called preamble. This section is 7 bytes long, and it actually used in conjunction with SFD, start of frame delimiter, that is 1 byte. In total, this preamble with SFD is 8 bytes. And basically this part is used for synchronization of sender and receiver. And it indicates actually that soon after this preamble, actual frame will be sent. And preamble is as simple as sequence of zeros and ones, like 0, 1, 0, 1, 0, 1, and that's it. And again, its pure goal is to synchronize receiver with sender and say, hey, attention, soon frame will be transmitted. And finally, before actual frame, SFD will be sent. And it is like that. It is sequence of zeros and ones with two last ones. So 1, 0, 1, 0, 1, 0, 1, 1. And after SFD, actual frame starts. And every frame starts with destination MAC address. That is 6 bytes long, or 48 bits as you already know. After destination MAC address comes source MAC address, that is also 6 bytes long, or 48 bits. And you may ask me a question, so why destination MAC address comes first before source MAC address? Do you know? Answer is following. Some switches operate in so-called fast-forward mode. And such switches receive only first part of every frame, destination MAC address, and already after receival of this section, switch looks into MAC address table and starts forwarding of such frame to destination port. And such forwarding allows switch to transfer frame faster. It does not wait until it will receive entire frame. Alright, so after source MAC address comes another optional section in the frame header. And this section is called VLAN tag. VLAN stands for virtual LAN. And it is possible to create different virtual LANs on the same network switch. And we will get back to VLANs a bit later in this course. Length of this section is 4 bytes. After this optional VLAN tag comes type. And the type is 2 bytes long. And type actually indicates which type of protocol is encapsulated next. And for example, if there is IP version 4 packet inside here, then type will be for IP version 4 header. If there is IP version 6 payload here, then type will be different. Finally, after type section, there is actual data payload. And basically, frame header ends here after type. And afterwards comes data that was received from upper layer in TCP/IP or OSI model, from network layer. And basically this data or payload has already network layer header and transport layer header inside. Afterwards, in every frame, there is frame trailer that contains CRC, or it is called also FCS, that stands for cyclic redundancy check or frame check sequence. And that is actually checksum of the frame. So what is the purpose of this checksum? Every receiver, when it receives a specific frame, it verifies this trailer, verifies checksum. How it is actually constructed? Entire frame is taken, except of course preamble and SFD, and using specific one-way hash function, every device calculates this trailer that is 4 bytes long. And if frame was modified somewhere on the way between sender and receiver, for example, somewhere part of data was modified due to some interference or some collision, receiver, after creation of the checksum and comparison with this checksum attached to the frame, will see that checksums don't match. And it will simply discard such frame. Of course, if frame was not modified, checksum will match and the receiver will proceed with processing of such frame. That's the purpose of this CRC or frame check sequence trailer. Please notice that total frame length is from 64 bytes to 1522 bytes, depending on the length of data part, payload part. And if some device receives frame that is less than 64 bytes, then such frame is discarded. Also, please note that length of data or payload depends on the presence of VLAN tag. If such VLAN tag is present, then minimum data payload could be 42 bytes. Otherwise, when VLAN tag is absent, then data payload size must be minimum 46 bytes. Great, that is the structure of Ethernet frame, and please notice that this structure is defined in this standard. And wireless networks related standards like .11a, .11ac or .11n define other frame headers, but those headers also contain destination and source MAC address sections. So, in summary, there is preamble and SFD that are used in conjunction, and they actually indicate the start of the frame, and the frame starts immediately after SFD, and the frame starts with destination MAC address. Next comes source MAC address, afterwards comes optional VLAN tag. Next comes type that tells what is actually inside of this payload at the beginning. Next comes data, and finally every device adds CRC or FCS checksum that is used for verification of frame integrity. And if checksum at the receiver does not match, then the receiver will simply discard such frame. And of course, when frame is discarded, receiver will not notify someone about that. So frame is discarded simply silently. Receiver does not perform any other action except that. And of course, if a frame is discarded, some part of data is discarded as well, and upper layer protocols like TCP will try to recover from this packet loss. Alright, so that is the structure of Ethernet frame, and the main parts that are interesting for us are here, so destination MAC address and source MAC address, that are always present in every single frame. Also, before wrapping up this lecture, let's quickly calculate the total overhead that is added to every single frame at the data link layer. So, preamble and SFD 8 bytes in total, next destination MAC address and source MAC address 12 bytes, in total we get 20 bytes here. Next, let's omit the optional VLAN tag, next we add the type, 22 bytes, and finally 4 bytes here, 26 bytes. So 26 bytes is minimum overhead that is added to payload at the data link layer. And of course, if payload is small, and let's say it is minimum possible 46 bytes, then actual frame size will be increased really much, because we will add 26 additional bytes to 46. And that means that throughput in such case will be much lower than actual bandwidth of a specific link. Alright, that's all for this lecture, and next let's talk about different types of communication like unicast, multicast and broadcast. I'll see you guys just in a moment. In the previous lecture we have discussed the structure of the Ethernet frame defined in 802.3 IE standard, and we have calculated that in total every device on data link layer adds minimum 26 bytes of overhead. If VLAN tag is present, then total overhead will be 30 bytes. That is actually huge amount of data that is added to payload. Now let's talk about different types of communication. And those types are related not just to data link layer. On network layer and on other layers they are also applicable. So, first and foremost, there is unicast. And the term unicast is used when specific device wants to send data to other single device. So it is unicast. For example, when I talk to other single person, I use unicast transmission. Next, multicast. Multicast term is used when one device wants to send data to a specific group of other devices. For example, let's say that there are students that are listening to some lecture in the classroom, and the teacher says, "Hey, you students at the last desk, could you please repeat what I have just said?" It means that in such case, this teacher has used multicast transmission, asked several students. And of course, normally in such cases, no one is able to answer at the last desk. And last but not least, there is broadcast type of transmission when single device communicates with all other devices. So every piece of information sent by this device is received by all those A, B and C devices. It is broadcast type of transmission. And getting back to previous example, teacher can ask all students in the class, what is the purpose, for example, of, I don't know, frame? It is broadcast transmission. So that's different types of communication. In short, there are three different types: unicast, multicast and broadcast. Alright, now after the small pause, let's discuss types of MAC addresses. I'll see you next. Following previous lecture where we have talked about three different types of communication like unicast, multicast and broadcast, let's talk about three different types of MAC addresses that are used on data link layer of the TCP/IP model. And they are unicast, multicast and broadcast. So first let's talk about unicast MAC addresses. And unicast MAC address is actual MAC address that is assigned to any network interface card, NIC. And you and I use different MAC addresses that were assigned by manufacturer of our NICs. It is unicast MAC address. And getting back to example when I have explained you how switch fills MAC address table, it actually adds unicast MAC addresses and maps them to specific ports when it receives some frames from different ports. Next type of MAC address is multicast, and such MAC addresses are used in multicast transmission. But what is the use case of multicast MAC addresses? Sometimes specific group of devices wants to get same information, for example, same video stream or audio stream. And in such case, of course, sender may send multiple copies of the same stream, specifically using unicast to every single device. But it is a waste of bandwidth. And in such case, several devices may register to receive specific stream. And sender may send only one stream to destination multicast MAC address. Of course, in such case, destination IP address will be also multicast, and it will be actually mapped to destination multicast MAC address. But we will get back to it a bit later. For now, just have a look at this example where I have demonstrated you some kind of multicast MAC address. Here it is. It always starts with 01:00:5E. And the first bit in this second section is always 0. So here is an example of multicast MAC address. And of course, multicast MAC addresses can be only used as destination MAC address. If switch will detect source MAC address set to multicast MAC address, of course, such frame will be simply discarded. So that is multicast MAC address. And finally, broadcast MAC address. Here you see actual broadcast MAC address, and it is just one. There are no other broadcast MAC addresses. And it consists actually of all ones in binary format, or in hexadecimal format it is FF, FF, and so on. It is broadcast MAC address. And if, for example, switch receives frame with destination MAC address equal to this one, it will send such frame to all ports except port where this frame was received from. So that is the behavior of the switch when it receives frame with destination broadcast MAC address. It is intended to all devices in the same switched network. Broadcast MAC address. And of course, same as with multicast MAC addresses, broadcast MAC address cannot be set as source MAC address in the frame. Alright, let's quickly summarize. Unicast MAC addresses are used by regular devices like mobile phones, computers, laptops, and so on, and they are assigned by manufacturer, and they consist actually of two different parts, Eurocabinet OUI and NIC specific part. Next one is multicast, that is used for multicast transmissions, for example, of some video or audio streams. And finally, broadcast, and the broadcast MAC address is used as a destination MAC address in the frame when some device wants to send the frame to all devices in the same switched network. And switches will forward such frames to all ports. That's are types of different MAC addresses. Next, after the small pause, let's talk about duplex, and I'll explain you what is the difference between half duplex and full duplex. I'll see you just in a moment, guys. We have just discussed different types of MAC addresses like unicast, multicast, and broadcast MAC addresses. And now let's talk about other property, and it is actually physical layer property. And we will discuss difference between half duplex and full duplex. These terms are related actually to how data is transmitted over specific single physical link, like, for example, copper cable or fiber cable or wireless connection. So, let's first discuss what is full duplex. Full duplex communication happens when two devices are able to send and receive data between each other simultaneously. And it means that in this case, data is transmitted and sent over different channels, some channels. And if we talk about fiber optic cable, then there are actually two different wires with fiber inside. And if device A wants to send data to B, it uses first wire, and if device B wants to send data at the same time to A, it uses second wire. Let me actually quickly get back to types of different cables, and actually here on this image you see two different cables here and two different connectors at the end. That's what I'm talking about right now. So duplex transmission, full duplex transmission. We are able to send and receive data using fiber cable. Also, it is possible to transmit in full duplex mode using copper cable. Recap that there are 4 different pairs of wires, in total 8 wires, and we are able to use some pairs for transmission and some pairs for receival of data from remote side in full duplex mode. Alright, that is full duplex communication, and it happens when any device can simultaneously send and receive data over specific single physical link. Second type of communication on physical layer is half duplex. And when half duplex is in place, then only single device can either send or receive data over the same physical media, physical link. In this case, there are two devices connected to same cable, and only one device can send or receive data at any moment of time. For example, when device A sends data to B, then B is able only to listen, it is not able to send. Also, if there are multiple devices, more than 2, connected to shared media that is working in half-duplex mode, then only one device among all is able to send some data. All others must silently listen. That is a half-duplex. And half-duplex mode is supported in copper cables and in wireless. And more than that, wireless standards like .11a, .11n, .11ac work only exclusively in half-duplex. And that means that if there are multiple devices connected to the same wireless network, at any moment of time, only one device can transmit data. Alright, next let me explain you what happens when two devices simultaneously in half-duplex mode try to transmit data. I'll see you next. We have just discussed that there are two different modes of operation of physical media on physical layer of the TCP/IP model, and they are full duplex and half duplex. And now let me answer the question, what happens when two devices try to transmit data in half-duplex case. And this event is called collision. Collision happens when two different devices attempt to transmit data simultaneously in case when physical media works in half-duplex mode. And depending on the media, either wired or wireless, collision will actually happen differently. For example, if it is a collision in wireless network, then two signals will actually overlap and create unrecognizable waves that will not be able to recognized and correctly decoded by any receiver that is connected to the same media. Same applies actually to copper cable connection. When two devices try to transmit data in half-duplex mode, then electric signal will overlap in the copper cable and again create unrecognizable signal. In fiber cables it is not possible because fiber cables always operate in full duplex mode. You send and receive data simultaneously via the same fiber cable. But now we need to answer the question, how actually devices handle collisions. So what happens after collision? How devices detect collision and how they act actually after collision. Collisions are handled differently, and this behavior is actually described in every Ethernet standard like .3 for wired communication or .11 substandards for wireless communication. And let's discuss it next. Before we have discussed what is collision, and collision happens when two different devices attempt to transmit data over the same media that works in the half-duplex mode. And different standards, i.e. standards like 802.3 or 802.11, handle collisions differently. They actually define how devices need to handle collisions. And in 802.3 standard, there is such mechanism as CCMA-CD, that stands for Carrier Sense Multiple Access with Collision Detection. And main keyword here is detection. Devices that operate in hull duplex mode and that are connected to specific shared media, because in such case media is called shared, many devices are connected to the same physical media, have such mechanism enabled. And they are able to detect when collision happens. And if collision happens, all devices become silent for some period of time. And on every device, this period is random. After this random period, device that wants to send some data again attempts to send frame again, starting from preamble, then SFD and so on. And if collision happens again, then same mechanism is enabled again. All devices become silent, enable random timers, and only after those timers try to transmit data again. And of course, in CCMA-CD, when any device sees that there is already some activity in physical media and some data is already being transmitted there, of course, in such case, device will wait until media will be free for transmission. And only when media is free, device will try to transmit its own frame. That's mechanism called CCMA-CD. Of course, this mechanism is a bit more complicated than I have just described, but in a nutshell, it works like that. That is CCMA-CD. Alright, in wireless standards like .11a or .11n, another mechanism is utilized, and this mechanism is called CCMA-CA, that stands for Carrier Sense Multiple Access with Collision Avoidance. Avoidance is attempt to avoid collision instead of handle collision. And when this mechanism is enabled, different devices that are connected to the shared media, for example to the same wireless network, actually they agree when and how every device will send its own data. But if other devices that are not connected to our wireless network will send some data on the same frequency as we are using for our network, then of course collision will happen. And frames will be discarded, and of course, in such case, frames must be retransmitted. Altogether, with collision avoidance mechanism, wireless routers or wireless access points and their clients actually manage common transmission media, wireless media. And with collision detection mechanism in place, devices like computers detect and manage collisions independently. There is no single point of management of collisions. Every device, when it detects collision, becomes silent for some period of time and after this period tries to retransmit data. So that's two different mechanisms, CCMA-CD and CCMA-CA, that are utilized and that are actually defined in different IE standards, like .3 for wired communication and .11 for wireless communication. And again, please notice that all currently existing wireless standards support only half duplex mode. It is not possible to use full duplex and send and receive data simultaneously in wireless networks, because wireless is actually shared media. Cable is dedicated media, yeah? And wireless is shared. Alright, let's next discuss what is collision domain, because collisions may happen only in specific places of network and they don't impact other sections of the network. Let's discuss it next. Previously, we have discussed what is collision and which mechanisms exist that help to handle collisions. And there are two different mechanisms, collision detection and collision avoidance. And now let me talk about one more important term that is called collision domain. And collision domain defines the actual part of computer network where collision may happen. And if collision happens in specific part in specific media, it does not impact other parts of the network. other collision domains. And here I have drawn several examples where different network devices are utilized. And let's first have a look at this diagram where I have shown hub. I haven't talked about hubs before because they are actually dinosaurs and they are not used anymore in computer networks. But at the beginning of computer networks era, those hubs were utilized. And they are actually unmanaged devices that could interconnect different computers with each other. But they work on physical layer of the TCP/IP model. They simply take signal from one port and transmit it to other ports. That's it. It is similar to case when you simply take one coaxial cable and connect multiple TVs at home to the same cable, using just splitters, and that's it. Splitters are also physical layer devices. So that's hub. And when you connect different computers using hub, then you create single large collision domain. And of course, in such scenario, you could work only in half duplex mode. Only one device could transmit data at any moment of time. And that means that hubs create large collision domain. And all computers connected to hub will be affected if collision happens. And of course, such mechanism as CCMA-CD could detect collision at every computer and handle it. Alright, let's have a look at this part. In this part I have demonstrated you switch and different computers connected to the switch. Switch works on physical and data link layer of the TCP/IP model, and it processes frames. And actually every computer is connected to switch using dedicated cable, either copper cable or fiber cable. And actual connection between every computer and switch is collision domain. If, for example, this link operates in half duplex mode and collision happens here on this link, then this collision will not affect this connection and this connection between other ports and other computers. It means that collision domain will be as small as just single link between computer and switch. And in this diagram there are three different collision domains. Great. And finally, let's have a look at this example where I have shown wireless access point, and let's suppose that there is specific wireless network and there are three different computers connected to the same wireless network. In such case, this wireless network is single collision domain. And in this scenario, all those computers and wireless access point must agree on usage of collision avoidance mechanism in order to distribute available wireless bandwidth. And collision domain again will be common for all devices and wireless access point. These are examples of different collision domains. Great. Next, let's proceed, and I'll explain you next how different devices agree on speed and duplex, which will be utilized for specific physical link. I'll see you guys next. We have just discussed what is collision domain, and how different devices handle collisions. And you should remember that if you use switches, then each link that connects device to switch is actual collision domain. Now let's discuss how devices agree upon speed and duplex, which will be used after connection of specific link. From, for example, laptop to switch, or between two different switches, or from switch to router, or some other link. So, when specific cable, either copper cable or fiber cable, is connected between two different devices, they start negotiation of speed and duplex. And maximum possible speed is actually defined by type of the cable. Recap that there are different categories of copper cables, and there are different types of fiber cables as well, and different types of fiber connectors. That's why it is not possible to negotiate speed that is larger than possible supported speed of physical media. There are special techniques that allow to devices to negotiate actually speed and duplex. And please notice that fiber cables don't support half duplex. They operate only in full duplex mode. And most commonly used speeds for fiber cables are 1 gigabit per second or 10 gigabits per second. Next, copper cables support HAL duplex only at speeds 10 megabits per second or 100 megabits per second. But please notice that HAL duplex is not desirable, because again, collisions may happen in HAL duplex and throughput is greatly reduced in comparison to full duplex mode. And in HAL duplex, you get 100 megabits per second for both sides. In full duplex mode, you get 100 megabits per second uplink and downlink, so in total 200 megabits per second. That's why try to avoid any HAL duplex settings whenever possible. Actually, I could tell you that most modern switches even don't support HAL duplex at all, and they are set only to full duplex mode. But, for example, if part of the copper cable is broken somewhere and some small wires are broken and not available for use, then of course you could still use this cable, but in HAL duplex mode. And finally, here is an example that I have just mentioned for 100 megabits per second case. If duplex is full, then available link bandwidth is actually doubled. And if a link supports 1 gigabits per second and two sides have negotiated such speed, then 1 gigabits per second will be uplink for computer A and downlink for computer A as well. So it is able to transmit and send data at this speed simultaneously. And it is a great advantage. And of course, second advantage is that collisions will not happen here at all. And please also note that if, for example, one of two wires in fiber cable is broken, then physically on physical layer, link will not even come up. So link will still be down and the negotiation will not happen at all, because it's not possible to use fiber cables if one of the wires is broken. Alright, that's how different devices negotiate speed and duplex. And again, it happens on every single link that is connected between two different network devices. And please try always verify which speed and duplex were negotiated and try to avoid half duplex settings. My recommendation to you, if you use some network switches, simply disable HAL duplex on all ports. That's it. In such case, all computers, all servers will be connected at full duplex and will fully utilize available speed of physical connection. That's all, guys, and that's all for actual theoretical part. And next, let's jump a bit into practice and using Wireshark analyze structure of Ethernet frame. I'll see you next. We have discussed a lot about Ethernet protocol, and we have also discussed the structure of every Ethernet frame. And now it's a good time to dive a bit into practice and go back to Wireshark and analyze several frames and look specifically at Ethernet headers. And recap that every Ethernet frame has the source and destination MAC addresses, and every MAC address contains two different parts, OUI and network interface card specific part. Alright, let me open up Wireshark. And here let's start packet capture. Let's wait for several packets to arrive, and it's enough for the sake of this lecture, and please select any packet you like. And let's have a look at this section below, and let's expand first this frame section. And basically in this section you see data from Wireshark itself. It, for example, tells when this packet has arrived. Also, it tells you encapsulation type, it is Ethernet. Also, here is interface ID. In my case, it is EN0 interface, and its description is Wi-Fi. Also, you see, for example, time delta from previous captured frame. Also, you see frame number. It is actually internal frame number in Wireshark after the start of the capture. Frame length, in this case, it is 66 bytes. Recap that minimum frame length is 64 bytes. And in this example, it is a bit more than minimum size. Also, you see such data as whether frame was marked or ignored, and also you see protocols in frame section. And basically this line contains information about all headers that were added on different layers of the TCP IP model. And here we see that at data link layer there is Ethernet header. Afterwards comes IP header. In a moment I'll explain you what is ether type. And after IP comes TCP. Alright, also you see that Wireshark has applied the TCP coloring rule for this specific packet. That's why here in protocol section I see TCP. Alright, that's information about frame itself, about bytes that were received on network interface card actually. Alright, let's minify this frame section and let's expand Ethernet 2 section. In this section we see destination and source MAC addresses. And first, as you see here, comes destination MAC address, and next to it comes source MAC address. And if I go back to diagram, you'll see exact order here. So first comes destination MAC address and next source MAC address. Please notice that in this Ethernet frame section, we don't see preamble. Because there is no sense actually to show preamble here, because it is always the same and it contains sequence of zeros and ones, and SFD, starter frame delimiter, has 2 ones at the end. That's why again there is no sense to show it here, because preamble and SFD are always the same. Alright, let's have a look for example at destination MAC address and let's expand this section. Notice that in parentheses here I see full MAC address that contains 6 different parts, each has 2 different hexadecimal characters, and those sections are divided using colon. And also notice that Wireshark has replaced OUI part with vendor name, in my case this TP-Link. It is a wireless router, and this wireless router was actually destination for this specific packet. Next to it you see additional fields like this one, and let me briefly explain you what does it mean. Actually, using OUI part, every device is able to distinguish whether frame is unicast or multicast or broadcast. Recap that we have talked about those 3 different types of frames before. And actually, if bit number 1, 2, 3, 4, 5, 6, 7, if 7th bit is set to 0, it means that this MAC address is globally unique address, or factory default. And that means that this MAC address was assigned by manufacturer when a specific device was created. Again, this bit number 7. And if I have a look at OUI part, it is here 98DAC4. And let's have a look at hexadecimal character 8 and convert it to binary. You could use any binary converter, but it will be 1000. And in this representation, in binary representation of hexadecimal character 8, I see 0 at place number 3 and 0 at place number 4. Again, 8 is 1000 in binary. That's why if bit number 3 in second hexadecimal character is set to 0, then such MAC address is considered as globally unique address. And if bit number 4 of hexadecimal character number 2, again it is 8 in this case, is set to 0 as well, then such MAC address is considered as individual address, unicast. For multicast and broadcast addresses it will be set to 1. That's what those bits mean. Again, those bits are bit number 7 and bit number 8 of OUI part, this part. Alright, that's how Wireshark has decoded destination MAC address, and in the same way it has decoded source MAC address. In my case, source MAC address is MAC address of Apple network interface card, that's why OUI part here is Apple. And also you could have a look at those bits here and here, bits number 7 and 8, and actually on this place there is number 4 in hexadecimal character, and the 4 is represented as 0100 in binary format. That's why bits number 4 and 3 here are zeros. That's why, again, in this case, this MAC address is considered as globally unique address, and it is individual address or unicast. Alright, that's our destination and source MAC addresses. Let's go back to diagram and let's have a look at next fields. And basically, next field, it is optional, it is VLAN tag. And it is absent in this example, because this traffic is sent without any VLAN tagging. Alright, next field after it is type, and it is 2 bytes long. Let's have a look at this section, and it is actually this field that we have just observed. It is type. And in my example, type is set to IP version 4, or in hexadecimal format, it is 0800. Actually, this prefix 0x means that number is represented in hexadecimal format. And here you see that number itself contains 4 characters, 4 hexadecimal characters. Every hex character is 4 bits long, and in total there are 2 bytes. And if I go back to diagram, you see 2 bytes here. And here in this example again, we see combination 0800. And basically different protocols of the network layer, upper layer for data link layer, have different IDs. And IP version 4 packet has ID 0800 in hexadecimal format. It is a common agreement to use this number for IP version 4. And this number is inserted into type field in Ethernet frame in order to be able to distinguish which header comes next after data link layer. And it is required in order to correctly parse next header and understand what is the structure of that header. So that is a type field here in Ethernet frame. And after this type field comes actual data or payload. And of course, this data contains IP version 4 header in this example, and afterwards it has TCP header in my case. Also, Ethernet frame has CRC or FCS, and basically Wireshark does not show this FCS information here because it's just verified and that's it. If FCS is correct and it means that actual frame was not corrupted or changed somewhere on the way of transmission, then actual frame is accepted and is processed further. So we strip Ethernet header, then go to IP header and so on. Again, here in this output, we don't see FCS or CRC field. All what we see are destination and source MAC addresses and type of the frame. That is actual link to next header. It tells what comes next. In my example, IP version 4 header comes next. Alright, that is the structure of this specific Ethernet 2 frame. In the same way, you could have a look at one more packet, for example, let me choose this one, and Ethernet 2 header will be exactly the same, because communication actually happens between my computer and nearest network device, that is actually Wi-Fi router in my case. So destination and source MAC addresses pairs will be the same everywhere. So here you see that. But of course, they will be in different order depending on the way how specific frame travels, either from my computer to wireless router or back. Great, that's all for this practical lecture, and if you want, you could of course continue analysis and have a look at several other frames and examine Ethernet 2 headers there. And after the small pause, let me try to generate a broadcast frame and see how it looks like here in Wireshark. Let's do that next. Following previous lecture, let's continue analysis of some Ethernet frames, and in the previous lecture I have found several unicast frames. And basically unicast frame is sent from specific unicast globally unique MAC address to another unicast globally unique MAC address. And I have actually observed communication between my computer and nearest network device, that is wireless router in my case. In your case, probably you have the same setup and there is wireless router, or probably you are connected using wired connection to specific router or switch. And now let's try to generate some broadcast frames. And recap that in the broadcast frame, destination MAC address is set to FF and all Fs, or in binary representation all ones. And such frames are sent by network devices, for example by switches, to all ports except port where such frame was received from. Alright, let's now try to generate such frames. And let's start capture. And now let's simply disable internet connection. I'll simply disable network interface card, like that. So please disable yours as well. But don't stop capture at the moment. And now let's re-enable interface, like that. And wait until you will be connected again. So I am connected, and now let's stop capture, like that. And now let's look for specific protocol, and this protocol will be DHCP. Simply type DHCP and press enter, like that. And if you obtain IP address dynamically, then you should see DHCP requests here. No worries, we will talk about IP addresses and DHCP a bit later on in this course, but for now I just want to show you that this protocol actually uses broadcast MAC addresses. And if I have a look at this first request, DHCP request, and have a look at Ethernet 2 header, I'll see that destination MAC address is set to broadcast, all Fs. If I expand this section, I'll see the same decoding as we have seen before, and in this case I see that LG bit is set to 1 and IG bit is set to 1 as well. And this tells us that this MAC address is locally administered address. That is not the factory default, of course, it is a broadcast address, and broadcast addresses are not assigned to any network interface cards. And also we see that this MAC address is group address, either multicast or broadcast. And in this example, this MAC address is broadcast MAC address. Alright? So, my computer has sent from its source MAC address, here I see my source MAC address, frame to broadcast MAC address, this one. That's how this DHCP frame looks like. It has unicast, unique source MAC address, but destination is broadcast. Great. Let's now have a look at one more protocol, and here instead of DHCP, write ARP, like that. Press enter, and you should see several ARP packets. And please try to find the packet like this, ARP announcement. And in such packets, you'll also see in Ethernet 2 header destination MAC address that is set to broadcast MAC address. Same as for previously analyzed DHCP frame. Again, same information here as well. That's how you're able to catch several frames where destination MAC address is set to broadcast. But please notice that in those analyzed frames, source MAC address is always set to unicast, unique MAC address, because it is built in by manufacturer into every network interface card. And broadcast cannot be set as source MAC address, as well as multicast MAC address also is not able to be set as source MAC address. So that's all, and that's how you could find several frames where destination MAC address is set to broadcast. And next, let's actually wrap up this section dedicated to Ethernet. We have discussed a lot, and now you actually know enough in order to proceed and go on to discussion about IP headers. Alright, let's next summarize what we have discussed so far. Alright guys, we have discussed a lot about Ethernet protocol, and we have even tried in practice to analyze several headers of the Ethernet frames, and we have seen unicast and broadcast frames. And now let me quickly summarize key points of previous lectures, and afterwards we will move on to next layer of the TCP/IP model, to network layer. So, Ethernet is a set of different protocols that are defined by IEEE organization, and Ethernet actually defines how communication occurs on data link layer and physical layer of the TCP/IP model. Next, there could be different medias on physical layer, like copper cables, fiber cables, or wireless. And different standards exist for copper and fiber cables and wireless connections. For example, there is a standard called .11ac that is mostly used nowadays, and it is the most fast transmission in wireless connection. Fiber cables could transmit data at speeds up to 100 gigabits per second. Copper cables are usually used for connections up to 1 gigabit per second. Alright, next to it we have discussed what is network interface card, and the NIC is actually created by specific manufacturer, and every NIC must have built-in by manufacturer specific MAC address that must be globally unique and must be unicast. There could be wireless NICs or wired NICs, depending on which media is used on physical layer of the TCP/IP model. Alright, MAC address is actually hardware address, and it consists of two different parts, OUI and network interface specific, and each section is 24 bits long, and the entire MAC address is 48 bits long. And actually every manufacturer, when it wants to create some NICs, must get this OUI ID or several IDs, range of IDs, from the same organization that actually creates standards, from IEEE organization. Alright, also we have discussed MAC address notations, and most commonly used is this one. It contains 12 hexadecimal characters in 6 groups, and those groups are split using colons, like that. Also, there are alternative versions of MAC address notations like this or like this. And you will probably never see this representation because it is very long. Great. Next to it, we have discussed some characteristics of every network like bandwidth, throughput, latency, RTT or ping, and jitter. And all those network properties are very important, and they must be considered when you build any network. Next, we have discussed what is switch, and the switch is actually a network device that works on physical and data link layers of the TCP/IP model, and its sole responsibility is to forward frames from source to destination as fast as possible. And usually it happens on wire speed, very fast. Next, we have discussed how network switch actually fills MAC address table, and when all computers are connected to switch and MAC address table is filled up, then every frame is forwarded from specific port, from port where sender is connected, to another specific port where receiver is connected. And that's thanks to this MAC address table. Next, we have talked about Ethernet frame format, and key fields here are destination MAC address, source MAC address, each 6 bytes long, and also there is type, that is actually linked to next header in data payload section for this Ethernet frame. Also there is a 8-byte long preamble and SFD section that actually indicates preparation phase for actual transmission of specific frame. And also there is CRC or FCS trailer that is used for integrity check at the receiver side. And if frame was corrupted or was modified somewhere on the way due to some interference or noise in wired or wireless media, then such frame will be silently discarded without any notifications to sender. That's structure of Ethernet frame, and the minimum frame length is 64 bytes. Next to it, we have discussed different types of communication, and there are unicast, multicast, and broadcast types, and similarly there are 3 different types of MAC addresses: unicast, multicast, and broadcast. And just in the previous lecture we have seen on practice how unicast and broadcast frames actually look like. We have not analyzed multicast frames because it will require some additional setup, create some streaming server and register for streams from that server. That's why I decided not to show you that here. Alright, next we have talked about half duplex and full duplex communication, and basically this communication on physical layer of the TCP/IP model. And we have discussed that in half duplex collisions may occur, and collision is a situation when two devices try to transmit data simultaneously and signal actually overlaps. And there are different techniques that handle collisions, and those techniques are called CCMA-CD, collision detection, that is used in wired media like copper, and there is CCMA-CA, collision avoidance, that is used in wireless connections. And with such mechanism, CCMA-CA collision avoidance, it is possible to distribute the bandwidth of available wireless connection among different clients that are connected to the same wireless network. Also, we have discussed what is a collision domain, and if different devices like desktop computers or servers are connected to switch using cables, then each cable is actually separate collision domain. So if collision happens on specific link, it doesn't propagate further to other ports of the switch. But there were old devices very long ago called hubs that acted actually as physical connectors between different devices, and in such case collision domain was very large, and it actually covers all cable connections and hub itself. Also, in wireless media, collision domain is as large as the same wireless network. That's why special mechanism, collision avoidance mechanism, is used here to distribute equally bandwidth between all different devices in wireless media. Alright, also we have discussed how speed and duplex are negotiated when specific link is connected between two different devices. And of course, optimum setup is when there is full duplex, and with full duplex you could transmit and receive at the same speed without any collisions, and of course bandwidth is doubled and we achieve actually maximum performance. Alright, that's all for this section where we have discussed Ethernet header, and we have discussed actually data link and physical layer of the TCP/IP model or OSI model. And next it's time to proceed and move one level up and go to network layer. And in the next section, at the beginning of it, I'll explain you why do we actually need some additional addressing and why we can't go just with MAC addresses and that's it. So I'll see you guys in the next section. Previous section was dedicated to physical and data link layers of the TCP/IP or OSI models. And now it's time to move one level up to network layer and discuss what is IP address and what is router. In this section, we will discuss basically need for IP addresses on network layer, and also we will discuss what is the purpose of routers, how they find optimal ways to specific networks, and how they actually route different packets. I'll see you guys inside. Before talking about IP addresses and routers, let's quickly get back to previous section and let's get back to actually switched network concept. And in switched network, different devices are interconnected using switches. Switches operate at the physical and data link layers of the TCP/IP model. And main responsibility of every switch is to switch frames as fast as possible. Usually it happens on wire speed in hardware. And also every switch has a table of MAC addresses, where each MAC address of specific endpoint, for example laptop or server, is mapped to specific port. So, switch fills MAC address table and switches frames. That's it. And now let's talk about disadvantages of switched network. And there are actually two main disadvantages. And first one is that every switch, as we have discussed before, sends broadcast frames. Broadcast frame is the frame where destination MAC address is all Fs, so broadcast MAC address. Switch forwards such frames to all ports, except port where such frame was received from. And let's suppose that there is a large switched network. For example, in this case, there are two different switches, but there may be other switches. And if any of those computers sends broadcast, let's suppose that this computer sends broadcast frame. So in this frame, source MAC address will be this one, it matches with the MAC address of this device, and destination MAC address will be broadcast MAC address. So it is a broadcast frame. And this switch will send such frame to this port, to this port, and to this port where upper layer switch is connected. And if this switch has also some other connections, then this switch will forward such broadcast frame to all remaining ports except this one. If there are other switches after this one, they will perform same operation. And this single broadcast frame will be copied multiple times across entire switched network. And basically there are a lot of broadcast frames in every network, because there are many protocols like ARP or DHCP that actually require broadcast frames, and we have observed that in previous section. That's why such broadcast frames can entirely flood entire switched network. And this is called broadcast storm, because again, every single broadcast frame is replicated multiple times to all ports. That is the first disadvantage of switched network. Second one is large MAC address tables. Let's suppose that again here is this switch that is interconnected with this switch. And let's suppose that on this switch corresponding port is gigabit 0/1 that is connected to this switch. And in this example, in MAC address table of this switch, there will be 3 MAC addresses, at least 3 MAC addresses of those 3 computers mapped to gigabit 0/1 interface here on this switch. And that is again due to nature of every switch. When switch sees any new frame with new source MAC address, it maps this source MAC address to specific port. And when any of those computers sends any frame that reaches this switch will add MAC address of corresponding device to MAC address table. And if there are many different switches and many different computers, let's suppose thousands of different computers, then MAC address table on every switch will be very large. And of course, every MAC address table has some limitations, and if limitations will be reached, some MAC addresses will be simply dropped from that MAC address table. And if a switch does not know about destination MAC address, then it will forward specific frame to all ports. And that is exactly the same behavior when you install new switch into the network. If it doesn't know about specific destination MAC address, it will forward such frame with unknown destination MAC address to all ports. And again, it will create multiple copies of the same frame. And finally, if switched network is very, very large and contains hundreds of switches and tens of thousands of millions of computers, then such network will be simply unusable, because it will be flooded with broadcast frames and switches will constantly perform actions with MAC address tables. That's why switched network is not a good solution for large networks. Of course, you could connect using switch several devices and interconnect several switches between them. But if you want to add much more devices and create a very large network, like internet, then of course other solution should be used. And now it's finally time to answer the question how we are able to interconnect different switched networks, like in this example, where we have, let's say, 2 computers and switch between them, and another pair of computers and one more switch between them. And the solution here is to use routers and logical IP addresses on the network layer of the TCP/IP model. And let's start by defining what is IP address. I'll see you just in a bit. Let's now define what is IP address. IP address is logical address that is assigned to devices on network layer of the TCP/IP model. And if device wants to communicate with other devices, it must have IP address assigned to it. MAC address is hardware address and it is assigned by manufacturer to specific network interface card, and it is a data link address. And IP address is a logical address that is assigned to specific devices, usually by DHCP servers on network layer of the TCP/IP model. And here you see example of IP address. It consists of 4 sections, and here you actually see familiar to you numbers, and those numbers are in decimal format. So MAC addresses are represented using hexadecimal characters, and IP addresses are represented using decimal characters, like you see here in this example. And please notice that IP addresses may change over time, and same device may have different IP addresses. And for example, at home your computer may have one IP address, and when you move, for example, outside to any cafe, then your computer will have different IP address. But in both cases, your computer will be connected to internet. so IP address may change. But MAC addresses are usually unchanged, because they are assigned to NICs by manufacturer. But of course, please note that you are able to change MAC address manually if you want to, but usually there is no need to do so. So, IP addresses are dynamic, usually dynamic, and MAC addresses are static and they don't change. Now let's talk about difference between IP version 4 and IP version 6, because here in this case you see example of the IP version 4 IP address. So I'll see you guys next. IP address is a logical address of a specific device on network layer of TCP/IP model. And usually IP addresses are assigned dynamically, while MAC addresses are static and don't change. And now let me briefly explain you difference between IP version 4 and IP version 6. Basically, there are two different protocols that define communication of devices on network layer of TCP/IP model. And those protocols are IP version 4 and IP version 6. IP version 4 is a standard for a long time, and IP version 6 standard was ratified just a few years ago, and before that it was a draft standard. And actually here you see examples of two different IP addresses, IP version 4 IP address and IP version 6 IP address. And you may notice that IP version 4 IP address is much more shorter and easy to read than IP version 6 IP address. And notice that format of IP version 4 address is in decimal, so 4 different decimal numbers, while format of IP version 6 address uses hexadecimal characters, same as in MAC addresses. But there are much more hex characters than in MAC address. In total, basically length of IP version 6 IP address is 128 bits, very long number. And here in this representation you see that it contains 8 different sections, and each section contains 4 different hex characters, while IP version 4 address contains only 4 different sections, each represented using decimal number. And the reason why IP version 6 protocol was developed is that there are not so much IP version 4 addresses in the world. And in the next lecture, I'll explain you how many IP addresses exist, IP version 4 addresses, and what is the format actually of IP version 4 address. Because IP version 4 address is still more popular than IP version 6 address. And if I'll have a look at IP address that is assigned to my computer, I'll see basically IP version 4 address here. So my computer was assigned this address 192.168.1.182, and default router also has IP version 4 address 192.168.1.1. Alright, let's next guys discuss structure of IP version 4 address, and a bit later in this course we will get back to IP version 6 addresses. I'll see you just in a moment. Now you know that there are two different IP protocols, IP version 4 and IP version 6. And correspondingly, there are two different types of IP addresses, IP version 4 addresses and IP version 6 addresses. And now let's focus on IP version 4 addresses, and let's discuss format of any IP version 4 address. So, any IP version 4 address consists of 4 octets. Each octet is 8 bits long, and that means that entire length of any IP version 4 address is 32 bits. And usually each IP address is represented as 4 different octets splitted using dots, like in this example. And every octet is represented basically using decimal number, like 1, 12, 168 or 192. And now question to you. What is the lowest decimal number that you could see on any of those places? Answer is very simple, it is 0. And 0 in decimal is equal to 8 zeros on place of specific octet in binary format. If you don't know how to convert the binary numbers to decimal numbers, no worries, we will get back to binary math a bit later in this course. But now, another question. What is the largest number that you could see on any place here. It is 255, and that is the largest decimal number that could be represented using 8 bits in binary format. And it is equal to all ones on all 8 places of all 8 bits. So, range of decimal numbers on any place here, 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 or here is from 0 to 255. Alright, so now important notice. Total quantity of IP version 4 addresses is around 4.3 billion. And that is actually equal to 2 to power of 32, because there are 32 bits that are used for IP version 4 address representation. And now let's discuss whether this number is enough large or not. Is it enough for all devices in entire world? Please keep in mind that any human could possess multiple devices like several mobile phones, computer, home computer, work computer, and so on. So, answer is that this quantity is not very large. And basically it's not enough to assign IP addresses to all devices in the world. I mean unique IP addresses, same as we can achieve with MAC addresses. So MAC address has 48 bits, and that's why we could assign unique MAC addresses to all NIC cards in the world. But now we have only 32 bits. And now question, how we could actually manage those connections between different devices on network layer if there are actually not enough addresses? And basically there are two different techniques that are used in order to solve this problem. And first technique is usage of private and public IP address spaces, and NAT, Network Address Translation. And we will discuss both techniques a bit later. But please keep in mind for now that IP version 4 addressing space is not large enough to be able to have unique IP version 4 addresses on all devices in the world. Also, please notice that it is possible to represent every IP version 4 address using 4 different octets, each with 8 binary bits, like in this example, and here you see actually this IP version 4 address converted to binary format. So 32 bits, 4 octets, each octet has 4 different bits. Alright, that is the IP version 4 address format, and next let's quickly get back to comparison of IP addresses and MAC addresses. I'll see you guys next. In short, IP version 4 address consists of 32 bits, and usually it is represented using 4 different decimal numbers, separated using dot. And smallest possible decimal number on every place is 0, and maximum number is 255. Now let me explain you once again difference between MAC addresses and IP addresses, because it is very important to understand. In the same switched network, devices may have different MAC addresses, assigned by different manufacturers, and every MAC address has its own organizationally unique identifier. It is the first part of every MAC address. And in the same switched network again, different devices may have different MAC addresses assigned by different manufacturers. It means that OUI prefixes are of course different on all devices in the same network. But IP addresses must belong to the same network. And here you see example of that. Here you see switch, it is switched network, and here you see several devices, like laptop, server, and mobile phone that is connected, for example, via wireless access point that also operates on data link layer. We will get back to it a bit later. But it is a switched network. And notice different MAC addresses on all devices. Those MAC addresses have different OUI prefixes. But it doesn't prevent those devices from communication with each other. But in the same switched network, devices must have IP addresses, logical addresses, from the same network. And on this example, you see that all IP version 4 addresses start with 172.17.5. And afterwards, in the last octet, there are differences. So here this IP address ends with .1, this ends with .78, and this ends with .32. We will discuss a bit later how you could understand whether IP addresses belong to the same network or not. For now, we could simply compare those prefixes of IP version 4 addresses and see that they are the same. If this phone has, for example, IP like this, 182, and it connects to the same switched network, then it will not be able to communicate with this server and this computer, because its IP address is from different network. That is the main idea of IP addressing on network layer. Different devices must belong to the same network, if they belong to the same switched network. And switched network is network where different devices are interconnected on data link layer of the TCP/IP or OSI model. Alright, so please keep in mind this very important point. So MAC addresses may be from different manufacturers and it doesn't impact communication between devices. But IP addresses in the switched network must be from the same logical network. Alright, let's next proceed, and next I'll explain you difference between unicast, multicast and broadcast IP addresses. I'll see you guys after the small pause. I have just noted that MAC addresses may be different from different manufacturers in the same switched network, but IP addresses must belong to the same logical network on network layer of TCP/IP model. And now let's talk about different types of IP addresses. And same as with MAC addresses, there are three different types: unicast, multicast, and broadcast. Unicast IP addresses are assigned to specific device in the network. You could do that either manually or dynamically. And here is an example of unicast IP version 4 address. And unicast IP address is used for one-to-one communication. If two devices have unicast IP version 4 addresses, they communicate directly with each other, so point-to-point communication. Multicast IP addresses are used when specific device wants to send data packets to multiple devices, to specific group of devices. And in such case, destination IP address is multicast IP address. And here is an example of multicast address. It starts in first octet with 224. And last type of IP address is broadcast address. And here is an example of broadcast IP version 4 address. And here on all places you see 255. And I have told you that that is the largest number, decimal number, that could be represented using 8 different bits. And in this case, all bits are set to 1. And if I convert this broadcast IP version 4 address to binary format, I'll get actually 32 ones. And broadcast IP address is used when specific device in the network wants to send the IP packet to all remaining devices in the same switched network. I emphasize, in the same switched network. Broadcast IP packets don't travel all over the world. So, that is a broadcast IP version 4 address. Also, please notice that there are so-called broadcast network addresses. And the format of broadcast network address could be, for example, 152.10.97.255. And we will get back to this term a bit later when we will talk about subnetting and about network addresses and broadcast network addresses. Now please keep in mind those three types of IP addresses: unicast, multicast, and broadcast. Alright guys, let's proceed, and next I'll explain you what is router. I'll see you just in a bit. Now you know that the same as with MAC addresses, there are three different types of IP addresses: unicast, multicast, and broadcast. And now it's time to define what is router. Router is network device that is responsible for routing of IP packets on network layer of TCP/IP model, of course. And it means that router actually works on physical, data link, and network layers. And that means that every router also has ports, and ports of router have MAC addresses and, of course, IP addresses, because again, router operates on network layer of TCP/IP model. But please note that routers not just forward packets to destination networks. They also need somehow discover remote networks. For example, this router needs somehow get information about this network, where those computers are located. And this network is located behind this router. And vice versa, this router needs to get knowledge about this network that is located behind this router. And actually, there are special protocols called routing protocols that are used for exchange between different routers of information about different networks. And only when exchange was completed and this router knows about this network, it is able to route packet, for example, from this laptop, from this IP address, to this laptop with this IP address. So, routers build routing tables and forward IP packets. And they perform their operations on network layer of the TCP/IP model. And they work actually with IP packets. But please notice that routers, of course, work on data link and physical layers of TCP/IP model as well. For incoming packets, every router performs decapsulation till network layer, and for outgoing packets, every router performs encapsulation. Alright, that is the responsibility of router. It finds optimal paths to destination networks and it routes packets on network layer of TCP/IP model. And next, let's discuss difference between local area network, shortly LAN, and wide area network, shortly WAN. I'll see you guys next. Now you know that there are special devices called routers that operate on network layer of TCP/IP model, and their responsibility is to route IP packets between different networks. And of course, for that, they need to build routing tables with remote destination IP networks. Now let me explain the difference between local area network, shortly LAN, and wide area network, shortly WAN. Local area network is a set of different devices and communications between them under common administration. And usually LANs are located in the same geographical area. Example of LAN is, for example, network in your home. And when you are able to replace your devices, change connections between them, connect to your network different devices like mobile phones, TVs, and so on, then you actually manage this local area network. Another example of a local area network is a small office network that has, let's say, several switches and one router that is connected to internet provider, and there are several computers, laptops, and other devices in this small office. Also, we could name local area network of a large company that is spread across different buildings, and every building has multiple floors. But all devices in those buildings are under common administration. We could name it also local area network. Wide area network is actually a set of local area networks that are interconnected with each other, and usually WAN is spread across different geographical areas. And we could say that the internet is actually wide area network, and it is a set of different LANs that are interconnected with help of internet providers. And actually, network of every internet provider is local area network of that provider. So that is the difference between LAN and WAN, local area network and wide area network. And next, let's have a look at this diagram where I have shown two different LANs, local area networks, and one large WAN that is actually a set of those two LANs. But let's discuss this diagram in the next lecture. I'll see you just in a moment. Now you know that local area network is a set of devices and connections between them under common administration, and WAN is a set of LANs actually. And now let me briefly explain you typical WAN with several LANs, local area networks. Let's suppose that here is LAN number 1, local area network, and there are two laptops, one switch and one router. Every laptop has, of course, IP address and MAC address, and notice that IP addresses are from the same network, and MAC addresses have different OUI prefixes. That is pretty normal. Also, there is a switch that actually works on data link layer of TCP/IP model, and its responsibility is to switch frames between those three devices: this laptop, and this router. This router has two interfaces: local area network interface, this one that faces this switch, and WAN interface that faces actually internet. And on this side of the connection is usually one of internet providers that actually connects this local area network to wide area network, internet. Sometimes there are multiple connections to multiple providers. In case one provider fails, then you are able to use another link. Alright, so in this example there is just one connection to internet, and this router has two different interfaces. And each interface, same as with any computer, any device in the network, has IP address and MAC address. And there is local area network IP address, and notice that in this example this IP address is from the same network as those devices have. There is MAC address on this interface, because again every network interface card must have MAC address. And also on other side there is another interface that has wide area network IP address, WAN IP address, that is usually assigned by internet provider. And of course this outside interface has also MAC address. So two MAC addresses on both sides and two different IP addresses on different sides of the router. Also on other side there is one more local area network here, and the picture here is the same, except that fact that here you see other IP addresses and they start with 192, and the local area network IP address on this side of the router also has IP address from this network. It also starts with 192, 34 and so on. Same as with this router, there are two different interfaces. One interface faces this local area network, and it is connected to this network switch, and another one is connected to another internet provider in another place in the world. And this outside interface has also wide area network IP address, different from this one of course, and it also has its own MAC address. And basically now those two local area networks, this one and this one, are interconnected, and it is possible to get access to internet from this computer or this one or this one or this one. Because now those LANs are actually part of global wide area network, internet. And responsibility of those routers is actually route packets from those devices to internet and back. And if there is only one uplink on each side, here and here, it means that routers don't need to keep in memory all networks in the world. They only need to know about the link to internet provider, and all packets going to internet will be routed to router on internet provider side. That's it. And it means that this router and this router will have actually default gateway that points to corresponding internet provider. That's it, default route. And the provider will forward incoming packets back to corresponding router, and router will forward them back to corresponding network device, like this computer or this computer. But please notice that in this example, IP addresses of those computers, here, 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 and here, are private IP addresses. And you are not able to go to internet with such IP address. Any router of any public internet provider will block such packet with such source IP address. That's why IP packets from every of those computers need somehow be converted in order to be able to travel to internet and back. We will discuss how it is solved a bit later in this course, but now I'll ask you to verify which IP address is assigned to your network interface card. I'll verify mine. And here I'll see IP address that starts with 192, same as in this example. And it means that my IP address actually is also private IP address. Alright, that's how typical communication between LANs occurs, and basically routers interconnect different local area networks. Alright, that's all for this example, and we will get back to technique that allows you actually communicate using private IP addresses a bit later. And next, let's proceed and discuss IP addresses classes. There are actually 5 different classes in IP version 4 address space. I'll see you just in a bit. Now you know what is the purpose of the IP address and why do we actually require IP addressing on network layer of TCP/IP model, and why it is not enough to have only MAC addresses. And also you know what is the purpose of the router. Router is a network device that works on the network layer of TCP/IP model, and its responsibilities are: first, to build routing tables and find optimal paths to remote networks, and second, route actual packets to their destinations. And it means that routers interconnect different networks. And now it's time to dive a bit deeper into IP addressing and discuss different classes of IP addresses, and also discuss difference between private and public IP addresses. And let's get started with classes of IP addresses. As you see here in this table, there are 5 different classes of IP addresses: A, B, C, D, and E. Here in second column you see IP addresses ranges that belong to different classes. In next column you see representation of the first octet in each IP address in different classes. And finally here in the last column you see default network mask. Alright, let's start with the class A IP addresses. Here is a range, and the first IP address in this class is 1.0.0.0 and last one is here. The first octet you see here 126. And first octet of any IP address that belongs to class A always starts with 0. All remaining bits could be any, either 0 or 1, but first bit will be always 0. Default network mask for class A IP addresses is 255.0.0.0. No worries, we have not yet discussed what is subnet mask, and we will talk about subnetting and masks in the next section. For now, just keep in mind that default network mask is this one, 255.0.0.0. Next class is B, and here is a range of IP addresses for this class, and first IP address is here, 128.0.0.0, and last one is here, 191, and all 255s. And notice that first octet in every IP address in this class B has 1 0 at the beginning of the first octet. And that means that class A and class B IP addresses don't overlap, because here you see 0 at the beginning and here you see 1 0 at the beginning. And all remaining bits could be any, either 0 or 1, same as in this case. Default network mask for class B IP addresses is 255.255.0.0. Next range is here, and the next class is C, and IP addresses start with this one, 192.0.0.0, and end with 223 and all 255s. And now first octet starts with 110, so those 3 bits are fixed. And all remaining 5 bits could be any. And of course, all remaining bits in remaining octets, octets number 2, 3, and 4, could be any in all classes. Next class is D, and here is its range, and it starts with IP address 224.0.0.0, and last one is here. And first octet now starts with 1110, it means that 4 bits are now fixed. This range is reserved for multicasting. And there is no default network mask for those IP addresses, because as you know, multicast IP addresses, same as MAC addresses, could be used only as destination IP addresses. And IP addresses from this range are used for multicast transmissions of video or audio streams. And last class is class E, and here is its range from 240.0.0.0, and last IP address is here. And now IP addresses in this range have 5 first bits fixed, 1110. And this range is called experimental range, and those IP addresses are reserved for future use. And that means that you are not able to use IP addresses from class D or class E for assignment to any host. Because again, this range is reserved for multicasting, and this range is experimental. And that means that you are allowed to use any IP address from those ranges, from classes A, B, and C. Alright, that's our classes of IP addresses. You don't need to memorize all those classes. You just need to keep in mind how first octets look like in every class. So, class A IP addresses always start with 0, class B start with 1, 0, class C start with 1, 1, 0, and that's it. Very simple approach. Alright, please notice that in this range, there is no IP address that starts with 127. And here you see actually gap between this one and this one. And the reason for that is that 127 range is reserved for loopback purposes. And next, let me talk about what is localhost or loopback IP address and show you it on practice. I'll see you guys next. Before we have discussed that there are 5 different classes of IP addresses – A, B, C, D, and E. But basically, you could assign to any device in the network IP address only from first 3 ranges, either A or B or C. Class D is used for multicast transmissions, and Class E is experimental. And now let me talk about special IP address that is called actually localhost or loopback IP address, and this IP address is 127.0.0.1. Technically, this IP address should belong to class A range, but actually it doesn't belong to any range at all, and here you see this. So number 127 in the first octet is not included here in this range. And using this IP address, you could verify whether network stack actually operates on specific device or not. Also, using this IP address, you could connect to any services that are running locally on localhost. And actually, this IP address is available for use on all operating systems. And if you're able to ping this IP address, let me show you that, it means that a network stack operates correctly. So ping 127.0.0.1, and I see responses. And notice very small time. And that's because now I'm pinging localhost, local computer. And even if I'll disable network adapter and repeat ping, I'll see same responses as before. And that means that localhost IP address doesn't depend on network connection. You could use it even without it. And next, let me quickly demonstrate you how you could use some local web server, for example, and access it using this localhost loopback IP address. I'll see you next. Now you know that there is localhost or loopback IP address 127.0.0.1 that is actually available at any computer that has network interface card. And you could use actually this IP address for any local services. For example, you could create a web server and launch it locally on your computer, or you could create a SMTP server and send emails, or anything else. And now let me quickly demonstrate you how we could set up a web server. And for that, I'll use software called Docker. And using Docker, you could create different containers, including container that will be running web server. And you could install Docker pretty fast and easily. Just click here, get started, and install Docker on your computer. I have Docker already up and running here. And now I could create new container. Let me go to the terminal, and here I'll simply type following command: docker run -p 8080:80. And here will be name of the image I want to use, and it will be Nginx web server image. Let's press enter now, and let's go back to web browser, and here type 127.0.0.1:8080. Enter, and I see welcome to Nginx. And basically via localhost loopback IP address, this one, I have connected to container that serves actually this HTML web page. No worries if something is not familiar to you and you don't understand what is 8080 here. Single goal of this lecture was to demonstrate you that you could use this localhost IP address for running any services. And here you see an example of web server that is running on a local host. Alright, let's go back to terminal and press here Ctrl+C in order to terminate this process. And now if I'll go back to web browser and refresh page here, I'll see site can be reached, because now this service is not available. Alright, that's how you could use this localhost IP address. But please notice that this IP address is available only on computers and laptops, and probably on some mobile phones. But it is not available on network devices like switches or routers. They need to have other IP addresses assigned to their interfaces. Alright, let's proceed, and next let me explain you what is private IP address and what is the difference between private IP address and public IP address. I'll see you guys next. We have just tried in action access to localhost all-back IP address, and we have launched localhost web server. Alright, now let me describe you what is the difference between private and public IP addresses. Private IP addresses are IP addresses that are not routable in global internet network. And that means that routers of internet providers will simply drop any IP packets that have either source or destination IP address that is from private IP addresses range. Here in this example you see private network with several devices like a laptop or mobile phone. And here in this example I have used private IP addresses from the range 192.168.1. And in the last octet you see different IP addresses like .10, .11 or .12. Those IP addresses again are from private IP addresses range. Also here on this router on inner interface you see IP address from the same private network, and in the last octet it has .1. And of course inside of this private network those devices could easily communicate between each other, because their IP addresses are from the same network. But when any of those devices wants to connect to internet and access any public web server, this access will be blocked if IP address, source IP address in any packet, outgoing packet, will remain unchanged, will remain private. But this router, if it has on external interface public IP address, like in this example, this router will be able to access resources in internet. But again, if IP packets are coming from its public IP address. Of course, private networks may be the same in different places in the world. And you could create same network somewhere here, for example. And this router will be connected to internet as well. Let me quickly connect it like that. And of course, this router will have another public IP address here on external interface, and those hosts in this private network may have same IP addresses as those devices in this private network. And basically, if I check IP address on my computer, I'll see similar IP address that is also from private network, from private range. And router, default router in my case, has the same IP address as routers on inner interfaces here and here. And again, that proves that those IP addresses could be easily used and are used in multiple places in the network. But now question. If those devices have private IP addresses that are actually non-routable in global internet, how those devices could access internet? Answer is very simple. There is technology called NAT, Network Address Translation, that allows those IP addresses go outside via router by changing source IP address in every packet. And we will get back to this technology a bit later. For now, just keep in mind that there are private and public IP addresses, and private could be used only locally, and private IP addresses are not routable in global internet, that is a global wide area network. Alright, next let me talk about different ranges of private IP addresses. Before talking about private IP addresses ranges, let me finally define what is network. Every single device in Internet must belong and belongs to a specific network. Network is a logical group of devices. And devices in the same network could easily communicate between each other via switches. They don't require routers for that. And again, all devices in the same switched network have IP addresses from the same network. But how it is possible to determine whether two devices belong to the same network or not? For that, every network has two different parts. First part is network prefix, and second part is network mask. And using those parts, we are able to split every IP address in two different parts: network part and host part. And this division is similar to division of every MAC address to two different parts, OUI and NIC specific, where OUI part is the same for all devices produced by the same manufacturer. Same applies here. All devices in the same network have same network part. And host part may be, of course, different on different devices. And where network part ends and host part begins is defined by network mask. And with such network mask, we define that first 8 bits are network part and remaining bits, 32 minus 8 equal to 24, is host part. For now, that's all what I want to tell you about network. We will get back to network masks in the next section. For now, just keep in mind that every network consists of two different parts: network prefix and network mask. That's it. Let's proceed, and next let's discuss different ranges of private IP addresses. Previously, we have defined what is network. And basically, every network consists of two parts: network prefix and network mask. And using this knowledge, let's proceed and let's discuss different ranges of private IP addresses. Please recap that private IP address is not routable in global internet network. Alright, there are three different ranges of private IP addresses from different classes: Class A, Class B, and Class C. There is only one Class A network that is actually private. And here is a range of IP addresses from this network, and you see that this network is actually 10.0.0.0/8. 8 is default network mask for Class A networks. There are also 16 Class B networks that also represent private IP addresses ranges. And you see that in first octet there is always 172, but in second octet there could be number from 16 till 31. And here is an example of private Class B network: 172.16.0.0/16, where 16 is default network mask for Class B IP addresses. And finally, there are 256 Class C networks that define private IP addresses ranges. And here you see that actually first and second octet are fixed, and they are 192.168. And in third octet could be any number from 0 to 255. And here is an example of the private Class C network. It starts with 192.168.1.0, and network mask is 24. It is default network mask for Class C network. And that is that range that is used most often. And in my case, I use exactly this range on my computer and on my wireless router. In total, there are around 18 million IP addresses that are considered as private. And the nice point here is that you could choose any network from those ranges in order to assign IP addresses in your local area network. You don't need to ask anyone for permission to do that. You could easily choose any network and go with it. Let's summarize. There is one Class A network that is private, and in the first octet it has 10, and all remaining octets are host octets. And actually there is just one example of such private network. It is 10.0.0.0/8. And this network is very short and easy to use, and very often it is used for assignment of IP addresses to hosts in local area networks. Next, there are 16 class B networks, and in the first octet there is 172. And finally, there are 256 class C networks. They start always with 192.168, and in third octet could be any number from 0 to 255. Alright, these are different private IP addresses ranges that you could use in your local area networks. And those IP addresses, again, are non-routable and are reusable and are reused in multiple places in Internet. Alright, that's all for private IP addresses ranges, and next let's talk about public IP addresses ranges. See you next. We have just defined several private IP addresses ranges. And now let's define public IP addresses ranges. And it is very easy. Any IP address that belongs to class A or class B or class C and is not private is public. So we need to look at this table and look at the previous table that we have discussed in previous lecture that defines ranges of private IP addresses, and we will get actually ranges of public IP addresses, and they are here. Any IP address that belongs to any of those ranges is considered as public. And public IP addresses are routable in global network internet. And please notice that you could not simply choose any IP address from the public ranges and use it on your devices and access internet. You need to get permission for that. And there is a special organization called ARP, and this organization is responsible for assignment of the public IP addresses. And if you want to get a public IP addresses range, you need to contact this organization. And of course, there are not so many public IP addresses ranges free to use, and probably you need to wait for some time in order to get a specific range. And again, this organization assigns and controls public IP addresses ranges. And also notice that you need to pay for public IP addresses. They are not free. And also you could verify which company any public IP address belongs to. For example, if I'll go here and type RIP check IP address and click, for example, on this first link, and here in this search bar, please enter A.A.8. Remember that this IP address we have used before, and I have told you that this IP address is assigned to Google servers, and this IP address is from public IP addresses range. We could basically verify that and it belongs to this range. So let's query for this IP address, press enter here, and also please select this checkbox search resource objects in all available databases, this one, and click search once again. And if you'll scroll down, you'll see that this network, entire network A.8.8.0 with mask 24 is assigned to Google. Also here on this line origin, you see special number AS15169, and it is actually autonomous system number that is also assigned by RIP or other organizations. And we will get back to this term a bit later when we will talk about global routing protocol called BGP. Also, except that you could find, for example, contact email of the owner of this specific public network range. That's how you could easily verify owner of specific public IP address. If you know some other public IP addresses, feel free to create another query or two. Great, that's all for this lecture, and next let's discuss what is static IP address and what is the difference between static and dynamic IP addresses. I'll see you guys in the next lecture. We have just discussed the difference between private and public IP addresses. And now let's discuss difference between static IP addresses and dynamic IP addresses. And let's start by talking about static IP addresses. So static IP address is IP address that is assigned to specific device, and this IP address does not change. And in this example, there is IP address 2512 that is assigned to this specific web server, for example. And the advantages of using static IP addresses are following. Static IP address is convenient for any static services like web service, email service, or something else. And when such IP addresses are assigned to specific servers, it means that you are able to access those servers permanently using a permanent static IP address. It is very easy to use. And also it is possible to use a DNS service, domain name service, in order to map a host name of specific server to its IP address. And this mapping will be also permanent. And you will be able to access any server either using its host name that is included in domain name or its IP address. In similar way, we have actually accessed Google's DNS servers a.a.a.a. This IP address is public and it is static. But of course, there are some disadvantages of using static IP addresses, and the first one is that public static IP addresses, of course, are expensive. And that's because you need to pay for any public IP address or public IP addresses range when you rent this range. And when you assign a specific static IP address that is public to specific server, this IP address will not be able to be used on other servers. So it is reserved only just for one server. And of course, when you use static IP addresses, then you need to take care about additional security of the servers that are configured to use those IP addresses, because attackers may attack those servers very easily when they know their IP addresses and when they know that those IP addresses are not changed. And in such case, you could set up, for example, firewalls in front of any servers that use static IP addresses and open only necessary for web server, for example, or SMTP server ports, and block any other incoming connections. Alright, that is a static IP address. And usually it's no need to assign static IP addresses to end-user devices like your mobile phones or your laptops. And in such case, you could easily use dynamic IP addresses. But let's discuss dynamic IP addresses in the next lecture after this small pause. Previously, we have discussed what is static IP address, and static IP addresses are usually assigned to public servers that are running some public services like a web service or SMTP service. And now let's discuss where and how dynamic IP addresses should be used. Dynamic IP address is IP address that is assigned dynamically to different devices. And usually this assignment happens using a special protocol and special server called DHCP server. DHCP stands for Dynamic Host Configuration Protocol. And using this protocol, you could automatically assign different IP addresses to different devices. And in this example, this laptop has dynamically assigned IP address, for example, 5711. And when any device has IP address already assigned, of course, such device may be able to communicate with other devices in the network. And it happened that in this example, this IP address is actually from public IP addresses range. But of course, when we talk about local area networks, then it makes sense to use, of course, private IP addresses ranges. Let's discuss now advantages and disadvantages of dynamic IP addresses. First of all, dynamic IP addresses are actually cheaper than static IP addresses. And in most cases, they are even free, because they are used from private IP addresses ranges. And when you use dynamic IP addresses, then of course you gain more privacy, because it's more harder to gain access to specific device when its IP address may change and changes over time. Also, please notice that there is special service called Dynamic DNS, or shortly DDNS, and using this technology you could automatically update mapping of hostname to IP address when IP address of a specific device changes. And using DDNS, you could even use dynamic IP addresses on public servers, and information in DNS records will be updated automatically. But please notice that update of DNS systems all over the world takes some time, and we will get back to it a bit later in the course. And sometimes your servers may be inaccessible when information in DNS cache is obsolete. And that is actually a disadvantage of using DDNS, so be careful with that. Now let's discuss disadvantages of dynamic IP addresses. First disadvantage is that it could be easily changed, and one time you could have one dynamic IP address assigned, in several hours this IP address may change. And of course, in such case, when you want to use dynamic IP addresses, you need to set up and manage DHCP server that is responsible for assignment of dynamic IP addresses to different devices. And of course, please notice that when you have set dynamic IP addresses assignment on specific end-user devices like your mobile phones, then of course when you change your location and move from one network to another, then IP address assigned to your device will of course change, because different networks have different DHCP servers and of course different IP addresses ranges. That is dynamic IP address. Alright. Let's next make a quick demo and let's observe whether our IP addresses are assigned dynamically to our computers or not, and if dynamic, then let's change it to static assignment. Let's try that next. We have just discussed differences between static IP addresses and dynamic IP addresses, and also discussed their advantages and disadvantages. And let's now quickly observe how IP addresses are assigned to our computers. And for that, I'll go to network settings of my network adapter, open network preferences, and here I'll click advanced, and here go to TCP IP. And I see that in my case I use actually DHCP. And that means that IP address that I see here is assigned to this computer automatically by DHCP server. And basically, in my case, wireless router that I am connected to acts actually as DHCP server, and it assigns IP addresses to all devices connected via wireless connection. Here I see IP version for address, here is subnet mask, we will discuss subnet masks just in next section, and here is default router. And also please note that I could click on this button, renew DHCP lease, and renew DHCP IP address assignment. Let me try that. And I see that the same IP address was assigned again. And the reason for that is that DHCP server has in memory previous mappings, and if a specific client reconnects after a specific amount of time, then the same IP address will be assigned to it as before. And this record is kept in memory for some period of time. Of course, when you reload the device, your DHCP server, those records may be flushed out, or you could clean this cache yourself. Alright, now let's try to assign IP address to our computer, not by DHCP, but using static assignment. For that, I'll choose here option 2 manually, like that, and now let me assign IP address from the same network range, and I'll assign IP address, for example, 192.168.1, and here in last octet I could use any value from 1 to 254. And I'll explain you why 0 and 255 are excluded from this range. And let's, for example, use 200 as value in last octet. Notice that subnet mask actually specifies where I'm able to change host part, and actually I'm able to set any value only in last octet. First 24 bits are fixed, that's why I have put here 192.168.1. Alright, let's save changes, click OK. And now let's try to click apply and verify whether I'll still be able to connect to internet or not. And I'll go to web browser and here connect, let's say, to Google.com, and I see that there is no internet. Probably changes were not yet applied. It seems that I need to set also DNS records manually, and I could add here 8.8.8.8 as DNS server. Remember that it is Google's DNS servers, and here I'll click OK and click apply. And now let's verify connection, and now web server has responded correctly. That's how I was actually able to change IP address of this computer to static IP address. If I go back to network settings and go to advanced TCP IP and change IP address, for example, to, let me try to set IP address from other range, for example, let's say 3, and save changes. Apply. And refresh page again. I'll see that the server actually doesn't respond. And the reason for that is that I have set IP address to this computer from other network that differs from the network where my default gateway is located. So here is this difference. So now my computer is in different network than my default router. Alright, let me get back to DHCP assignment like that. Click Renew DHCP lease. And notice that I was assigned IP address that I have just used in static assignment. It is .200. Alright, let's click OK, apply, and try to refresh page here, and I am again connected to internet. That's how we were able to change dynamic assignment to static assignment and back. Great, that's all for this lecture and comparison of static IP addresses and dynamic IP addresses, and next let's discuss structure of the header of IP packet. It has a bunch of different fields, and let's discuss them next. I'll see you guys in a moment. You already know, guys, what is the difference between private and public IP addresses. You know what is IP address, and also you know what is the difference between static IP addresses and dynamic IP addresses. And now it's finally time to talk about the structure of IP version 4 packet. And please notice that IP version 4 packet does not have any trailer. It contains only header. Recap that on the data link layer in frame there was frame check sequence at the end of the frame. In IP version 4 packet there is only header that contains multiple sections. And please notice that minimal header length is 20 bytes or 160 bits. Also, there could be additional options after destination address field, but the options are optional and they are actually used not so often at all. Alright, let's now have a look at IP version 4 packet header in greater details, and I'll explain you what every section here means. IP version 4 packet header starts with version. Version is 4 bits long, and for IP version 4 packet it is always set to 4 in decimal format. Next section is IHL, that stands for Internet Header Length. And in this field you may find the length of the header of IP version 4 packet. Minimal length, as I have told you before, is 160 bits. And actually in this field AHL you may find the quantity of 32 bits sections. And by default there are 5 such sections. Here is first section, here is second, I am talking about rows. Here is third, fourth and fifth. And that means that there are minimum 5 32-bit sections. And that's why in most cases in IHL field you'll find value 5. That stands for 5 32-bit sections in IP version 4 packet header. Alright, that is IHL. Next field is DHCP, that stands for Differentiated Services Code Point. And using this field, it is possible to prioritize different packets over other packets. Let me give you an example. Let's suppose that there are multiple data streams coming via router, for example. And there are FTP stream. FTP is used for transfer of large files like video files or something else. There is another data stream that is HTTP data stream, someone browses internet. And also there is a third small stream that stands for voice communication, real-time communication between some endpoints. And using DHCP field, you are able to prioritize voice packets that are coming from a real-time application, for example, Skype or something else. That is DHCP. Some large packets may wait until router will process in priority some small real-time packets. Alright, next field is ECN, that stands for Explicit Congestion Notification. And using this field, routers could tell others that there is congestion on some of the links. Recap that we have discussed that it is possible to congest some links when there are more incoming packets that the router is able to process on outgoing link. And in such case, routers could mark some packets using ECN field. And that is an indication for other routers that there is somewhere congestion on the link, and probably they may slow down transmission rate. It is achievable, for example, using TCP protocol on upper layer of TCP IP model. I'm talking about transport layer. Alright, that is ECN field. Next field is total length. And in this field you may find total length of entire IP version 4 packet. And the possible sizes are from 20 bytes, it is actually only header, till 65,535 bytes. It is a maximum packet size. Again, total length is length of entire IP version 4 packet. Next three fields in IP version 4 packet header, identification, flags and fragment offset, are used for common purpose. And purpose is following. Large packets may be splitted into smaller packets, called fragments. But those fragments, technically, are parts of the single packet. And when packet was splitted into specific fragments, and this could be performed, for example, by sender or by router on the path between sender and receiver, then in identification field there will be unique identifier, and it will be the same in all fragments of the same packet. And this unique identifier is required in order to allow destination host to gather all fragments of the single initial packet to the original packet. Because there could be different fragments of different packets. And if there is no such identification field, then recipient will be able to understand which fragment belongs to which packet. In the next field flags, you may find information whether packet was fragmented or not. And if it is not a fragmented packet, then in those flags will be 0 bit that stands for non-fragmented packet. Otherwise, if a packet was fragmented, then here you'll find bit 1. We will see it on practice. In the next field fragment offset, you may find ID of specific fragment, because if one packet is split into multiple fragments, then each fragment has specific offset number, 1 by 1. And that's a field that is used for that, fragment offset. These are three fields that are used for fragmentation purposes of the single packet. Alright, next field is time to live, and it is 8 bits long, and this field is used for following purposes. Recap that every packet travels via routers independently from others. And basically it is possible to get into a situation when single packet will travel in a loop. So for example, one router will send packet to another router, and another router will send this packet back to the original router. It is possible. The easiest way to achieve such situation is to set default routes on both routers pointing to each other. And this field, TTL field, is used to prevent infinite loops of single packet. And when TTL field becomes 0, then router simply silently discards such packet. And basically every router, when it receives specific IP packet, it decrements TTL field by 1. And afterwards sends packet to next router. Next router performs the same action. It decrements by 1 TTL field. And again, when it becomes 0, then router simply silently discards such packet. Alright, next field is called protocol, and it is 8 bits long, and it is actually link to upper layer protocol that is used inside of this IP version 4 packet. I'm talking about this data payload section. Because if there is a transport layer header, then this protocol field will point to specific protocol, for example TCP or UDP, that is encapsulated here inside. Next field is called header checksum, and it is similar to FCS field in frame, in the trailer of the frame. But on data link layer, FCS was calculated based on entire frame. Here, this checksum is calculated only from the IP version 4 header. So data section is not included here in calculation of this header checksum. And please notice that every router, when it receives a specific IP version for packet, and when it decrements TTL field by 1, needs to calculate new header checksum. Every router performs this action. Alright, after this field comes source IP version for address field that is 32 bits long, and after source address comes destination address that is also 32 bits long. After destination IP version for address, there could be optional options that are almost never used. And after that comes data or payload. And again, notice that this data payload may contain other headers, for example, TCP or UDP headers. That is a structure of IP version for packet, and again, notice that minimum size of IP version for header is 20 bytes or 160 bits. Great, that's all for this lecture, and next let's have a look on practice on IP version for packets, and for that we will again use Wireshark. I'll see you guys in a bit. Now let's get back to Wireshark and analyze a few IP version for packet headers. Let's go there and start capture by clicking on this blue icon. Let's wait for several packets to arrive. It's enough. Let's stop capture and let's open up any packet you like. And let's expand the Internet Protocol version for header, for example this one. And recap that the header starts with version field. And it is set to 4 in decimal format or in binary to 0100 for IP version 4 protocol. Very simple. Next comes header length, and recap that it is set to quantity of 32 bit sections. And if there are no options in the header, then this value will be set to 5. 5 32-bit sections, in total 160 bits. And in binary format it is 0101. Here you see that. Next field is DHCP field, Differentiated Services Code Point, and in this specific packet it is set to CS0 or 6 zeros. This field is 6 bits long, and it means that this specific packet has no priority over other packets. This is default priority, all zeros. And also basically you see default here. Next 2 bits stand for ECN, explicit congestion notification, and here you see default value as well, 2 zeros. And also you see here not ECN capable transport, and that means that my computer actually does not support processing of those bits, and even if they will be set, they will be simply ignored. Alright, that is DHCP and ECN. They are grouped together in Wireshark output. Alright, next field is total length, and it is length in bytes, and this length is length of entire IP version 4 packet. Recap that header length is 20 bytes, here you see that, and the remaining part is, in this example, 32 bytes long. Total length of entire IP version 4 packet. Alright, next you see identification field, flags field and fragment offset. And those fields are used together. And basically, this specific IP version 4 packet is not part of fragment sequence. And actually here you see flag don't fragment. And basically this second bit here that is set to 1 tells that this packet should not be fragmented. And this bit is called don't fragment. And if a packet is fragmented and there are more fragments coming afterwards, then this third bit that is set in this example to 0 will be set to 1. Again, if it is a fragment. Alright, that's our flags that are related to fragmentation process. And next field fragment offset is also 0 in this case, it's default value, because again this packet is not a fragment. For fragments, those numbers will be different. Each fragment will have separate offset. Alright, next field is time to live or shortly TTL, and here you see value 64. And basically this specific packet comes actually from my computer. Here you see MAC address of my wireless adapter to wireless router, and my computer has set this TTL field to 64. And basically different devices set different default values for TTL. There is no common approach here. But in this example, you see value 64. And nearest router will decrement this TTL field in IP version 4 header and send this packet to next router, and so on. Next field is protocol, and it is set to TCP here. And TCP has its own reserved value of protocol, and it is 6. That's why here in the protocol section, if you will see 6, then you could understand that inside of this data section, inside of payload, there will be TCP header. And basically here we see that this header comes next. So it is a link to inner protocol that is encapsulated inside of this IP version 4 packet. Next field after protocol field is header checksum, and recap that here you will find the checksum of entire IP version 4 header that doesn't include data or payload. And any router or receiver may verify this header checksum in order to be able to understand that the IP version 4 header was not changed during transmission. But in this example, you see that validation is disabled and header checksum status is unverified. And actually, you are able, using one of the options inside of Wireshark, enable validation of header checksum, if you want. But honestly, header checksum is a bit redundant, because recap that there is a checksum field, FCS, at the end of every frame. And if frame was changed on the way, and if it was corrupted somewhere, then frame will be discarded on data link layer. It will not go up to network layer. That's why actually there is no need to check header checksum in IP version 4 packet. But actually there are other protocols that work on data link layer of TCP IP model that don't have checksum. And in such case, this checksum in IP version 4 header may be helpful. Alright, next field is source IP address, and in my case I see IP address of my computer that ends with 182, and destination is here. And notice that source IP version 4 address is from private range, and destination IP version 4 address is from public IP addresses range. If you don't trust me, please get back to one of the previous lectures and have a look at diagrams which show ranges of private and public IP addresses. Alright, that's our final fields here in IP version 4 header, source IP version 4 address and destination IP version 4 address. That's it for this specific IP version 4 packet. Great. Next, after the small pause, let's have a look at one more packet and compare its header with this header. I'll see you guys next. Alright guys, we have just analyzed one of the IP version 4 packet headers, and now let's do one more analysis and let's try to capture DHCP requests and responses and afterwards analyze those packets. Recap that DHCP is used for dynamic assignment of IP addresses to devices, and I'm using DHCP on my computer. So for that I'll disable network adapter, turn Wi-Fi off. Next I'll start new capture, continue without saving, and next I'll turn Wi-Fi on. Alright, Wi-Fi is on and now I'll stop capture, and here in display filter I'll enter DHCP, like that. And I see two DHCP packets. And let's have a look at first one that has source all zeros and destination all 255s. And let's expand IP version 4 header here. This field and this field are the same as in previous packet. So version is 4 and header length is 20 bytes. And value here is 5. 32 bits sections in IP version 4 header. Next, DHCP field and ECN are default, so CS0 and 00 for ECN. Next comes length of entire IP version 4 packet, in this example 328. Next, in identification field, I see special ID, and that means that this packet is one of the fragments. But in flex section, I see that bit don't fragment is not set and bit more fragments is also not set. And that means that this fragment is last one in the sequence. And actually, I see no need for fragmentation for this specific packet, but actual fragmentation was performed, and there is just single fragment in this example. Single fragment that belongs to this specific fragment group. And fragment of set for this fragment is 0. This is the first fragment in the sequence. Alright, TTL is set in this example to 255. It is the largest possible value for TTL field. Protocol is UDP, and UDP has its own ID, it is 17. Recap that TCP had value 6, UDP has value 17. That is included in protocol field in IP version 4 header in this specific IP version 4 packet. Next comes header checksum. Again, there's a checksum that is calculated of all fields in the IP version 4 header. And next, you see source IP version 4 address that is set to all zeros. Why is that? Answer is very simple. My computer does not have IP version 4 address at this moment of time because it requests IP address from DHCP server. That's why source IP version 4 address here is all zeros. And destination here is broadcast IP version 4 address. In binary format, it is all ones. And when such packet is sent in switched local area network, then all devices, all other computers, must process such packet because it's a broadcast packet. Destination IP version 4 address here is set to broadcast. And the reason why it is set for broadcast is that we are actually searching for DHCP server in our switched network. And if there is DHCP server, then it should see this packet and respond to us and assign us IP version 4 address. Alright, that is the IP version 4 header in this specific DHCP request. I will not dive deeper and look at UDP and DHCP sections, because now we are analyzing IP version 4 header. That's why let's have a look at another DHCP packet, this one. And in this one, I see same fields here, here, here. Total length is similar. Identification field has another identification ID. It means that this response packet is actually also fragment, but it is the last fragment in the sequence. Here we see more fragments not set, and fragment of set is 0. Next, TTL is set to 64. Let's compare it with TTL in this request. It was set to 255. Here you see 64. And that's what I have told you. Different devices set TTL, original TTL differently. Next comes again protocol UDP, because inside there is UDP header. Next header checksum. Source is IP address of wireless router that acts actually as DHCP server. And destination is set to 192.168.1.182. That is IP version 4 address that was assigned by DHCP server to my computer. And basically you see same IP address that I have used before. Alright, these are examples of IP version 4 headers in DHCP request and response. And now let's quickly analyze also ARP protocol packets. You should see several ARP requests on your computer as well. And now, surprise! We don't see IP version 4 header in this specific packet or this one or this one. Immediately after Ethernet 2 header comes ARP section. And here, for example, I see sender MAC address, sender IP address, target MAC address, and target IP address. I will not dive deeper now into ARP protocol, but I want to just show you that ARP actually works at network layer of TCP IP model, and it does not require IP version 4 header. And if I expand Ethernet 2 section and have a look at ether type here, it points to ARP protocol, not IP protocol, and ARP has its own ether type 0806 in hexadecimal format. That is an example of this specific ARP request. That's all for this lecture, and that's all actually for this section, where we have dived a bit deeper into IP addressing and discussed structure of IP version 4 packet. And next, let's summarize what we have here discussed. I'll see you just in a bit. We have finished this introduction section dedicated to network layer of TCP IP model, and basically we have just started talking about network layer, and we are not yet done. And in the next sections we will talk about subnetting, about routing protocols in details, but in this introduction section I wanted to give you some first insights on what is router, what is IP address, and what is the difference between different kinds of IP addresses. And now let me quickly summarize what we have discussed here in this section. We have started by talking about disadvantages of switched network, and there are two disadvantages. First, broadcast frames travel across entire switched network, and if it is really large and if it has many devices, then it could simply slow down transmission of regular unicast frames. Second, MAC addresses tables become very large if there are many different devices in switched network. That's why we need to have some kind of solution that allows us to interconnect different switched networks. And that solution is split devices into different networks on network layer of TCP/IP model and place routers between them. And we have discussed that IP address is a logical address that is assigned to devices on network layer of TCP/IP model. And in this example, you see IP version 4 address. Next, we have discussed the difference between IP version 4 and IP version 6 addresses, and here you see two examples of IP version 4 and IP version 6 addresses, and the length of IP version 4 address is 32 bits, whereas IP version 6 address length is 128 bits. And this address is represented in hexadecimal format, while IP version 4 address is represented in decimal format. It is much more easier to read. Alright. Next, we have discussed details about IP version 4 address format. It contains 4 octets, each octet 8 bits long, and totally there are 32 bits. And in general, there are about 4.5 billion IP version 4 addresses available. And you could represent IP version 4 address in binary format as well, like in this example, but it is not convenient for understanding and use. Alright. Next to it, we have discussed difference actually between MAC addresses and IP addresses, and I have told you that devices in the same switch network must have IP addresses from the same network. And in one of the previous lectures, we have actually tried to change IP address of local computer to IP address from other network that is different from the network where router is located. And I was not able to access internet or other services. Because again, in the same switch network, devices must have IP addresses from the same network. But MAC addresses may be, of course, produced by different manufacturers and have different OUI prefixes. Great. We have discussed that there are three types of IP addresses: unicast, multicast, and broadcast. When there is a point-to-point transmission, then unicast IP addresses are used as source and destination. If you want to send some IP packets to group of devices, then you could use multicast IP address as destination. And when you want to send a specific IP packet to all devices in the same switch network, then you could use broadcast IP address as destination address. Next, I have explained you what is a router, and the router is a network device that operates on physical, data link, and network layers of TCP/IP model. And main responsibilities of every router is first to find paths to remote networks, and second to route packets to destination networks. And basically routers interconnect different networks. Alright, we have discussed also what is the difference between local area network and wide area network, and LAN is a set of network devices, end-user devices, and connections between them that are under common administration. And usually LANs are located in the same geographical area. WAN is a set of different local area networks, and Internet is the largest WAN available. Alright, next we have discussed on this example how routers interconnect different networks, and actually routers allow different LANs to be connected together into WAN. And in this example, I have demonstrated you two different local area networks that are connected to internet, and that's why those LANs are able to communicate with each other. And that's thanks to routers. Alright. Next, we have discussed the different classes of IP addresses, and there are 5 such kind of classes: A, B, C, D, and E. And you could use classes A, B, or C for assignment of the IP addresses to end-user devices. You are not able to use class D or class E addresses, because D is reserved for multicasting, and such IP addresses could be set only in destination field. And the class E addresses are experimental and are reserved also for future use. Alright, next we have discussed what is localhost, and such IP address as 127.0.0.1 is actually available on all operating systems, and using this IP address you could connect to any local service, like web service or some other services that are running on your local computer. Next to it, we have discussed what is the difference between private and public IP addresses, and now you know that devices with private IP addresses are not able to access internet if their IP addresses will remain the same in source IPv4 address field in IPv4 header. And that's why we could use some kind of network address translation and replace source IP addresses in packets with public IP addresses, in order to allow such devices as this one or this one or this one access internet. And of course, private IP addresses could be reused in multiple places of internet, and they are reused. We have discussed different ranges of private IP addresses. There is single class A network that is considered as private. Here it is, 10.0.0.0/8. 8 is network prefix, and it actually tells where network part of network prefix ends and where host part begins. We will get back to it in next section and discuss in greater details. There are also 16 class B networks that are considered as private, and in first octet you will find here 172, and in second one could be any number from 16 to 31. And here is an example of class B private network, 172.16.0.0/16. 16 is default mask for class B network. And there are also 256 class C networks, and in first and second octet you will always find here 192.168, and in third octet there could be any number from 0 to 255. That's why there are 256 class C networks available. And here is an example of a private network from this range. Class C network 192.168.10, and 24 is default network mask. 24 bits are network part, and 8 bits host part. And in general, there are 18 million IPv4 addresses that are considered as private. And most popular networks are 10.0.0.0/8 or 192.168.10/24. Alright, that's our private IP addresses ranges. All other IP addresses that belong to class A or B or C and are not private are public IP addresses. And here you see ranges of public IPv4 addresses. There is also difference between static IP addresses and dynamic IP addresses. Static IP address is assigned to specific device statically, and usually static IP addresses are used for public servers that have some services like HTTP or SMTP enabled, and in such case those servers will always have the same IP address. And dynamic IP addresses are usually used for end-user devices like mobile phones, laptops, computers, and the dynamic IP addresses are assigned via DHCP protocol by DHCP server, and devices that have DHCP enabled end-user devices may have different IP addresses at different moments of time. But in all cases, they may easily access internet, even with different IP addresses at different moments of time. It is very easy. And MAC address is usually unchanged. Great, that is a dynamic IP address, and next to it we have discussed structure of IPv4 header, and the header is 20 bytes long without options, or 160 bits, and it contains multiple fields, and the most important for us are source IPv4 address and destination IPv4 address. There are also 3 fields that are used in conjunction and are related to fragmentation of packets. And if packet is very large, then network devices like routers may fragment those packets themselves. And those fields, identification, flags, and fragment offset, are used for that purpose. Also, there is important field protocol that actually tells us which protocol header is encapsulated here at the beginning of a data payload section. And we have seen that, for example, TCP has ID 6, number 6, as protocol ID, and UDP has number 17 as its ID. Also, there is TTL field that is used to prevent infinite looping of specific IP packet. And every router actually decreases TTL by 1 when such packet is received by router. And of course, in such case, every router must recalculate header checksum when IP packet is sent to next router. It means that every router performs some operations with IP version 4 header. It does not keep it the same as in incoming packet. Alright, also there are such fields as DHCP that is used for prioritization of different packets, and ECN that could indicate whether there is a congestion somewhere on some link on the way between the sender and receiver. Other fields are, I could tell, technical fields, and they are not very significant, like total length or IHL or version or header checksum. Alright, that's all for IP version 4 packet header, and that's all for this section. In the next section, we will dive a bit deeper into subnetting, and I'll explain you in details what is network mask, how it is used, how you could determine whether two different IP addresses belong to the same network or not, and how you could actually perform subnetting on your own. I'll see you guys in the next section. I hope you enjoyed previous section, and now it's time to move on to next section. And in this section we will discuss in greater details what is mask, what is subnet, and how to perform following actions. First, determine whether two IP addresses belong to the same network or not. Second, calculate quantity of available hosts in specific network or subnetwork. And third, how to perform subnetting yourself. Please note that we will not dive too deep into subnetting. And single goal of this section is to make you clearly understand what is mask and how it is used in computer networking. That's why let's get started, and let's start again with explanation of what is network and what it consists of. I'll see you inside. Let's start our discussion about subnetting and network masks, and first let's get back to definition of network. Network is actually a logical group of devices, and every network in computer networking consists of two different parts. First part is network prefix, and the second part is network mask. And basically using network mask, we define where in network prefix is network part and where is host part. And in the same switched network, devices must have same network prefix, but they have different values in host part, this part. That is the purpose of network mask. And now let's have a look at several examples of network and define what is network address, what is broadcast network address, and what is IP address of regular host in network. Let's have a look at first example next. So network consists of two parts, network prefix and network mask. And let's have a look at example of the first network. And in this example, network is 10.0.0.0, it is network prefix, and mask is /8, or in decimal representation 255.0.0.0. So masks have different representations, either slash representation like in this example, or in decimal format. Alright. So network address here is equal to network prefix. It is 10.0.0.0. Next address is network broadcast address. And in this example, broadcast address for this specific network is address where in host part all bits are 1. And broadcast address for this specific network is 10 .255.255.255, all ones in the host part. Recap that in this example, network part is first 8 bits, and remaining 24 bits is host part. And finally, here is an example of the host address. Address that could be assigned to any host in this specific network. And I have used IP address 10.5.0.41 as an example of IP address in this specific network. But technically, here could be any IP address between those two addresses, this one and this one. Even address 10.0.0.1 will work. This IP address is also host address in this network. So, in any network, there are two reserved IP addresses. First IP address is address of network itself, that is equal to network prefix. Second address is broadcast address, where in host part there are all ones, and all IP addresses in between could be assigned to any host in this network. But please keep in mind that all hosts in this specific network will have network mask equal to this mask, /8 or 255.0.0.0, if they belong to the same network. That is a first example of specific network that consists of network prefix and network mask. Next, after the pause, let's have a look at one more example. Now time for a small challenge. Here is a network that consists of network prefix and network mask, and please specify network address, broadcast address, and any host address for this specific network. I hope it was very easy. Let's do that together. So network address is equal to network prefix 172.19.0.0. Broadcast address is address where in host part all bits are ones, and host part in this specific network has 16 bits, so broadcast address will be 172.19.255.255. And the sample host address will be any IP address between those two. So let's add some sample address 19. Let's say 100.12, like that. So here is a sample IP address that belongs to this specific network. Again, network address is equal to network prefix. Broadcast address has all ones in host part, and host part is defined by network mask. And host address is any address between those two. Alright, that was example number 2, and next let's have a look at one more example. One more example. Here is a network with mask 24, and the first question whether this network is from private range or not, and the second, same as before, please fill in network address, broadcast address, and sample host address. Answer to the first question is yes, this network is from private IP addresses range. Network address is equal to prefix 192.168.7.0, like that. Broadcast address will be 192.168.7.255, and the host part in this specific network has just 8 bits, because 24 bits is network part. Host address will be any between those two addresses, 192.168.7 and let's say 80. And here is a sample IP address in this network. If I write here, for example, 10.80, then this IP address will be from different network, because I have modified network part. That's why I'll get back to 7 here in third octet. That is the example of a class C network range, actually. And now let's quickly go into the terminal and try to ping network address and broadcast address of the network we are currently located in. I'll check my network. So I'll go to network settings here, and my network here is 192.168.1.0/24. And I don't see mask here actually in this output, that's why I'll go to network preferences, go to advanced, and here TCP IP I'll see subnet mask. So in decimal format, it is 255, 255, 255.0 or /24. 24 bits is network part, and remaining 8 bits is host part. That's why I'll ping now IP address of my network, that is 192.168.1.0. Afterwards, I'll try to ping broadcast address of this network 192.168.1.255, and let's see what will happen. So let me close this, go to the terminal, and here I'll enter ping 192.168.1.0. It is network address of the network I am currently in. Let's see what will happen. And I see request timeout. And that means that nobody answers for this request. Great, let's clear terminal, and now let's try to ping broadcast address of my network. Ping 192.168.1.255. Recap that network mask is 24, that's why 8 bits, remaining 8 bits is host part. That's why here I have placed ones in host part, 255 in decimal. Let's see what will happen. And now I see responses from multiple IP addresses. Actually from my own IP address, here it is, and from other IP address that is located in the same network. And basically this IP address is assigned currently to my phone, mobile phone, that is connected to the same wireless network. And that means that when you try to access a broadcast address of your network, then all devices in your network will actually receive such packets. And basically you don't see response from my wireless router. And it seems that it is configured not to answer to broadcast network requests. That's simple as that. Alright, that's how you could verify that the broadcast address of the network is actually used if you want to communicate with all devices in the same switched network, in the same IP network. Alright, that's it, and now let me try one more thing, and I'll try to ping broadcast IP address. Let's do that. Ping 255.255 once again and once again. It is a broadcast IP address, and let's see what will happen. I see again responses from two IP addresses, from my own and from IP address assigned to mobile phone. And that means that you could also use this IP address as destination IP address in IP packet in order to make all hosts in the same network receive this IP packet. Alright, that's quick demonstration, and that's all for those examples where we have actually defined what is network address, what is broadcast network address, and what is host address. I hope that it is easy for you now to clearly understand what is the difference between those three addresses. Alright, next let's dive a bit into binary math, and I'll explain you how to convert binary numbers to decimal numbers and back. And I'll explain you how to perform OR and AND operations using binary numbers. And let's do that after a small pause. Let's now, guys, talk about binary math. And I'll explain you how to convert binary number to decimal and decimal to binary. And the good news is that you need to know only how to convert 8 bits binary numbers to decimal and back, because in IPv4 address there are 4 different decimal numbers, and each is represented using 8 binary bits. Very simple. So here in this table you see some examples of decimal numbers and their representations in binary format. So in decimal we have 10 available symbols from 0 till 9, and in binary we have only 2 symbols, either 0 or 1. Very simple. And in those examples, 25 is 11001 in binary format, 60 is 111100 in binary format, and 123 is for ones 011. But again, when we talk about IP addresses, IPv4 addresses, about subnetting, masks, and so on, then we usually talk about 8-bit sections, because there are 4 8-bit sections in IPv4 address. That's why you need to know how to convert binary numbers to decimal using 8 binary places, 8 binary digits. So here is an example of conversion of this binary number that consists of all ones, so 1111, 1111, 8 ones, to decimal. In order to convert a binary number to decimal number, you need to sum powers of 2. And here in those colored sections, you see actually powers of 2, starting from 0. 2 to power of 0, 2 to power of 1, 2 to power of 2, and so on, till 2 to power of 7. It is bit number 8, because we count bits from right to left. And when we want to get a decimal representation of this binary number, all ones, we need to sum up all those powers of 2. 128, that is 2 to power of 7, 64, that is 2 to power of 6, 32, that is 2 to power of 5, and so on. 2 to power of 0 is 1. It is at the end here. And finally, when we sum up all those numbers, all those decimal numbers, we get decimal number 255. And that is the largest decimal number that could be represented using 8 binary bits. And the lowest decimal number is, of course, 0, when here on all places we have zeros. In such case, we actually sum up all zeros and get 0 in decimal format. So 8 zeros in binary format is 0 in decimal format. Let's have a look at another example, and in this example we have another binary number 1010101. And in such case we need to sum up only those powers of 2 where we have 1 in binary format. So here, 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 and here. All remaining places will be simply 0, like that. And in this example, we sum up 128, that is 2 to power of 7, 32, that is 2 to power of 5, 8, that is 2 to power of 3, and 1, that is 2 to power of 0. And we get 169. That is another example. If you don't understand clearly what happened in those examples, try yourself. Please write any sequence of 8 binary digits, either 0 or 1, and try to convert them to decimal format. Alright, that's all for conversion from binary digits to decimal numbers, and in the next lecture let me explain you how you could convert decimal number to binary number. I'll see you guys next. I have just explained you how you could perform conversion of binary number to decimal number. And for that you need simply sum up corresponding powers of 2. And the largest power of 2 in IP version 4 binary math is actually 7th power, and it is 128 in decimal format. And now let me explain you how you could perform opposite conversion from decimal number to binary number. And let's have a look at this example where I want to convert number 140 to binary format. And for that you need to do similar task as before, and you need to write down all powers of 2 like that. And I have written all those powers above corresponding digits, and they are same as before, 8 digits. And now we start from the left bit, this one. And we compare this number and this number. If this number is larger than this one, then we put here 1, like that, and afterwards deduct from 140, 128, like that. Remaining number is 12. Now we compare this number 12 with 64. 64 is larger, that's why here we put 0. Next go to next bit, 32. 32 is also larger than 12, that's why here will be also 0. Next bit, 16. 16 is also larger than 12, that's why again 0 here. Next value 8. 8 is less than 12, that's why here I put 1 and deduct 8 from 12, like that. Remaining number is 4. Next bit here, and next number is 4. That's why here will be 1, and 4 minus 4, we get actually 0. That's why remaining bits here and here will be zeros. Simple as that. Alright, now task for you. Please try to convert this number, 228, to binary format using same approach. I wish you good luck. Alright, let's perform the same action together, and again we start from this left bit and compare this number and this number. This number is less than this number, that's why we put here 1, and from 228 we deduct 128, like that. It is 100. Next we compare 64 and 100. 64 is less than 100. That's why here I put 1 and deduct 64 from 100, like that. Remaining part is 36. Next I compare 32 and 36. This number is less than, that's why here I put 1 and deduct 32 from 36, like that. Remaining number is 4. Next I compare 16 and 4. 16 is larger than 4, that's why here will be 0. Same applies here. 8 is larger than 4. 0 here as well. Next number is 4. 4 is equal to 4, that's why I deduct 4 from 4 and get 0 and put 1 here on this place. And of course here will be 0 because 2 is larger than 0, so 0. And 0 here as well because 1 is greater than 0. That's how you could perform conversion from decimal number to binary number. Now you know how to perform two-way conversion from decimal number to binary number and back. And let's proceed, and I'll explain you what is AND and OR logical operators in binary math. I'll see you guys next. Previously we have discussed how to convert binary number to decimal number, and we have talked about binary numbers 8 digits long. Why 8? Because IP version for address is 4 sections of 8 bits. And now let's discuss binary math a bit deeper, and let's discuss AND and OR operators. They are very easy, and in this example let's have a look at AND operator. And let's suppose that we have two binary numbers 4 bits each. Number x and number y. And number x is 1010, here is this number, and number y is 0011, this number. And when we perform AND operation in binary math, then in result we will have zeros everywhere when any of incoming numbers have 0. And we will get 1 when all incoming numbers have 1 at corresponding place. So let's start from right. Here we have 0 and here we have 1, and AND operation in this case will produce 0, because here is 0, this AND operation in binary math. Here we have two 1s, that's why AND operation will produce 1. Here we have two 0s, and the resulting value will be 0. So 0 and 0 will produce 0. And the fourth digit, we count digits from right to left, 1 here and 0 here, AND operation will produce 0. And it means that we perform AND operation bitwise, bit by bit, starting from very last bit here. Actually, you could start from here, doesn't matter, result will be the same. And resulting binary number after AND operation x and y will be 0010. It is binary number with 4 digits. Similarly, you could perform AND operation between any other binary numbers any length long. Next, let's have a look at OR operation, binary OR operator. It works in similar way, bitwise, but now it will produce 1 when any of incoming bits here or here is 1. Let's start from those bits. Here we have 0, here we have 1. 0 or 1 will produce 1. Here we have 1 and here we have 1. 1 or 1 will produce 1. 0 or 0 will produce 0. It is a single combination here that will produce 0 using OR operator. And one more bit, 1 here, 0 here, 1 or 0 will produce 1. And here is resulting binary number after OR operation of x and y. It is 1011, binary OR operator. Alright, let's, having this in head, proceed and let's have a look at representations of mask. I'll see you guys next. After this quick introduction to binary math, let's get back to network mask. And we have discussed before that there are three main classes of IP addresses A, B, and C, and there are default masks. Class A has mask 8, Class B has mask 16, and Class C has mask 24. And usually mask is represented in slash notation, like in this example. Here is Class B network 172.16.00/16. 16 is network mask. And recap that every network has actually 4 octets, network part and host part, and network part is defined by network mask. In this example, 16 bits is network part, and the remaining 16 bits is host part. And we could represent this default mask for Class B addresses using either prefix notation, like here, or decimal notation, or binary notation. So, you could see such numbers very often, and you have seen in examples where I have demonstrated you network mask on my computer. It is in decimal format, same as you represent any IP version 4 address. But in this representation, network mask will always have ones at the beginning in the network part and zeros in remaining host part. That's why here we see 255, that is 8 ones in binary format, we have just discussed it. Again 255 all ones on all 8 places, and afterwards all zeros in third octet and all zeros in last fourth octet. That is a network mask in decimal format, same as we represent any IP version 4 IP address. Also, if you represent this mask in binary format, you'll get this sequence of numbers. Again, all ones here in first octet and second octet, and all zeros in third and fourth octets. That's that simple. And again, it is the same mask, /16. And now we need to somehow answer following question. Are both hosts in the same network or not? In this example, we see some hosts with some network masks that are configured on them either statically or dynamically by DHCP. So how we could answer this question? Are two different hosts belong to the same network or not? For that, we need to find first network address for each host and then compare network prefixes, network addresses. And how to do that, let's discuss next. Now you know that a network mask is actually sequence of ones, and afterwards comes sequence of zeros in binary format, and you could represent network mask either in prefix format, or in decimal format, or in binary format. And now let's try to answer the question whether two different IP addresses belong to the same network or not using this example. Let's suppose that there is network with network mask 24 in prefix format, or 255 in first 3 octets and 0 in last octet in decimal format. And now there are 3 different IP addresses, this one, and this one. And if we talk about network mask like this, then those 2 IP addresses will belong to the same network, because they have same network part, that is first 24 bits. And network part in those 2 IP addresses is 192.168.7. And host parts, of course, could be different and are different. And that means again that those 2 IP addresses belong to the same network. If we look at those 2 IP addresses, and keep in mind that network mask is 24 bits, then we could easily say that those 2 IP addresses belong to different networks. Because network parts here are different, and we could actually determine it visually, just by looking at those IP addresses, at this pair and at this pair. And in this example, I have demonstrated you actually Class C IP addresses, and we know that default network mask for Class C IP addresses is 24. Here it is in decimal format, and the network part here is 24 bits, and host part is remaining 8 bits. But how we could actually perform the same operation using binary math, not just visually as we have just done? For that, we need to use AND operator and apply this operator on IP address and mask. And in the result, we will get actually network prefix, and afterwards we need to compare those network prefixes. And let's have a look at another example and do some binary math there. But let's do it after the small pause. Let's now have a look at another example and perform binary math here using AND operator. And I'll demonstrate you how you could determine whether two different hosts belong to the same network or not. And as incoming data, we have two different IP addresses with their masks. So here in this example, PC1 has IP address 172.16.121.35/16. 16 is network mask. And another computer has this IP address 172.16.83.140 with the same mask as this one /16. And now let's answer this question whether those two IP addresses or hosts in the same network or not using binary math. And here is calculation for PC1 and here is calculation for PC2. Let's start with PC1. Here I have written host IP address in binary format. So I have converted decimal IP address into binary format using zeros and ones. And same as in decimal representation, you see here dots between different octets. Afterwards below, you need to write network mask, also in binary format. Network mask here in this PC1 computer is /16. It means that first 16 bits will be set to 1. All remaining bits will be set to zeros. And afterwards we perform AND operation, binary AND operation, on those two numbers, host IP address and network mask. And as a result, we will get this sequence of ones and zeros. In third and fourth octet we have all zeros. In first and the second octet we have same bits as in host IP address here. And basically, as a result of this AND operation, we get network prefix. Here it is in binary format. And when we convert this binary number, actually 4 different binary numbers, to 4 decimal numbers, we get network prefix in decimal format. And for this PC1, it is 172.16.0.0. We have simply converted this number to decimal number. That's it. Now we perform same operation for another host, for another computer, PC2, that has this IP address with this mask. And now host IP address is represented here using binary notation. Afterwards, same network mask that is 16 bits long, all ones here and all zeros here. Then we perform AND operation and get network prefix in binary format. Here it is, 4 different binary sequences. Afterwards, same as in this example, we convert those 4 binary numbers to decimal numbers and get prefix in decimal format 172.16.00. And finally, we need simply compare those two prefixes, this one and this one. If they are the same, actually here you see network addresses, network prefixes, then two hosts belong to the same network. If they are different, then hosts are in different networks. That's that simple. In this very simple example, those two hosts, of course, belong to the same network, and you could even determine it visually just by looking at those IP addresses and their masks. And the binary math has proved that. But in more complicated examples, we will have a look at them next. You will not be able to do that just visually. You need to perform some binary calculations, like in those examples. Alright, so in this example, those two hosts belong to the same network 172.16.0.0/16. Mask is 16. Great. Let's next have a look at another example, and I'll ask you to perform some binary calculations. I'll see you guys next. Alright guys, we have just looked at example where we were able to determine whether two different hosts belong to the same network or not, and in the previous example they belong to the same network actually. Very easy example. And now another example, and actually task for you. Please determine whether those two computers with those IP addresses and corresponding masks belong to the same network or not. Please note that this PC1 has network mask 24 and this one has mask 16. Your goal is to find network prefixes for both computers and compare them. If they are the same, then computers belong to the same network. If not, they are in different networks. Very simple task. I wish you good luck. Alright guys, let's, same as before, do the same action. Calculate network prefix for PC1 and do the same action for PC2. So here is math for PC1. Here is its IP address in binary format. Here is network mask. It is 24, that's why 24 bits here are set to 1 and remaining 8 bits are set to zeros. When we perform AND operation on those two sequences, we get this sequence, and it has zeros in last octet, and first, second, and third octet have the same bits as in host IP address. And when we convert those four binary sequences to decimal format, we get this value: 172, 16, 121, 0. It is network prefix of PC1 network. Next, we perform similar operation for PC2, again its host IP address here, then network mask, it has mask 16, that's why here 16 ones and 16 zeros, and operation will produce those bits. Third and fourth octet have zeros, and resulting network prefix will be 172, 16, 0, 0. And now simply compare this network prefix and this, and of course they are different. And that means that those two hosts belong to different networks. Alright? And basically you could easily tell that just by looking at masks. So here are different masks, that's why those hosts are in different networks. But binary math has proved that. Alright. Next, let's have a look at one more example, and of course, same as in this example, I'll ask you to try to find it out yourself. I'll see you guys next. One more example and one more task for you guys. Now you need to answer the same question: are both hosts in the same network or not, with those addresses and masks. Here is PC1 IP address and mask 26, not 24, not 16, not 8, 26. And here is IP address and mask of PC2, also 26. Good luck! Alright, quick answer: they belong to the same network. But just by looking at those IP addresses, you are not able to determine it, and you're not able to answer this question for sure. That's why you need help of binary math here. So here are calculations for PC1. Same as before, host IP address in binary format, network mask, but now you see that in the same octet, in the last octet, we have partially ones and partially zeros. Because now mask is 26. That's why we need to take two additional bits from the last octet. They also belong to network prefix, to network part. So network part is 26 bits, and host part is 6 bits. And same as before, we perform AND operation, and as a result we get this sequence of ones and zeros. First three octets are the same as in host IP address here, but in the last octet we have set only first two bits to the same bits as in host IP address. They are 0 and 1, because here in network mask we have 1 and 1, and all the remaining bits are zeros. And now when we convert those binary numbers to decimal numbers, we get this network address: 192.168.3.64. 64 is equal to 2 to power of 6, because here at place number 7, when counting from the right, we have 1. All the remaining bits are zeros. That's why here in last octet will be 64. Same math applies for PC2 here, and again here is its IP address, here is network mask, again 26 bits, same as in this example. AND operation, and finally we get same network prefix. Converted to decimal, those addresses are the same. And please notice that Actually, here in this example, we have used subnets, and subnet is part of network with default network mask. And actually here we see IP addresses with default mask 24. It is class C network, but actual mask is 26. And the reason for that is that you could, and it happens very often, split network to different subnetworks. And that's what we will discuss a bit later in this section. I hope that this example is clear. If not, please watch again this lesson in order to fully understand what has just happened. We actually ignore those dots between binary sections and perform bitwise AND operation, bit by bit, and afterwards convert resulting sequences of bits to decimal format. And that's how you could find network prefix knowing IP address and mask of a specific host. Alright, I hope you enjoyed those small examples, and I hope you understand now how to perform binary math using binary numbers that represent IP address and mask, and as a result you get actually network prefix. Next, let's answer the question how you could find out maximum quantity of hosts, devices, that could operate in the same network and have different IP addresses. Let's discuss it next. I hope that the previous examples were helpful for you, and now you understand how to find the network prefix address, knowing IP address and mask of specific host. You need to convert decimal numbers to binary numbers and perform AND operation, and afterwards convert result back to decimal representation. That's that simple. And now, using several examples, let's answer the question how many hosts could be in the same network. And here is an example number 1. And the network is 172.19.0.0. It is a private addresses range with default class B mask 16. It means that 16 is quantity of network bits and 16 is quantity of host bits. And changing those bits, you could actually assign different IP addresses to different devices in this network. And here in this example, network address is 172.19.0.0. It is equal to this prefix. We have discussed that before. Broadcast address is here. It has all ones set in host part, in 3rd and 4th octets, here. And if you want to get information about available IP addresses for assignment to different devices in this network, you need to do following calculation. You need to take 2 to power of 16 in this example, because 16 is quantity of host bits, and afterwards minus 2. And resulting value for this specific network will be 65,534. It is quantity of different host IP addresses that could be used in this specific network, with this specific mask. In this example, of course, this number is very, very large. And I have told you that you should avoid situations when there are many different hosts in the same switched network. And when you use same network, for example, this one, and such many hosts, then of course we will get the same problems as we have discussed before. Large switched domain, large broadcast domain, many broadcasts, and large tables on switches. That's why this network has really a lot of host IP addresses, and it is not recommended to use such, let's say, wide networks with so many available host IP addresses. But again, math here is following. We need to put 2 to power of quantity of host bits, in this example 16, and afterwards minus 2. I haven't told you what is minus 2. But minus 2 is minus this address and minus this address, because those IP addresses couldn't be used for assignment to any host, because this IP address is network address, and this IP address is broadcast network address. Alright? So that's why here we see minus 2. Always minus 2 when you want to find out quantity of host IP addresses. Alright, let's have a look at example number 2 after the small pause. Alright guys, I hope that it is clear how to find out quantity of host IP addresses in any network, knowing network prefix and network mask. And if it is clear, please solve this task yourself. Alright, let's do it together. So quantity of host bits in this example is 8, because network mask is 24. 32 minus 24 is 8. Network address is following: 130.18.31.0. It is equal to network prefix here. Broadcast address will be 130.18.31.255, like that. In host part, we have all ones. In decimal format, it is 255. And now let's find the quantity of available IP addresses using same formula as in previous example. I'll paste this formula here, but here, instead of 16, will be 8, like that. 2 to power of 8, because 8 is quantity of host bits in this specific network. Again, minus 2, and it will be equal to 256 minus 2, or 254, like that. It is quantity of available IP addresses in this specific network with mask 24. Again, we need to deduct network address and broadcast address. You are not able to assign those IP addresses to hosts in this network. That's why formula is following: 2 to power of 8, 8 is quantity of host bits, minus 2. That is equal to 254. And this number is relatively small and it is not too large, and it means that you could easily use networks with 24 mask, for example, for home usage. Because I'm sure that you will not have more than 254 devices in your local area network. It is very large quantity of devices even in terms of large office. So that is how you could find out the quantity of available IP addresses in specific network with mask 24. Alright, also you see that in this example I have taken some public IP addresses range, not private. But it doesn't matter. Calculation is the same for all cases. Alright, next let's have a look at one more example. Alright guys, one more example and one more task for you. Same task: how many hosts in this network? Alright, let's do it together as usually. So quantity of the host bits will be 32 minus 27, and it is equal to 5. So 5 is quantity of host bits here. Network address will be 19.125.31.128, like that. Broadcast address will be 19.125.31. And now what will be here? Here we need to perform some binary math. And basically, let me do that here. And the last octet will be actually 1, 0, 0, 0, 0, 0, 0, 0, like that. It is binary representation of 128, last octet in this network prefix. And now network mask is 27. And that means that 3 first bits here in last octet belong to network part. That's why let me make them in other color, like that. Probably blue will work. And if I want to find broadcast address, I need to place all ones on remaining host bits, 5 host bits. Here is quantity of host bits. That's why here will be 1, 1, 1, 1, 1. And now I need to convert this binary number to decimal number. And actually it will be 255 minus 64, that is 2 to the power of 6, minus 32. And I'll open up calculator. I am too old to do this math in my head, so 255 minus 64 minus 32, like that. And resulting value will be 159. And 159 will be here in last octet, like that. It is broadcast address for this specific network. You don't see here 255. In order to find out the broadcast address, you need to do some binary math, as we have just done together. So here is last octet for broadcast address for this specific network. Let me actually keep this number here, and I'll add arrow like that. So because it is a last octet in a broadcast address. Alright, Actually, calculation of broadcast address for this network was the most challenging part in this example. And now let's finally find out quantity of available IP addresses in this specific network with 27 masks. And formula will be following: 2 to power of 5 minus 2. Let me add here power like that. And result will be 2 to power of 5 is 32 minus 2, so result is 30, like that. That's quantity of available IP addresses that you could assign to different devices in this specific network. Again, minus 2 minus network address, this one, and minus broadcast address that we have just calculated together. Alright, that's how many hosts could be operational simultaneously in this network with this mask 27. I hope you enjoyed those 3 examples, and now you know how to find out quantity of host IP addresses in every network, knowing network prefix and network mask. Next, let's move on to subnetting, and I'll explain you what is subnetting and how to perform subnetting. I'll see you guys in the next lectures. Now it's finally time to discuss what is subnetting. But before starting this discussion, let me quickly remember key points of the previous lectures. First one. There are several classes of the networks, and the main classes are A, B, and C. And the IP addresses in those classes have default masks. Mask 8 for class A, mask 16 for class B, and mask 24 for class C. That is the first key point. Second key point, we know how to find out maximum quantity of the hosts in every network. And before we have seen that in networks with such masks as /8 or /16, such quantity is very large. Also, we know that there are public and private IP addresses, and public IP addresses are actually expensive first, and there are not so much IP addresses available. And using subnetting, we could first get rid of default masks and don't stick to default masks at all. Second, we are able to decrease quantity of the hosts in every network. And third, we could optimize usage of public IP addresses. So, what is subnetting? Subnetting is process of creation of multiple subnetworks from the same single network. And in this example, you see network of class B 172.16.0.0 with default class B mask /16. And in total, there are 32 bits in every IP address, as you already know. And in this example, 16 bits is network part, and 16 bits is host part. And using subnetting, we could borrow several bits from the host part and create, using those bits, additional subnets. And in other words, we could split this single network into multiple networks, called subnetworks. And of course, those subnetworks will have different mask from this one. And subnets of this network could have a mask, for example, /20 or /24 or even /30. That is subnetting. And next, after the small pause, let me answer the question why in greater details. I'll see you guys next. I have just answered the question what is subnetting. And subnetting is process of splitting one single network into multiple subnetworks. And this process actually uses several host bits and adds them to network part. But now let me answer the question why do we need subnetting in greater details. So first reason. Using subnetting, we could decrease quantity of the hosts in each network. Let's have a look at this network. This network is from public IP addresses range. It is class A network, and its default mask is /8. 8 bits is network part and remaining 24 bits is host part. So prefix of this network is 20.0.0.0. And remember that we have calculated quantity of available hosts in every network. And for that we need to bring 2 to power of quantity of host bits and then deduct 2. And for this specific network, quantity of available host IP addresses is here. So 16 million, almost 17 million. This number is very, very huge. And you'll never find such network with so many devices that operate simultaneously. Because again, every single network on network layer of TCP IP model belongs to the same switch domain at layer 2, at data link layer. And it means we have large broadcast domain and large MAC addresses tables. We have discussed it before. Again, same network is same broadcast domain. That's why, again, you'll never find network with so many hosts inside. That's why, using subnetting, we could decrease quantity of the hosts in network. Very simple reason. Second reason is here. Using subnetting, we increase quantity of available networks. What does it mean? If we again look at the same network as before, so 20.0.0.0/8, then this network, it is again public network, could be used only in one place in the world, only in single switched network. For example, here is a router, it has IP address 20.0.0.1, from this network, mask is /8. There are a few devices, for example, this computer, this laptop, and this mobile phone, that have IP addresses from the same network. Notice IP addresses are different, mask is the same. And again, if you use this network somewhere in internet in any place, and if this network is available globally and other routers know about this network with such prefix /8, then you are not allowed and it is not possible to use the same network somewhere else in other places. And that means that if you use just 4 IP addresses here from this network, then all remaining IP addresses, just take this number and deduct 4, will be simply wasted. They will not be used at all. And it is, of course, waste of public IP addresses space. That is expensive and that is very limited. So again, using subnetting, we could increase quantity of available networks. And if we split, for example, this network into, let's say, 8 subnetworks, then we could use parts of this network in multiple places in internet. And that means that subnetting will help us to split this huge network with huge amount of hosts into multiple networks, but with fewer hosts in each. So that is an answer to question why. Why do we need subnetting? And next, let's have a look how subnetting is actually performed on practice. I'll see you guys next. Now you know answers to questions what is subnetting and why do we need subnetting. And now it's time to have a look at one of the examples of subnetting. Let's suppose that we have network 172.16.0.0/16. It is a private network range and this is class B network, and that's why here is default mask /16. And let's suppose that our goal is to create 4 subnets from this single input network. And for that, we need again simply borrow several bits from the host part. 16 bits here is network part, 16 bits here is host part. That's why we take 2 bits from the host part. And using 2 bits, we could create 4 different combinations. Here they are: 00, 01, 10, and 11. And using such borrowing approach, we could extend default mask 16 to mask 18. And this will be mask of every subnet. And every subnet will of course have less host bits than this input network. And quantity of the host bits in every subnetwork will be 16 minus 2, minus quantity of the borrowed bits. In this example, quantity of the host bits in every subnet will be 14. Alright? Let's continue. And here I have actually shown all 4 subnets. Subnet 1, Subnet 2, Subnet 3, and Subnet 4. Network part, first 16 bits, is the same in all subnets. And it matches with this network part in this input network, 172.16. In binary format, these numbers are here. So this number is 172 and this number is 16. Again, this part is the same in all subnets. But next, those parts that represent borrowed bits, so 2 bits were borrowed from the host part, are different in each subnet. That's what makes every subnet actually unique network. And this subnet has 0, 0 on places of those borrowed bits. This subnet has 0, 1, this one has 1, 0, and this last subnet has bits 1, 1 on those places. And again, every subnet will have new mask, not 16, instead 18, because we have borrowed 2 additional bits. Here you see that. And that's why mask for every subnet will be 18. 18 here, 18 here, 18 here, and 18 in last subnet. And that means that, again, quantity of the host bits will be 16 minus 2, or 14. And please notice that we have borrowed 2 additional bits at the beginning of the 3rd octet. And it means that now network part in each subnet actually ends after 18th bit here. Not in the middle of octet, but after 2nd bit in 3rd octet. And that's why when we convert those binary digits to decimal format, we actually convert, for example, 01000000. That is 64 in decimal format. Or we convert number 10 and 6 additional zeros, it is a 3rd octet for subnet 3, to decimal and get 128. And notice that actually there is so-called step between different subnets. So here in 3rd octet you see 0, then we add 64 and get 2nd subnet, add 64 again and get 128, it is subnet 3, and then once again we add 64, it is last subnet. And of course notice that we could create maximum 4 subnets when we borrow 2 bits. And now question to you, how many subnets we are able to create if we borrow, let's say, 4 bits instead of 2? Answer is 2 to power of 4. That is 16. If we borrow 4 bits instead of 2, then we could create 16 different subnets. And in this example, mask for every subnet will be which? 16 plus 4 / 20. Alright? And also please quickly answer the question, what is the maximum quantity of hosts that you could use in every subnet? Answer is very simple, it is 2 to power of 14. 14 is quantity of host bits in every subnet, minus 2, because every subnet will have own network address. Here you see those network addresses basically. And every subnet will have its own broadcast network IP address. And by the way, if you want to do some practice, you could calculate broadcast network addresses for several of those subnets, for example, subnet 2 and subnet 4. Again, if you want to do so. That's how we have subnetted one single network into 4 different networks. And those networks that have non-default masks are usually called simply subnets. And mask is called subnet mask, alright? Because again, here you see class B IP addresses, but mask is not default one. Mask is larger than default mask /16. Great. Next, let's proceed, and after the small pause, I'll demonstrate you how you could perform multiple layer splitting to subnets, or let's say nested splitting. I'll see you guys just in a moment. Now you have knowledge how to perform subnetting. You need to borrow several bits from the host part and create several subnetworks from the main incoming network. And now let me demonstrate you an example of nested subnetting. And in this example, I have taken another input network, for example 126.461.0/24. This network is from public IP addresses range, and this network belongs to class C. And this network is shown here at the top, with default mask 24. Let's say that first we borrow just single bit from the host part and increase mask to 25. So here is this mask. Using just single bit, we could create two subnetworks, because on single place we could put either 0 or 1. And here you see network prefixes for those two new subnetworks. First one will have same prefix as this one, as incoming network, and second one will have 1 at the beginning of the last octet. And this one is 2 to the power of 7, or 128. That's why here, again, you see two prefixes for two subnetworks that were created using one borrowed bit. Here is network mask for every subnetwork. Great. Now you could, for example, split one of those two networks. And let's suppose that we want to split this one. And we take this network as input network, borrow once again just one bit from the host part in this network, and create two subnetworks. And those subnetworks will have now mask 26, 25 plus 1, one borrowed bit. And again, using just one bit, we could create only two subnetworks. That's why here you see only two prefixes. First one has same prefix as this network. In last octet it has 128. And second one will have 1 to 1s set at the beginning of the last fourth octet. And it is 128 plus 64. That is equal to 192. It is a second subnet of this incoming network. And actually, we have just created subnetworks from the subnetwork. And this is subnetwork of this input network with default mask 24. Great. Next, let's assume we want to split into 4 different subnets this network, this actually subnetwork. And in such case, we need to borrow 2 additional bits from the host part. That's why network mask of those subnets will be 26 plus 2, 28. And here we have 4 such kind of subnets. And here you see difference in last octet. First subnetwork, same as in previous cases, has the same prefix as original input subnet, this one. Afterwards, let's say we want to split this one into 2 subnets. Let's borrow 1 more bit. Network part will be increased by 1 more bit, and the subnet mask will be 29 for this and this subnetworks. Next, we split this subnet into 2 additional subnets and borrow 1 more bit from the host part, and resulting mask will be 30. And here is first subnet prefix, and here is second subnet prefix. And finally, let's assume we want to split this subnetwork into 2 subnets, borrowing 1 more bit, and resulting mask will be 31 for this subnet and this subnet. And prefixes are here. But now, please notice that when there is mask 31 in any network, then such network will not have any available IP addresses for assignment to devices like mobile phones or laptops. Because in such case, when mask is 31, we have only 1 host bit. And when you calculate quantity of available host IP addresses, then you simply bring 2 to the power of 1, that is 2, and deduct 2, because 1 is network prefix IP address and second is broadcast network address. And we get actually 0. And that means that such networks with such masks simply don't exist, because there are no usable IP addresses. And that is the reason why largest mask that you may see somewhere is /30. With such mask, you may have 2 IP addresses that you could assign to different devices. And such networks with such masks are very nicely suitable to so-called point-to-point links that connect just 2 devices, like 2 different routers. So in this example, there are 2 different routers, and we actually need only 2 IP addresses, 1 per each side. That's why here we could easily use, for example, this subnetwork with this mask /30 and assign first available IP address, that is 249 in last octet, to this router, and next IP address, that is 250 in last octet, assigned to second router. And of course, 248 will be IP address of network itself, and 251 will be broadcast address for this specific network. And again, there are only two usable IP addresses that you could assign to different devices. Like in this example, we assign to different interfaces of two routers on both sides of this layer 3 link, because it is a link on network layer of the TCP/IP model. That's why we require IP addresses on both sides. Alright? Also here in this table, I have added for your reference information about quantity of subnets and quantity of hosts depending on mask. So if mask is 24, it is actually default mask for this specific network, then you could have only one subnet, this specific subnet. And the quantity of the hosts you could calculate using the same formula as before, 2 to power of 8, where 8 is quantity of host bits for this specific network, minus 2 of course, and resulting quantity of the hosts will be 254. If we have mask 25, then we could have two different subnets, like this one and this one. And in this case, each subnet will have 126 available hosts. 2 to power of 7 minus 2. It is 126. And so on. If mask is /30, then total quantity of subnets that you could create is 64, because we borrow 30 minus 24, 6 bits, and 2 to power of 6 is 64. And each such kind of subnet will have two available IP addresses for assignment to hosts, like I have shown you in this example. Alright? That is subnetting that is called nested subnetting. You could split subnet into other subnets and so on and so forth. And now the most important notice of this lesson. If you have created subnet, for example, let's say this subnet, and you have already used this subnet somewhere on any of the links, and you have assigned IP addresses and masks /26 to some devices, some routers in any part of the network, then you are not allowed to split this subnet into other subnets, like this one, this one, this one, and use them somewhere else, because you have already used this network. Alright? And for example, in this case, when you perform initial splitting to two subnets, to this one and to this one, and let's assume you have used this network somewhere with this mask, you are allowed to use another network and split it to subnets. And for example, you could have this subnet somewhere and those two subnets somewhere. Or you could keep only this network, and use those four subnets. Again, main idea is that subnets can't overlap. Because if they do overlap, then you may get problems with routing, because routers won't be able to determine correctly where they should route specific packet. Because, for example, this network is actually part of this network. It is included in this network. Same applies, for example, to any of those networks and this network. Any of those subnets is part of this input network. This is the main idea behind subnetting. You are not allowed to use network somewhere that you have subnetted, split it into subnets. This is very, very important to keep in mind. Alright, that's all about subnetting, and I don't want to dive deeper, because subnetting it is not the task you will perform every single day. But I wanted to cover this topic here in this course in order to make you understand what is mask and understand that mask could actually be larger than default mask, like /8 or /16 or /24. And if you meet such mask, for example, as 28, 29, don't be afraid. It is simply mask of a specific subnetwork, nothing else. Alright guys, that's all for this lecture, and next let's summarize what we have discussed in this section dedicated to IP addressing and subnetting. Now it's time to summarize what we discussed in this section dedicated to networks, subnets, quantity of the hosts in the network, and subnetting. So network is a set of devices, and it is actually a group of devices, and each network consists of network prefix and network mask. And every Class A, Class B, Class C network has its own default mask, like /8 for Class A, /16 for Class B, and /24 for Class C. But I promise you that in reality, you will never meet such small mask like /8, because in such networks there are too many hosts, and such networks are not usable at all for this reason. That's why you could meet, in most cases, such masks as 24, 26, 28, 30, when we talk about point-to-point link between two different routers. Alright? Also, we have discussed what is actually network address and what is broadcast address. And in each network, there are always two reserved addresses. One is reserved for network address itself, and second one is called broadcast network address. And such address has all ones in the host part. And here is an example of broadcast address for this particular network. Also, we have talked about conversion of decimal numbers to binary numbers and back. And when you want to convert binary number to decimal number, then you need to sum up powers of 2. And when we talk about IP version 4 IP addressing and subnetting and so on and so forth, then you need to remember only powers of 2 up to 7s. That is equal to 128 in decimal format. If you want, you could remember those powers of 2 if you are about to perform conversion of binary numbers to decimal numbers every single day. Alright, we have also talked about binary AND operator and binary OR operator, and they are used when you want to find out network prefix of specific network specific host belongs to, knowing IP address of that host and its mask. Also, we have discussed what is network mask and its representations, and usually it is represented after slash after specific network prefix, like in this example. But of course, you may see such representation when you see, for example, at the settings of IP address and mask on your computer. Also, it is possible to represent mask in binary format, but it is only required when you perform some binary math. In other cases, you could use simply slash notation or this decimal notation, similar to IP addressing notation. We have also performed some sample calculations in order to find out whether two different hosts belong to the same network or not. And for example, in this case, this one, we have found out using binary math that those two hosts are actually in the same network, but without binary math, it is relatively difficult to do. That's why we need to perform AND operation between host IP address and network mask in order to find out what is network prefix. Great. We have also found out how to calculate quantity of the hosts, that is, quantity of available IP addresses in every network, and formula is here. You need to put 2 to power of quantity of the host bits, in this example 16, and deduct 2. 2 stand for one network address and second broadcast address that are always present in every single network or subnetwork. So 2 IP addresses are reserved for that. Also, we have discussed what is subnetting and why it is needed. And subnetting is process of splitting of one single network into multiple subnetworks. And we could do this process by borrowing multiple host bits and adding them to network part. And in such a way, we increase mask and actually decrease quantity of the host bits. And we have seen this example where we have splitted this network into 4 subnetworks. And you see actually 4 resulting network prefixes with new mask /18, because we have borrowed 2 additional bits from the host part in original input network. Also, I have told you what is nested subnetting, and you could perform subnetting as deep as needed, but please keep in mind that the maximum possible usable mask is /30. When mask is /31 or even /32, that is not possible at all, then you will not have any usable IP addresses for assignment to hosts. With mask /30, you are able to have two different IP addresses, and it is pretty nicely suitable mask for point-to-point links, like a link between two different routers, where there are no other devices except those two. Also in this table you may find the quantity of subnets and quantity of the host IP addresses that are available for assignment for different subnets depending on subnet mask. And please notice that main idea behind subnetting is that when you perform subnetting of specific network, then you are not allowed to use this input network somewhere. For example, when you split this input network into other subnetworks, smaller networks, then you are not allowed to assign IP addresses with this mask to any host on any link. Alright? That's again when you perform subnetting. If you don't subnet any network or subnetwork, for example, in this case, we have not split it into subnets this network, this subnet actually, then you are allowed to use this subnet with such mask anywhere you want. For example, on DHCP server, you could create network IP addresses pool with this prefix and this mask, and assign dynamically IP addresses to computers and mobile phones in specific network. Alright, that's all what I wanted to tell you here about subnetting and some logical operations related to decimal and binary numbers, and that's all actually for this section. And in the next section we will discuss what is ARP protocol and why it is needed, and afterwards I'll explain you how communication between two different devices actually happens when on the way there are switches and routers. I'll see you guys in the next section. Have a rest and bye-bye. Welcome to the next section. In this section we will continue discussion of a network layer of TCP/IP model, and specifically we will focus on two protocols, ARP and ICMP. Both those protocols are called supporting protocols because they don't transmit actual end-user data. But using ARP protocol, we could resolve end-user IP address to MAC address of that remote host. And that is very useful when two different hosts want to communicate in local subnetwork, or when specific hosts want to send data to remote host located in other network. Using ICMP you could verify, for example, connectivity between two different hosts, but except that ICMP could also perform other actions. After that, we will discuss how actually two different hosts communicate on network and data link layer if they are located in the same network and if they are located in different networks. Let's get right into it. Let's start by defining what is default router or default gateway. From the previous sections, you know that every host in every network has at least two different settings. First, it is IP address, and second, it is network mask. And using IP address and mask, we could calculate actually network prefix of the network this host belongs to. And for that, we need to perform bitwise AND operation. Also, except those two settings, IP address and mask, every host like mobile phone, computer or server in any network has also one more setting that is called default router or default gateway. What is the purpose of this device? If we look at this picture and look at this router, we could understand that this router actually acts as gateway to internet for those devices located in this local network. And it is fully correct. Default router is used for connection to other networks. All packets to other networks are routed via this default gateway or router. In this example, those hosts have IP addresses from the network 172.16.10/24. It is basically a subnetwork of the class B network, because here you see mask 24. And mask is consistent on all devices, including local area network interface on this router. This router has now two different interfaces, LAN interface and WAN interface, and different IP addresses on different interfaces and of course different MAC addresses. And notice that the LAN IP address on this router is set to 172.16.1.1. And exactly this IP address is set as default gateway or default router on all those hosts in this local network. Of course, this network may have other devices like mobile phones, servers, desktop computers or something else, and all of them will have same default gateway, same router, this one, and IP address will be 172.16.1.1. But now question. How actually those computers understand when they need to send data via router and when they need to send data directly to other host if it is located in the same network? Answer is not very short, and actually purpose of this section is to explain you how different hosts communicate in the same network, local network, and how they communicate if some host wants to send data to other host located somewhere in internet, and how actually this default gateway works in such case. Also, please notice that we could set up a default gateway on end-user devices like laptops or mobile phones using either DHCP protocol dynamically or statically. In such case, if you set up configuration of network card on computer statically, then you need to set up IP address, mask, default gateway, and DNS server. We will get back to DNS a bit later in one of the next sections. In this section, we will focus on network layer and on ARP and ICMP protocol. But for now, let's finalize our definition. Default gateway or router is a device that acts as a gateway to other networks, except local network. Alright, keeping that in mind, let's proceed and let's talk about ARP protocol, and next I'll explain you what it does and how it works. I'll see you guys in the next lecture. Previously we have discussed what is default gateway or router, and this device plays crucial role in communication between different hosts if they are located in different networks. And now it's time to define what is ARP. ARP is Address Resolution Protocol, and its name is pretty self-explanatory. It is used to resolve address. But what address? Let's start with some facts. ARP protocol is network layer protocol, same as IP version 4 protocol. Both those protocols, ARP and IP version 4 or IP version 6, work on network layer of TCP IP model. And ARP protocol has its own ether type, that is in hexadecimal format 0806. And now question of the day. What is ether type number for IP version 4 protocol? Do you remember? IP version 4 protocol has ether type 0800 in hexadecimal format. Next, ARP protocol does not use IP version 4 header. It means that immediately after Ethernet header comes ARP header, actually ARP packet. And there is no IP version 4 header. Please keep in mind that. Next, ARP protocol is used for resolution of destination IP address to destination MAC address when some host wants to send data to another host. Next fact. ARP request is sent from the source host to destination broadcast MAC address all Fs. That is ARP request. ARP response is sent unicast from destination host to source host. Alright, keeping all those facts in mind, let's proceed, and after the small pause I'll explain you how ARP protocol works using diagram. I'll see you guys next. We have just defined what is ARP, and ARP stands for Address Resolution Protocol. And now let's have a look at this diagram and I'll explain you how actually ARP works. Recap that ARP is used when any host wants to get MAC address of some destination host knowing its IP address. So let's have a look at this diagram, same diagram as before, and there are three different computers and one router that acts as default gateway for this local subnetwork, and the hosts have IP addresses that end with .5, .6, .7, and default gateway has IP address that ends with .1. It is its local area network IP address. On outside, it of course has another IP address, and in this example, this IP address is public, from public IP addresses range. Alright, so let's assume that this computer wants to send some data to computer with IP address 172.16.1.7. So its local IP address ends with .5 and the remote host IP address ends with .7. So here is this communication path. And now this host, when it performs encapsulation of data, recap that encapsulation happens when any host prepares data to be sent over wired or wireless media. Now it needs to answer the question, what is the MAC address of the host with IP address 172.16.1.7? That is IP address of this computer. And let's assume that at the moment this computer does not know remote MAC address. And if it does not know MAC address of this computer, it cannot perform encapsulation of packet on data link layer. Because recap that on data link layer we add the source MAC address and destination MAC address. That's why using ARP protocol, this computer sends ARP request. And let's have a look at this request on the next diagram, this one. And here on this diagram I have shown actually two different steps. First step it is ARP request and second step is ARP response. Let's first have a look at ARP request. When this computer wants to get MAC address of destination host, in this example this host, it sends ARP request to broadcast MAC address, all Fs. In this example, all those hosts, those three computers and this router are connected to the same switched network. Here you see this switch. And they have, of course, IP addresses from the same subnetwork, 172.16.1.0/24. It is prefix of the network where all those devices are located. And in this example, when this computer sends a broadcast request to destination broadcast address all Fs, all those hosts, those two computers and default gateway will receive and process this broadcast Ethernet frame. And that means that all those three devices will perform the encapsulation of this ARP request. They will have a look at the Ethernet header. They will see that the destination MAC address is set to all Fs, and that means that they will strip this Ethernet to header, and inside they will find ARP request. And inside of the ARP request, they will find following question actually. What is the MAC address of the host with IP address 172.16.1.7? Now all those three hosts, those two computers and router, will compare IP address in this request with their own IP address, and if they match, then this host will send ARP response. On this diagram, this host has IP address that ends with .7, and this host will send ARP response. And ARP response will be sent unicast from this host to this host. And that means that in this ARP response in Ethernet header will be source MAC address equal to MAC address of this computer, and destination MAC address will be MAC address of this computer, because in this ARP request, this computer has actually put its MAC address as source MAC address in Ethernet to header. Destination MAC address was broadcast, and source MAC address was equal to MAC address of this computer. That's why now this computer knows MAC address it needs to send response to, and the response is sent unicast to this MAC address. And in ARP response, this computer will also put its MAC address, and basically it will say my IP address is 172.16.1.7 and my MAC address is A637 and so on. That's how this two-step communication process looks like. Again, request is sent to broadcast MAC address and response is sent unicast from the host that has matching IP address. And now after this two-step communication process, this computer knows MAC address of destination host, this one. And of course now it is able to perform encapsulation of a packet on data link layer. That is the purpose of ARP protocol. Alright, let's now after the small pause analyze ARP requests and responses using Wireshark. I'll see you guys next. In short, ARP uses two different packets: ARP request that is sent to broadcast MAC address and ARP response that is sent unicast from destination host to source host that has actually sent ARP request. And now let's go to Wireshark and analyze their ARP request and responses. So let's first disable network interface card, in my case this Wi-Fi adapter, so turn Wi-Fi off. And now let me start capture. I'll select Wi-Fi adapter and start capture packets. And now let's enable Wi-Fi adapter back again. Turn Wi-Fi on. Let's wait a bit and here in display filter let's enter ARP like that and let's stop capture. Notice that I already see some ARP requests and responses. And please find now request that goes from your MAC address, in my case it is Apple MAC address, to broadcast destination MAC address. Here it is in my case. And in this ARP request, I see basically question, who has IP address 192.168.1.1? And this IP address is address of my default gateway. Please tell to 192.168.1.182. That is IP address that was assigned via DHCP to this computer. And let's now examine structure of this ARP request that goes to broadcast MAC address from my MAC address. Let's first have a look at those three sections. Frame section actually explains entire frame how it was received using Wireshark. Next comes Ethernet to header, and afterwards comes ARP section. And please notice that there is no IP version 4 header at all. And that's what I have told you before. ARP is separate protocol. It works on network layer of TCP/IP model, and it does not depend on IP version 4 header or protocol. So let's first expand Ethernet to header. Destination MAC address is set to broadcast, all Fs. Source MAC address is equal to MAC address of my network interface card. Here is this MAC address. And either type here is set to value 0x0806 in hexadecimal format. And this number is reserved by ARP protocol. Recap that IP version 4 protocol has its own number 0x0800 instead of 806 like ARP has. And that is indication that next after Ethernet to header comes ARP section. Alright? Let's now minimize Ethernet to section and expand ARP section. And in this section we see following data. We see hardware type, it is Ethernet. Next to it comes protocol type and it is set to IP version 4, and that means that in this particular ARP request we request MAC address by IP version 4 IP address. After that, after some additional fields, there are fields sender MAC address, sender IP address, target MAC address and target IP address. Sender IP address and sender MAC address are set to addresses of this computer. Target MAC address is all zeros, and the reason for that is that we don't know yet destination MAC address, because we have created ARP request in order to get this destination MAC address. But we know target IP address, here it is. It is IP address of default gateway in my case, that ends with .1. That is a structure of ARP request that comes from my computer to broadcast MAC address. Here we see this information in this destination MAC address field. Alright, let's now try to find a response to this ARP request. And response should come from MAC address of wireless router in my case, and here is basically this response that comes immediately after this request. Let's expand first Ethernet 2 section, and here in destination field I see MAC address of my Mac computer. Next I see source MAC address, it is MAC address of local area network interface on wireless router. And also I see type, ARP, same type as was in ARP request. Alright, let's expand the ARP section, and here we see same information as in ARP request, but now those sections are a bit different. Sender MAC address and sender IP address are equal to MAC address and IP address of wireless router default gateway, and the target MAC address and target IP address are equal to MAC address and IP address of my computer. It means that now this ARP response is sent directly to my computer using unicast Ethernet frame. That's why here you see unicast MAC addresses, source and destination. And basically here you see interpretation of this ARP response by Wireshark. And it tells us that IP address 192.168.1.1 is at this MAC address that starts with 98 and ends with D8. And now important notice. At the moment, my computer has this binding of remote IP address and remote MAC address in local ARP cache. And you could always observe which records are located in ARP cache using ARP command in terminal. Let's go to the terminal, and here simply enter ARP-A like that. On Windows, same command is available. And here on the first line I see basically record that was just obtained using ARP protocol. IP address 192.168.1.1 is at this MAC address. And again, this MAC address was received in ARP response from my default gateway. And this IP address with this MAC address is located behind Ethernet 0 interface in my case. Also on the next line I see this strange binding. And basically this binding IP address to MAC address was added to ARP cache automatically by operating system. And here I see strange IP address, this one. And my question to you, what this IP address represents? This IP address is broadcast network address of the network my computer is located in. My computer has mask 24 that was assigned by DHCP server, I have shown you that before in one of the previous sections. And that's why in host part there are all ones, 255 in last octet. And that means that here I see broadcast network address. And if my computer wants to send some data to destination IP address, this one, broadcast network address, then on data link layer my computer will add destination MAC address all Fs. It means that destination MAC address will be broadcast and destination IP address will be broadcast network address, right? Also, there are two additional records in my case, this one, and basically those mappings represent multicast IP addresses. Here is multicast IP address and here is one more multicast IP address. And multicast IP addresses are automatically translated to multicast MAC addresses. And here you see same sections at the beginning of every multicast MAC address. 105E. Alright, that's it about ARP cache on my computer, and basically main binding that I wanted to demonstrate to you is here. It is the IP address of default gateway and here is its MAC address. And that's data that was obtained by ARP protocol in those requests and responses. Alright, that's all for this demonstration, and next let's get back to diagram and I'll explain you how the same action looks like, I mean ARP request and response, if we want to send the data to remote host that is located in other network. I'll see you guys next. Wonderful. We have just explored how ARP protocol works in action, and there are actually two packets, ARP request and ARP response. ARP request is sent to broadcast destination MAC address and ARP response is sent unicast. Now let's have a look at other picture. And now let's assume that this computer with IP address 172.16.1.5 wants to send some data to computer with IP address A.A.A.8. It is IP address of the Google's DNS servers. And this server is located somewhere behind default router. It is located in other network, somewhere in internet. And of course, it has some MAC address. In reality, Google's DNS servers have, of course, different MAC address from this one. It is just imagined MAC address. But again, let's assume that this computer wants to send packet, IP packet, to this destination IP address, A.A.A.8. And now my question to you. Will this computer send ARP request to broadcast MAC address, in this case, or not, asking for MAC address of the computer with IP address A.A.A.8? Answer is no. It will not send ARP request for this IP address. Why? Because this IP address is located in different network. But how this computer will determine whether this IP address is from its local subnetwork or not? Very easily. It will take its network mask, in this example 24. It will apply this network mask to its own IP address, find out network prefix of the network it is located in, and apply same mask to destination IP address, this one, all 8s. And of course, it will find out that network prefix of this IP address is different from network prefix of its own IP address. And that means that this computer will understand in such way that this IP address is in different network. And now another question. How this computer now will handle this packet? How it will send it to this remote server with IP address all 8s? That's actually where default gateway or router comes in. In this case, without any ARP request, this computer will send IP packet dedicated to this server to default router. How it will do this task? Very simple. On data link layer, in destination MAC address field, it will add MAC address of LAN interface of this default gateway. In this example, this MAC address is A0, CD, and so on. Very simple. It means that for all destination IP addresses that are not located in this local subnetwork, all computers will utilize this default gateway. And all what those computers need to do is to ensure that default gateway will receive those packets. And in order to do that, they will need simply send on data link layer every packet to MAC address of this default gateway. Very, very simple. Default gateway will see that destination MAC address in such packets is equal to its own MAC address on this local area interface, performs decapsulation, and afterwards handles IP packet accordingly. It now looks into routing table, finds corresponding routes, and routes packets to other destinations. But that's another story. We need simply to send packets to default gateway if destination is outside of this local subnetwork. Very, very simple. And now it's time to dive into the practice, but before doing that, let me explain you how ICMP protocol works, because we will utilize ICMP protocol in order to generate some IP packets on network layer of TCP/IP model between our computers and remote server with IP address A.A.A.8. I'll see you guys in the next lecture. Now it's time to explain you what is ICMP and how it works. ICMP stands for Internet Control Message Protocol. Please notice word control. This protocol is not used for any end-user data. It is simply control protocol that is used for connection verification and error detection if there are some errors on the way between two different hosts. And in most simple case, there are two ICMP packets called ICMP request and ICMP response. And from one computer you could send ICMP request to remote computer, and if this computer receives this ICMP request, then it sends ICMP response back to original host. Very simple. It is unicast transmission on network layer of TCP/IP model. ICMP request, and next comes ICMP response. Now, after the small pause, let's dive into the practice and have a look at ICMP protocol in action and verify connectivity between our computer and default gateway or default router. I'll see you just in a bit. Let's now go back to Wireshark and analyze ICMP packets. For that, I'll start new capture, continue without saving, go to terminal, and here I'll enter ping 192.168.1.1. It is IP address of my default gateway. Let's press enter. I see some responses. And now let's go back to Wireshark and here stop capture. And in filter field, instead of ARP, I'll type ICMP like that. And I'll see ICMP ping requests and ping replies. And let's have a look at echo ping request, this one, that goes from my IP address to IP address of default gateway, this one. So, it has Ethernet 2 header, it has IP version 4 header, and it has ICMP section. So let's first explore Ethernet 2 section, and here I see source and destination MAC addresses that are unicast MAC addresses. So here is MAC address of my computer and here is MAC address of default gateway. And this MAC address is already in ARP cache. That's why we are able to send some data to default gateway. I could quickly go back to terminal and here type ARP-A like that. And I see this binding here. Here is MAC address of default gateway. Let's go back to Wireshark. Here in Ether type section I see IP version 4 because next to Ethernet 2 header comes IP version 4 header. Let's have a look at this IP version 4 header. And here source IP address is my IP address and destination IP address is IP address of default gateway. Alright, let's now have a look at ICMP section, and here I see type 8. It means that ICMP protocol has different types of messages, and in this example type 8 message was used. It is echo ping request. And here in data section we also find some dummy data that was sent from my computer to remote computer with IP address 192.168.1.1. Alright, also let's have a look now at ping reply, this one, that goes now from IP address 1.1 from default gateway to my IP address that ends with 182. And now in Ethernet 2 section I see reversed MAC addresses. Now destination is my MAC address and source is MAC address of wireless router. In IP version 4 header, IP addresses are also reversed. So source is now IP address of default gateway that I have pinged, and destination is my own IP address. And next to it comes ICMP section, this one. And type here now is 0. 0 stands for echo ping reply. Very, very simple. So type 8 is echo request and type 0 is echo reply. And if my computer receives echo reply, it now knows that destination host is reachable. That's actually what we see here. We see replies and also we see how much time it took for packet to travel to destination and back. So two-way delay. In my case, it is 7 milliseconds for this request, for second request it was 11 milliseconds, and for third request it was around 1 millisecond, very fast. And afterwards I have terminated this process. Alright, that's how those ICMP echo requests and echo replies are used and how we could actually explore those requests using Wireshark. And please notice that ICMP requires IP version 4 header, because ICMP packets could travel far away to remote hosts. And now let's actually restart capture and try to ping remote host with IP address 8.8.8.8, so ping 8.8.8.8 like that. I see responses and now RTT time is a bit larger, it is around 20 milliseconds in all cases. Let me terminate process, Ctrl-C. Let's go back to Wireshark, and now in ICMP filter I see ICMP echo requests to destination IP address equal to all 8s. Here is this IP address in IP version 4 header. And here in ICMP section I see same type, type 8, that stands for echo ping request. And here is a response from remote server. Source is all 8s and destination is my IP address of my local computer. And here in ICMP section I see type 0 echo ping reply. Alright, that's all for this practical section, and now you know that in most basic case, ICMP actually contains two different packets, ICMP echo request and ICMP echo response. Also, please note that ICMP has much more other different types, and ICMP could be used in different scenarios. For example, using ICMP, you could trace route path between two different hosts and find out which routers with which IP addresses are located on the way between two different hosts. Alright, next let's explore how actually ARP works in this case when you want to send some data from source host located in some subnetwork to remote host located in other subnetwork. Let's try that next. We have just explored how ICMP works in action, and there are two different packets, ICMP echo request and ICMP echo reply. And ICMP needs IP version 4 header because those packets travel all over the world between two different hosts. Now let's get back to this diagram where we want to send some data from this IP address that ends with 1.5 to remote IP address 8.8.8.8. And we need to answer the question how ARP protocol is used here and how this computer sends data to this remote IP address and which remote MAC address it utilizes for those packets. And I have told you that in such cases, all computers use destination MAC address equal to MAC address of default gateway. And let's now prove that using Wireshark. Let's go back to Wireshark and here let's click on any ICMP echo request that we sent in previous lecture. For example, this one that is sent from our computer to remote IP address. Let me basically stop capture and let me again reselect, for example, this packet. And let's have a look at Ethernet to header, because we are interested in destination MAC address that our computer adds at data link layer. And please have a look at this destination MAC address. It is equal to MAC address of default gateway. So, in IP version 4 header, in destination IP version 4 field, we see IP address of remote server 8.8.8.8 in this example. Source IP address is IP address of our computer. And on data link layer, source MAC address is of course MAC address of our own computer, and destination MAC address is MAC address of default gateway. And that means that for this particular packet, default gateway will perform decapsulation, strip Ethernet to header, look into IP version 4 header, find corresponding route to this destination IP address, and on outgoing interface, on WAN interface, it will add new Ethernet to header with new pair of MAC addresses, where source MAC address will be MAC address of its outside interface, WAN interface, and destination MAC address will be MAC address of the next router. We will get back to this situation a bit later when I'll explain you how routing works. But that's how default gateway handles all packets that go from local subnetwork to remote networks. Alright? Great, that's all for this section, and next let me quickly summarize what we discussed here. That's all guys for this section, and now let me quickly summarize what we discussed here. Now you know what is default gateway or router. It is a device that acts as a gateway for all outgoing packets that go to other networks except local subnetwork. Also, you know what is ARP protocol. It is network layer protocol and it has its own Ether type, and ARP is used for resolution of IP address to MAC address. So knowing IP address, we could get MAC address. Request is sent to broadcast MAC address and response is sent unicast. Also, we have observed how it works using those diagrams, and when computer wants to send some packet to another computer in the same network, Then it asks for MAC address of this other host. And that is done using broadcast ARP request, this one, that is received by all hosts in the same switched network. In this example, router and those two laptops will receive this broadcast request. And only one will answer to this ARP request, that host that has IP address equal to IP address that you see here in this ARP request. Of course, we could request for MAC address of the IP address that is actually absent in this switched network. In such case, nobody will answer. And we won't be able to send this data to another host, because we don't know which MAC address has this host. But in this example, there is such a host with such IP address, and it responds with its own MAC address. And this response is sent unicast to this laptop. Also, we have observed what happens when any device, any host, wants to send data to another network that does not match to its own local subnetwork. In this example, we send some data to remote server with IP address all 8. In such case, on data link layer, those hosts will encapsulate such packets and send them to MAC address of this default gateway. Very, very simple, and that's how it actually works, and that is the main outcome of this section. For remote packets, data will be sent to default gateway. It will perform decapsulation, and afterwards, on outgoing interface, it will perform again encapsulation with another pair of MAC addresses. Also, we have discussed what is ICMP, and in its most basic variant, it uses two different types of ICMP packets: ICMP echo request and ICMP echo reply or echo response. And using ICMP, we could verify connectivity between two different hosts. And that's what we performed. And we have pinged our default gateway, and we also pinged the remote DNS server of Google. That's all, guys, for this section, and in the next section I want to talk about TCP and UDP, and we will therefore talk about transport layer of TCP/IP model. Let's get right into it in the next section. Hi guys! Previous section was dedicated to ARP and ICMP protocols, and we have discussed how two different hosts communicate on network and data link layers if they are located in the same subnetwork, and how they communicate if those hosts are located in different networks and there are routers between them. Now it's time to move one level up in TCP/IP model, and in this section we will talk about transport layer. And I'll tell you what is the difference between TCP and UDP protocol. I'll tell you what are ports and what is multiplexing and demultiplexing. And of course, we will have a look at the establishment of TCP session using Wireshark, and also you'll understand where and how TCP and UDP protocols are used in modern computer networks. I'll see you guys inside. Over the course of the previous sections, we have talked primarily about data link and network layer of TCP/IP model. And you know that the most popular protocol on data link layer is Ethernet, and there are hardware MAC addresses that are assigned to different network interface cards by manufacturer. And on network layer of TCP/IP model, the most popular protocols are IP version 4 and IP version 6. And there are IP addresses. IP addresses are logical addresses, and they could change. Also, IP addresses could be assigned dynamically using DHCP protocol or statically manually. Now it's time to move one level up to transport layer and explain you its purpose. You know that after transport layer there is application layer. And on application layer there could be different applications like HTTPS, HTTP, SSH, IMAP or SMTP. There are many different applications. And on every single host, for example, server or mobile phone or laptop, different applications could work simultaneously. And they communicate with transport layer, and transport layer communicates with other layers. It means that all those applications need somehow use transport layer. And transport layer is actually used in order to send and receive application data between different hosts. And transport layer could send data either reliably with connection establishment or unreliably without connection establishment. And now it's time to define what is client and what is server, and let's do that next. When we talk about connection establishment between two different hosts on transport layer, there are always two sides of communication. One side establishes connection and another side accepts connection. And side that initiates connection is called client, and another side that accepts initiated connection is called server. And usually our end-user devices like mobile phones or computers are clients, and we establish connections from our computers or mobile phones to remote servers. And on the other hand, hosts that are located in internet and that offer some services like web services, mail services are called servers, and they accept incoming connections. But of course, those servers in internet may also initiate other connections, and in those connections they will act as clients relative to other servers. And of course, you may launch some services on your local computer and also act as server and accept incoming connections. But again, there are in each connection client and server. And in this example, there is laptop that acts as client, and this laptop connects to server that has such applications as HTTPS, HTTP, SSH, IMAP, and SMTP enabled. And this client can connect to any of those applications. And how this server understands which application this client wants to connect to, that's the question to transport layer. And that is a question which we will answer over the course of this section. But again, please notice that usually client initiates connection to the server, and server accepts this incoming connection. And when connection is established, client and server may exchange some data, application data over this connection. And of course, this connection will be a full duplex connection. It means that client may send some data to server and server may send some data to client. When there is no need to send any additional application data, then connection is closed. Alright, that's how client and servers communicate on transport layer of TCP/IP model. And again, please notice that the client may also act as server relative to other clients, and the server may also create another connections and be as client relative to other servers. And other servers may also initiate other connections to other servers, and so on. Alright, that's our clients and servers. And next, let's proceed and let's next talk about ports. I'll see you guys next. We have just defined what is client and what is server. And usually client initiates connections to server. And of course, client may initiate multiple connections to the same server or to the multiple servers if client wants to do so. And if client initiates some connections on transport layer to the server, there will be always two ports in every connection: source port and destination port. In this example, this client initiates connection at transport layer to this server, and in this particular example, source port was chosen as 1027, and protocol here is TCP in this example. We will get back to TCP and UDP a bit later. And destination port for this particular connection is 443, and protocol is also TCP. It means that in this example, client has initiated establishment of the TCP session using this pair of ports. Again, here is source port, it is port of the initiator of the connection, and here is destination port, that is a port that is opened on this server, on server side. Alright? Again, every single connection, either TCP or UDP, has two ports, source port and destination port. And when connection is established, then client sends data to the server from source port 1027 to destination port 443 in this example, and server, when it needs to send some data back to the client, it uses source port 443 and destination port 1027. This pair of ports is present in every single transport layer segment. Great. Next, let's discuss how applications use different ports. Because here we see actually well-known port, one of well-known ports. Let's talk about that next. There are many different applications, and different applications use different protocols. For example, such applications as Google Chrome or Safari or Mozilla Firefox use HTTPS and HTTP protocols in order to retrieve data from remote servers. And more than that, when you load any single web page, there may be multiple connections to different remote servers in order to get different pieces of the same web page. Also, there is such protocol as SSH that is used for communication with remote servers, and with this protocol you could open remote terminal session and manage remote servers. There are such protocols as IMAP Secure or SMTP Secure that are used if you want to send or receive some emails. And those all protocols could be enabled on the same server. And this server needs somehow distinguish which data belongs to which protocol. And that's where ports come in. Each of those protocols are actually well-known standardized protocols, have different default ports. And in this example, you see that HTTPS protocol has default port 443. HTTP, it is an unencrypted version of HTTPS protocol, has default port 80. SSH has port 22. IMAP Secure utilizes port 993. SMTP Secure works over port 465. I intentionally didn't put unsecure versions of those two protocols here, because I highly recommend you to use, whenever possible, only secure versions of protocols, like HTTPS instead of HTTP, FTPS instead of FTP, IMAP-S instead of IMAP, and SMTP-S instead of SMTP. Otherwise, data will be sent simply unencrypted, and if data is unencrypted, then anybody may intercept it when it is sent between two different hosts over internet connections and use this data for some purposes. To summarize, every protocol that works higher than transport layer of TCP/IP model has well-known default port. Of course, those ports may be adjusted if you want to do so, but here you see default ports of some well-known protocols. Great. Next, let's open our web browsers and analyze which connections are established when we want to load some sample web page. I'll see you guys next. Previously, we have discussed that there are well-known protocols like HTTP, HTTPS or SSH with default ports. And every client may initiate multiple connections to different servers using those well-known ports. And servers need to have those ports actually open. And now let's do quick practice activity. Open up your favorite web browser and go to any website you like. I'll open Instagram.com. Now right button click and choose Inspect. Next go to Network tab and here ensure that all is selected. And please also check checkbox Disable Cache. And now refresh page. And you should see bunch of different requests for different pieces of this web page. And web browser downloads such resources as images. For example, on this web page, this image is downloaded. Also, it downloads style sheets and actual HTML page. Great. Let's have a look at this table, and before doing that, right button click on any of the headers of any column, like that, and add also remote address column. If you'll do that, you'll see also a column with remote address and remote port, like this. If you scroll in this column, you'll see that there are actually different connections to different remote addresses. But port in this case is actually everywhere the same, it is 443, it is HTTPS connection, and that's why here I see this lock icon, connection is fully secure, because all resources were downloaded over secure version of HTTP protocol, over HTTPS. But main idea here is that different resources may be downloaded over different connections from different remote servers. For example, here is connection to domain connect.facebook.net and its remote IP address is 31.13.84.4 and again remote port is 443. And some JavaScript script was downloaded via this connection. Here is example of another request, and using this connection to this IP address and port, we have downloaded PNG file. And if you click on image name like that, you'll see actually additional section with different subtabs. In header section, you see request URL, you see remote address again with remote port. Also here you may find status code, that means that this particular resource image file was downloaded correctly from the remote server. Also below there are response headers and request headers. If I click on preview, I could see actual image that was downloaded from remote server. Notice that in this example there is actually placeholder image with black screen here, and different images will be downloaded in order to be shown here over this black rectangle. Alright? So that's how different resources are downloaded from remote servers. And main idea here that I wanted to communicate to you is that we could establish multiple connections to different remote servers in order to download different resources for the single web page. Great. Next, let's proceed, and next I'll explain you what is multiplexing and demultiplexing. I'll see you guys just in a moment. We have just observed that a single application may connect to different remote servers, create different connections, and download multiple resources from different servers. Of course, any client may send some data to remote servers, like when you enter username and password when you log in to your Gmail account. Also, you could open multiple tabs in the single web browser. You could use different mail clients, for example, or you could create different FTP sessions to remote servers. And that means that multiple applications may work simultaneously on the same host, and also multiple services may be enabled on remote servers. And process when different applications communicate over the same transport layer and using same IP address on the same host is called multiplexing. It means that we multiplex multiple data streams into the single stream from the transport layer. And for example, when client connects using different protocols like HTTP, HTTPS, SSH, IMAP-S and SMTPS to remote server that has those services enabled, it creates multiple connections on the transport layer, and it multiplexes all those data streams into the single data stream to this remote server. Of course, if we talk about this particular pair of hosts, about this client and this server, then we can say that on network layer of TCP/IP model, in every single packet, source and destination IP addresses pairs will be exactly the same. But on transport layer, headers will be different, and there will be different ports, different pairs of source port and destination port. And that's how every side of this communication will understand which application or which protocol particular segment, transport layer segment, belongs to. When this client has multiplexed different data streams from different applications and sent over transport layer to this server performs opposite operation. It performs demultiplexing. It means that it takes different segments that it has received on transport layer and directs them to different applications that actually need this data. When it sees that destination port is 443, it directs this traffic to HTTPS application. If there is destination port 22, then SSH protocol will process this data further, and so on. This process is called demultiplexing. Alright? Great. That's all for this definition of multiplexing and demultiplexing. And next, let me define what are different port ranges. Because, for example, here in those connections, you see some strange port numbers like 1030, 1241, and on this side, those ports are fixed. Let me next explain you what those ports here and here mean. So far we have discussed a lot about transport layer of TCP/IP model, and you know what is client and what is server. Also you know that in every single connection on transport layer there is always pair of ports, source port and destination port. Source port is client side port and destination port is server side port. Also, there may be multiple applications and protocols enabled on the same server, and in such case, server performs demultiplexing when it receives multiple segments on the transport layer from the same or from different clients. And after this demultiplexing, data is sent to different protocols or different applications on this server. Now let's discuss different port ranges. There are two fields in every header in every single transport layer segment: source port and destination port. And there are 16 bits in every field: 16 bits for source port and 16 bits for destination port. And using 16 bits, we could create many different port combinations. And basically, port range is from 0 to 65,535. This port is the largest port possible. There are three different ranges of ports. First range, from number 0 in decimal format to number 1023. And this range is called well-known range, and those ports are usually called system ports. And we have observed that such protocols as HTTP, HTTPS, SSH or SMTPS use ports from this well-known range. And that means that ports from this range could be used only by well-known applications that are used almost everywhere in the world. But let's suppose that you create some custom application or custom protocol, and this protocol needs to operate over a specific port. If you need additional port assigned to some custom protocol or application, you could use a range that is next here in this list. This range is called range of registered ports. And you could request specific port or ports from this range from organization called IANA. This organization manages different ports for different custom protocols or applications, and this range is here. Also, there is one more range that is called dynamic or private ports range, and organizations that require some ports to be assigned to their applications or protocols cannot claim ports from this range. This range is not assignable by IANA. And now you may ask me a question. Which port is assigned as source port in any connection when client initiates connection to a remote server? Answer is following. Client selects free port on its local host, but this port must be larger than 1024. It means that the client, when it initiates connection to a remote server, is not allowed to select any port from the well-known range. Those ports must be used only at server side when some services are enabled there, like HTTP or HTTPS service. Alright, that's all for this lecture, where we have discussed different port ranges. And the main range is here, and there are many different well-known protocols that use default ports from this well-known range. And clients are not allowed to use well-known ports as source ports when they initiate connections to remote servers. Also, please keep in mind that every single segment on transport layer of TCP/IP model has two different fields, source port and destination port, and every field is 16 bits long. But usually port numbers are represented in decimal numbers like 80, 443 or 22. It is not common to use binary or hex representation for port numbers. Let's next proceed, and after the small pause I'll explain you what is socket. We have discussed before what is client and what is server. And you know that in every single transport layer connection there is a pair of ports, source port and destination port. And basically on every single server there could be multiple applications or processes launched and up and running. And if we look at this picture, then somehow this server needs to open those ports in order to be able to accept some segments that come from some other clients to this server. And for example, port 443 should be opened here on this server, but port 445, for example, or 446, should be closed. And if someone attempts to send data for one of the closed ports, of course, server will simply reject such segment. And same relates to the client. Client also should somehow identify how it should process returned traffic that goes from server back to client. And that's where network sockets come in. Network socket is a host endpoint that is used for outgoing and incoming data. And it consists of 5 sections, 5 fields. And on every server and client, network sockets must be present if they want to process some data and send them up to application layer of the TCP IP model. Network socket consists of 5 different fields. Transport protocol, it could be either TCP or UDP. Next, source IP address, source port, destination IP address, and destination port. If there is client and server, and client initiates connection to server, then on server side you'll find network socket where source IP address and source port will match to client's IP address and client's source port that was used for initiation of the connection. And destination IP address and destination port match with IP address and port on server side. On client side, for the same connection, there will be also network socket. But source IP address and destination IP address and port pairs will be actually reversed. And on client side, destination IP address and destination port will match with IP address and port on client, and source IP address with source port will actually represent IP address and port of remote server for specific TCP or UDP connection. That is network socket. Now, after the small pause, let me show you some examples of network sockets. Now you know that network socket or internet socket consists of 5 different fields: protocol, source IP address, source port, destination IP address, and destination port. 5 different fields. And on every client or server there may be multiple sockets created at any moment of time. And sockets could be created dynamically and removed dynamically as well. And that depends on which connections are established between pair of client and server. Now let's have a look at some examples of network sockets. Here is first example. Protocol TCP, source IP address is here, source port is here, it is larger than 1024 because, as I have told you before, when client initiates connection to remote server, it chooses any free port that is larger than 1024. Here is destination IP address and here is destination port. In this example, destination port is 443. That is a well-known port and it is used by HTTPS protocol. And the HTTPS protocol is used by such applications as Google Chrome, Safari, Mozilla, and so on. And here also you see status or state of this specific socket. And for TCP, you may find such states as established or listen, for example. In this example, TCP session is considered as established. We will talk about establishment of TCP session a bit later in this section. But here again you see example of the socket that has 5 different fields: protocol, source IP, source port, destination IP, destination port, and also additionally state that is established in this case. And this actually set of different fields fully represents specific socket. And let's assume that some client sends to this server IP packet from this IP address to this IP address. On network layer of TCP IP model, this IP header is stripped, and afterwards server looks into transport layer header. And let's assume that there is protocol TCP, source port, client's port is this one, and destination port is this one, 443. In this case, server finds existing socket, this one, and in such way it understands that server should process this specific IP packet from the client. And basically every single socket is created by specific application or process on the server. And in this case, server will strip transport layer header and send inner data or payload to specific application that has created corresponding process that is responsible for corresponding socket, this one. If, for example, on transport layer of TCP/IP model, this server will find destination port equal to, let's say, 500, and there is no such kind of socket that exists on the server, then such transport layer segment will be silently discarded. Alright, let's have a look at next example of the socket. Here it is. In this socket, destination IP address and destination port are exactly the same as were in this socket. Same destination IP address and same port. But now source IP address and source port are wildcard. It means that this particular socket will accept any segment that comes from any source IP address, from any source port, but protocol, of course, must be TCP. And notice that state of this particular network socket is listen. It means that this socket listens for incoming connections via TCP from any source IP address and any source port. And destination IP address is set to IP address of the server itself, and destination port is 443. That is wildcard socket. Alright, next example. In this example, there is also wildcard destination IP address. It means that this particular network socket will listen to any TCP segments from any source IP address, from any source port, to any of the IP addresses configured on the server. Because server may have multiple network connections, it may have multiple network interface cards. But destination port must be 8080. And we also, at the server side, listen to any incoming segments on transport layer that are sent to any IP address of the server and to the destination port equal to 8080. And finally, last example, here it is. Protocol here is UDP. Source IP address and source port are wildcard. Destination IP address is 48 and destination port is 53. It is a well-known port reserved by DNS protocol. And that's how server may listen to incoming DNS requests that are sent to UDP port 53. These are examples of different sockets. And please notice that, for example, those two sockets may exist on the server simultaneously. What does it mean? It means that multiple connections may be established to the single same port that is open on the server. And let's discuss it in greater details next. On every single client or server may exist multiple sockets. And also you may see wildcard fields like wildcard source IP address or wildcard source port or wildcard destination IP address. But the destination port is usually fixed and it is set to one of well-known ports or ports from other ranges. Now let's discuss how single server may keep multiple sockets and how server may serve multiple clients that connect to the same destination port that is open on specific server. And let's assume that there is a server with IP address 42.16.118. And let's assume that it listens to connections to TCP port 443 and to TCP port 993. Those ports are well-known ports that are used by two applications, HTTPS and IMAP-S secure correspondingly. And those ports are TCP ports. So those two protocols work over TCP. And let's assume that there are several clients, 2 laptops and 1 mobile phone. And for example, this laptop has IP address this one, and now this laptop initiates TCP connection to destination IP address this one and destination port 443. In this case, initial connection will be made to wildcard socket that has source IP address and source port set to wildcard, and state of this socket on the server is listen. When this laptop creates this initial connection, server will create additional new socket with exact source IP address, this one, and exact port, this one. This port was chosen, by the way, by this client randomly, and it is greater than 1024. And destination IP address and destination port will be same as in this wildcard socket that listens to incoming connections. After that, in this separate socket, This client will establish TCP connection, and afterwards, when TCP connection will be established, this client and this server will exchange data over this particular socket. And of course, on client, there will be also new socket created. And in that socket, source IP address port and destination IP address and port pairs will be reversed. So destination IP will be equal to IP of this laptop, and destination port will be equal to this port. Source IP and source port in this particular socket on client side will be equal to those values that are configured on the server side. Great. Next laptop may initiate connection to the same destination port 443, this HTTPS protocol. But now this computer has different IP address and it initiates connection, transport layer connection, from another port. Let's assume this port is 1521. And destination IP and destination port are the same as were in this connection from this laptop. And now again, first TCP segment will be sent to the socket with wildcard source IP and source port. Afterwards, new socket will be created particularly for this specific connection from this specific computer with this IP and this port. And afterwards, when TCP session will be established, data will be sent over this dedicated socket between this laptop and this server. And it means that now there are two different sockets from two different computers that are created on the server side. And destination port for both sockets is the same, 443. But now this server will understand where to send specific data depending on the pair of IP address and port for every single socket. Wonderful. And now let's assume that there is one more device that wants to connect to this server, and now it initiates several connections to the same server. One connection is initiated from source port 1035 to destination port 443. Again, separate socket will be created for this particular connection. And afterwards, this phone creates two more connections to destination port 993. And let's assume different mail applications want to send or download some emails on the same device, on the same phone. And it means that now there will be two different TCP connections, but with different source ports. Here you see different ports from device with the same IP address. Here is the IP address of this mobile phone. And now on the server, for this particular destination port 993, this IMAP S port, there will be three different sockets. First one will be wildcard, with wildcard source IP and source port. Another one for source IP, this one, and source port 1045. And third one for this source IP and this source port 1081. And that's how server will understand where to send different TCP segments, either to this port or to this port, when data is sent from server back to client. And in a similar way, it will understand which socket to use when some segments come from this IP address. It will look into those ports because they are different. And in total, in this particular example, there will be two wildcard sockets for every port, every destination port 443 and 993. There will be three additional sockets for this particular destination port with exact source IP and source port. And also there will be two additional sockets for port 993, because this phone has opened two different TCP connections from different applications, let's say. That's how multiple sockets may exist on the server. And that's how multiple sockets may exist on every client. Next, let me explain you how different processes or different applications may create different sockets with the same destination port. I'll see you guys next. Every client and every server may have multiple sockets created at any moment of time. And those sockets may be either TCP or UDP sockets. But now question, whether two different processors or applications are able to utilize same destination port or source port or not? Answer is yes, they are able to do so if protocols are different. And let's have a look at this example. Let's assume that there is some process that has created this specific socket, where source IP and source port are wildcard, protocol is TCP, destination IP address is one of the IP addresses assigned to server, and destination port is 443. And state of this specific socket is listen. It means that this port is open on the server and it accepts any incoming connections from any source IP and source port. And parallel with this socket, there could be additional socket with the same destination port 443 that was created by another process, process 2 for example. But now protocol here must be UDP, because two different processes are not able to create same wildcard socket as this one. Only single process may be responsible for single socket like this one, with the same destination port. But again, two different processes may create different sockets if protocols here are different. So protocols are different, IP addresses, destination IP addresses are the same, this IP address of the server, and destination ports are also the same here. That is a just single case when destination ports in sockets may be served by different applications, by different processes. Great, that's all for sockets, and next let's dive a bit into the practice and examine which processes are running on our computers and which sockets are created there. Now you have enough knowledge about network sockets, and now is a good time to dive into the practice and examine how network sockets are used on client side and on server side. And now in this first demo, I'll demonstrate you how network sockets are created on client side when you open any new TCP connections to remote servers. And for that, I'll use Windows computer, and here I'll open PowerShell, it is terminal on Windows. And here I'll enter following command. Let me first clear terminal. And I'll enter command netstat. And after entering this command, you'll see in real time information about new connections or updated connections that are created on your local computer. And I already see some TCP connections. Here I see protocol TCP, I see local IP address and local port. I see also foreign IP address and foreign port. Port is basically represented here as a well-known protocol, HTTPS in this example, or HTTP in this example. Also, for every particular socket, because here we see sockets, you see state. For example, state of this particular socket is established. It means that TCP connection was successfully established. Here you see some other states like close wait or time wait. Alright, let's terminate this output, Ctrl-C, and basically that's how you could observe how new sockets are created on client side. If you don't see any connections here after entering netstat command, you could create new connections on your own, for example, open web browser and open any websites. Alright, now let me demonstrate you how you could use netstat command with some additional options in order to see all connections that exist on your computer. And for that, you need to enter following command. Let me first clear terminal, netstat, then space -ANP, here are different options, and afterwards you could enter either TCP or UDP. Let's first have a look at TCP sockets. And I'll see all sockets that are created on this particular computer. Notice that instead of star that represents wildcard IP or port, here you see all zeros, and that is actually wildcard IP. And 0 represents also wildcard port. So here you see wildcard IP, any IP, and wildcard port, any port. And on this line, first line, you see socket that listens to connections to any local IP address, but to TCP port that is equal to 135. Same picture you see here for this socket. This socket listens to connections, TCP connections, to local port 445, again from any foreign IP address and foreign port, and to any of the IP addresses on this computer. Similar picture is represented here in all those sockets. Here on this line you see some socket that was created for specific foreign IP address and foreign port. In my case it is equal to 51.135.186, port is 443. You could of course create additional connections. Let me quickly go to Chrome and create one connection to Instagram.com, one more connection to Facebook.com, and go back to PowerShell and enter same command here, netstart-anp TCP. And I see some additional connections that were just created from my local computer to remote servers. And again, in those created connections, you see some random source ports. Those source ports are different in every single socket. IP address is equal to IP address of this Windows computer. Here it is. And destination IP addresses and ports are different. But ports here are actually everywhere the same. Those ports are 443, except just this single connection where foreign port is 80. That's how you could observe different sockets on client. Also, you could use filtering if you want to filter by specific port or, for example, IP address. On Windows, it is done in following way. Let me clear terminal. And here, please enter following command. Same as before, netstart-anp TCP. Next comes pipe operator like that. Then type select -string. Then -pattern like that. And afterwards enter, for example, 443. And in this case, you'll see result filtered by 443. For example, you could filter by, let's say, IP address. And I'm interested, let's say, in this IP address. Let me copy it, paste here like that, press enter, and I see now output filtered by this particular IP address. Also, you could use filter, for example, by state of specific socket, and I could do something like that. For example, established. I want to have a look only on established TCP connections, and here they are. Great. You could also use netstart command in order to see UDP connections, UDP sockets. Let me clear terminal. And same as before, enter netstart-anp, and here instead of TCP will be UDP, like that. And now I see all sockets for UDP protocol. And notice that here we don't see any state, because UDP is connectionless protocol and doesn't have any states. And we will compare in details TCP and UDP protocol in one of the next lectures and discuss how headers look in TCP and UDP. But now let's focus just on network sockets. So here I see a list of UDP sockets, and here is local IP address and local port. Again, I see some wildcard records, but now, strangely, I see in frame address section stars instead of 4 zeros. It means that PowerShell sometimes displays 4 zeros as a wildcard IP address, sometimes star. Yeah. So in this output we see star here in frame IP address section and star here in frame port section. And state here is again empty. So here is example of UDP socket, and here we see that our local computer, this one, my local computer, actually accepts any UDP segments from any foreign IP addresses and foreign ports to local port 5353. It is UDP port. And local IP address may be any. Also here on this line we see UDP socket that accepts UDP segment only to local host IP address. Remember, we have discussed what is this IP address in one of the previous sections. It is localhost or loopback IP address. And the local port here in this particular socket is 1900. Also on this line you see UDP socket that listens to port 68 at this particular IP address. Great. That's how you could find list of TCP and UDP sockets on Windows computer. Now let me get back to Mac computer and do similar task there. I'll see you guys just in a bit. I have just explained you how you could observe list of sockets on Windows computer, and for that you could use netstart command. Same command is available for Mac OS and other Unix-like systems. And now let's perform similar action here and do some filtering as well for TCP and UDP sockets. So if I'll simply enter netstart command, I'll start process that will show new and updated TCP and UDP sockets. And for example, here I see TCP version 4 socket. It means that in this case IP version 4 IP addresses are used, for example this one. And here I see local IP address and local port, and here I see state of this specific socket. It is established. Here is one more socket, for example this one. It is for IP version 6 protocol, that's why here I see TCP version 6. And source IP address here is IP version 6 IP address, and source port is TCP port. Here is destination IP version 6 address and destination port. State is also established. Let me basically stop this output. And also, if I'll scroll up, at the beginning I'll see actually titles of all columns. Here is protocol, here is local address and local port, and here is foreign address and foreign port. For example, here I see HTTPS ports 443. States are established for all those sessions. Great, that's how you could see updated sockets or new sockets. And now let's enter similar command as we entered on Windows, net stat-anp. And next let's observe first TCP sockets. And I'll see a bunch of sockets that were created on this Mac computer. Let me scroll to the beginning of this output. And I see basically different sockets both for IP version 4 and IP version 6 connections. For example, on this first line, I see fin-wait state for this particular TCP connection, where local address is equal to IP address of my Mac computer. Here is local port, it was chosen randomly. Here is foreign IP address and foreign port. Foreign port in this example is 9418. Here is one more example of socket, here it is, where remote port is 443 and state of this particular socket is established. Also, I could find some wildcard records, for example, this one. TCP version 4, local port is 54750, local IP address could be any IP address among all IP addresses assigned to this particular computer, my local Mac. Remote IP address may be any, and remote port may be also any. And state in this particular socket is listen. It means that we listen, my computer listens, to any TCP connections from any remote IP and remote port to my local port 54750. Similar picture could be seen here, for example, on this line. My computer listens to any TCP connections to local port 5000. Similarly, my computer listens to TCP connections at port 3001, and so on. There are different ports that are currently opened on my computer, and state of all those sockets is listen. Great, now let me demonstrate you how I could apply filtering to this output. And for that I could use grep command. Let me clear terminal, and here after pipe will be grep, and let's filter, for example, by port 443, like that. And I'll see all sockets where port 443 is present somewhere on the line. I could also filter by IP address. Let me, for example, copy this IP address. You could copy any IP address from your sockets. Let me copy it, clear terminal, and grep by IP like that. And I see only single such kind of socket that has such IP address somewhere on the line. So that's how we could observe existing sockets, TCP sockets. And now let's observe UDP sockets. Same command, net stat-anp, and here will be UDP, like that. And now I see, for example, such socket as this one that says that my computer listens to any UDP segments from any remote IP address and remote port, but when destination port, local port on my computer is 138. Great, that's how you could find out UDP sockets that exist on your Mac computer. And now let's do following. Let's, after the small pause, again launch Docker container that will create web server, and afterwards I'll demonstrate you how you could find which process is responsible for a particular socket. It means which socket will send data to which particular process. Let's try that next. I have told you before that every socket is created by a particular process. And process is basically application that is running on specific computer. And now let me show you how you could verify which processes have created the corresponding sockets on macOS and on Windows. So first let me demonstrate you how to do that on macOS. For that I'll use command ls-of, and here will be several options -i, -n and -P like that. And here I'll see following table. Let me scroll to the beginning of it, and here I want to show you first title of those columns. So first column is command that was used in order to start corresponding process. Here is process ID, and it is a numeric number like 226, 451. Next comes user, and finally you see information about socket. For example, here on this line I see that process with ID 451 that was launched using command report D has created socket, TCP socket, that listens at local port 54750. Also, I see similar socket to this one, here on this line, and this is specific socket for particular connection. It means that some remote host, in this example, this host with this IP, has connected to local port 54750. And for that, my computer has created separate socket. Here is wildcard socket, here on this line, and here is specific socket with separate state. State is established in my case, that was created for particular connection. Great, but main idea here is that for every specific socket, there is specific process that is responsible for that socket. And when my computer sees some TCP packets that come to this port, it strips TCP header in transport layer segment and sends inner data to this report D process. And this process is actually application. It works on application layer of TCP IP model, and then this specific application processes corresponding data. Similarly, you see a bunch of other processes, for example, Google process with process ID, this one that listens at port 5353. That is actually UDP port. Please analyze your table as well if you are running Mac. If you are on Windows, you need to use another command. Let me show you that quickly. Let me switch to Windows, and first we need to start PowerShell as administrators. Here let's type PowerShell, and please click here Run as administrator. Click here Yes. Let me make this window full screen, clear terminal. And now let's enter command netstat -anp, same options as we used before, but now I'll add one more option B that will actually show which processes have created corresponding sockets. And next you could type either TCP or UDP, depending on which sockets you want to see here in this list. Let's press enter, and now I see a bunch of different TCP sockets that were created by different processes. And for example, here on this line I see that this particular TCP socket was created by process svc host exe. Also similarly, I could scroll up and find that there are some sockets created by search ui.exe process. That's how you could perform similar action on Windows. Great, let me get back to Mac, and next, after the small pause, let me launch Docker container that will create local web server, and afterwards we will explore how sockets are created when we connect to this local web server. I'll see you guys next. So far you know that on transport layer of TCP IP model, clients and servers create sockets. And sockets actually define how different segments on transport layer of TCP IP model are processed by different processes, because processes are responsible for different sockets. And now using Docker, let's create local web server and launch it on specific TCP port, for example 8080. And afterwards we will create connection to this new server. Let's try that. So for that you need, of course, Docker installed on your computer. Here is Docker desktop that is up and running. If you don't have Docker installed on your computer, please go to docker.com and install it. It is very easy, and it is available both for Mac and for Windows. Alright, so let's run Docker container, and it will be Nginx container. Nginx will actually launch web server and its default port is 80, but I'll expose containers port 80 to external port 8080. It will be port on my local computer. And afterwards I'll try to connect to this local port 8080 using web browser. But first of all, before creation of this new container, let's verify whether this port 8080 is used on our computers or not. And for that, we could use again command net stat -anp. Here will be TCP and next will be grep 8080, like that. And I see empty output, and that means that this port is currently unused, and it is safe to use it for any new service. Alright, let me clear terminal, and here will be docker run. Let's run new container. Here will be options I and T. Next will be one more option -p publish. External port will be 8080, internal port inside of the container will be 80, and next will be name of the image I want to use for this particular container, and name will be nginx, like that. Let's press enter, and container was created. Let's open up new tab, and here in the new tab, let me enter same command as we have entered before, net stat, and verify whether now there are some sockets that listen at port 8080. Net stat -anp TCP pipe grep 8080. And now I see that there is single socket. Protocol here is TCP/4.6, and that means that either IP version 4 or IP version 6 connections may be accepted using this socket. Local port is 8080. IP address here is wildcard, and that means that any of the IP addresses on my local computer could be used for those incoming connections. Remote IP address is wildcard, and remote port is also wildcard. It means that we accept any TCP connections from any remote host if they want to connect to local port 8080. And state of this socket is listen. It means that we listen for any incoming connections. Wonderful. Now let's try to connect, and I'll do that from the same computer where this socket is created. And basically, my computer now will act both as client and as server. Alright? Let me now open up a web browser. I'll open up Safari, and here in Safari I'll open up connection to localhost IP address 127.0.0.1, and here will be port 8080. Port is specified after colon, like that. And now I see response from the nginx web server. It means that connection was established from the client to server, and server has served some content to this Safari web browser. Let's go back to the terminal and verify status of sockets now. And for that I'll repeat same command with grep 8080. And now I see 4 additional sockets. Here they are. And state in all those sockets is established. Let's have a look at this first record. Protocol here is TCP version 4. Local IP address is here, 127.0.0.1, this loopback or local IP address. Local port is 8080. Remote IP address is also loopback IP address, and remote port is here. And this socket is similar to this socket. And basically, it is a server-side socket, this one on the first line. Our server, web server, that was launched using a docker command, has actually received new connection request from IP address this one and port this one, and in such case it created new socket for this particular connection. It is a TCP connection, TCP version 4, because IP version 4 IP addresses are used here, and afterwards our server has established connection with client. And here on the next line you see actually client-side socket, because my computer acts now also as client, and it has initiated connection from its port 56942 to remote port 8080. And that's why here we see those 2 different sockets. Here is server socket and here is client socket. Also, there are 2 additional sockets here and here with similar picture, but now port here is different from this one. And that means that for this single web page, this one, client has initiated 2 different TCP connections in order to retrieve different parts of this web page. I have shown you that for a single web page, client may create multiple connections to different servers. And that's what we see here in this example. Our client has created two different connections, this one and this one. You see that source ports here are different. Yeah? And similarly, server has accepted also two different connections, this one and this one. That's how picture of those sockets look like in this particular example when we created Nginx web server, published it at port 8080 and afterwards connected it using web browser. Alright, let's refresh this view now, and now I see that there are no active connections except this default socket that was created for wildcard connections. And the reason for that is that those TCP connections are not used anymore. Some data was transferred from server to client, and after some timeout, TCP sockets were destroyed. That's that simple. TCP connections were simply closed. If I go back to Safari web browser and refresh page like that, go back here and look again at list of sockets, I'll see again additional sockets. And now I see only single connection because another connection was not used because Safari has cached part of the web page. Great. That's how you could verify connection between client and server, and easily you could launch a web server using Docker. And now let's try to do following. Let's try to start one more process at the same port 8080 and verify whether this start will be successful or not. And let's try that after the small pause. If you followed me along in previous lecture, you have also launched a local web server using Docker, and afterwards you have created a TCP session from client to server and observed sockets that were created both on client side and on server side. In this example, client and server are located at the same computer, local computer. Now let's verify that Docker container is still up and running. For that, you could enter command docker ps. And I see that Nginx container is up, and here is this port forwarding that forwards traffic from external port 8080 on my local computer to internal port 80 inside of the container. And that means that if I go back to Safari and refresh page, I'll still see this page here. Now let's do following. Let's try to create one more process that will try to create same socket at the same local port 8080. That is currently already occupied by this specific Docker process. And I could actually verify quickly which specific process currently uses this socket with port 8080. Let me go back to this command. Here is this wildcard socket. And for that, I could enter command ls-of-i-n-p, and here will be grep 8080, like that. And I see that process com.docker with process ID this one actually uses this particular TCP socket. Okay, now let's create one more container with the same command as before that will try to use same port 8080. Alright, docker run -it-p publish same external port 8080, local port inside of the container 80, and next will be name of the image Nginx. Enter, and now I see error. Error response from daemon, driver failed programming external connectivity to endpoint, because binding for 8080 port failed. Port is already allocated. And that's what I explained you before. There is already socket that listens at port 8080. Here is this socket. And when you try to launch any other process or same process that will try to create same socket with the same local port, you'll definitely get such kind of error. Port is already allocated or occupied. It means that there could be only one wildcard socket that will listen at port 8080. Of course, you could use another free port, for example 8081, very easily. And now Docker container is up and running, and if I go back to Safari and change port here from 8080 to 8081, I'll get same response, welcome to Nginx. Because now there are two different wildcard sockets for different ports, 8080 and 8081. Great. Let me terminate this container, and actually that's all what I wanted to demonstrate you here in this lecture. And main outcome is that you are not able to create two different same sockets with the same protocol and the same local port by different processes or by same process. Alright, that's all for this practical section. Let's go back to this step and terminate this Docker container as well. Let's verify whether there are some Docker containers up and running. There are no containers. And now let's also verify status of sockets with ports 8080 and 8081. Let me go back to this command in history. Filter by 8080 and filter by 8081, and I don't see any processes that utilize sockets with local ports 8080 or 8081. That's all, guys, and next let's finally talk about TCP and UDP. Basically, we talked about those protocols a lot before, but now it's finally time to define differences between those protocols and talk about headers of them. And afterwards we will try in action how those protocols work. Actually, now at the moment you know behavior of TCP and UDP protocols, and you know that there are separate TCP sockets and UDP sockets. And now it's finally time to define differences between TCP and UDP, and I'll explain you where those protocols are used. First of all, let's discuss differences between those protocols. TCP is connection-oriented protocol, and that means that TCP connection must be established. So first there is connection establishment. Next, in established connection, you could transmit and receive some data, and afterwards connection is closed, and there is also a process of closing connection. UDP is connection-less protocol, and there is no connection establishment in UDP. One side simply sends UDP segments to another side, and another side simply accepts those segments. That's it. No connection establishment and no connection teardown. Next difference. TCP is slower in comparison to UDP, and of course it adds more overhead. TCP has larger TCP header, and of course it is slower due to this connection establishment and connection teardown process. UDP is faster because all what UDP needs to do is simply create a segment and send it to another side. No connection establishment, very small overhead, very simple protocol. Next, TCP has flow control and recovery from transmission errors. It means that if during TCP transmission some packet will be lost on the way between two endpoints, TCP will detect it and will try to retransmit same piece of data. And it works using specific sequence numbers. TCP marks every single segment with specific number. And when receiver sees that some number or some numbers are missing, it may request those missing segments from the sender. Also, receiver must acknowledge specific blocks of segments, actually blocks of bytes, that are sent from the sender to receiver. But of course, not every single TCP segment must be acknowledged by recipient. In such case, TCP may become very slow. Instead, there is so-called window size that defines amount of bytes that must be acknowledged before sending next batch of bytes. And this window size may vary during the same TCP connection. And that is called flow control. Again, TCP controls flow and it detects errors, and if there are some errors, then sender may retransmit some requested segments, some missing requested segments. UDP, on the other hand, doesn't have any flow control and it doesn't have any retransmissions. If some packets were lost on the way, then UDP will not retransmit them again. Here are some examples of application layer protocols that utilize TCP at the transport layer. And those protocols are SSH, HTTP or HTTPS, FTP or FTPS, IMAP or IMAP-S. UDP is used by such protocols as DNS, for example, DHCP, NTP, or Skype. Skype is actually an application that utilizes several protocols and it works over different ports, including some UDP ports and some TCP ports. Great, that is a comparison of TCP and UDP protocols, and next, after the small pause, let's talk in details about TCP protocol. Now you know differences between TCP and UDP. And now let's discuss in details TCP. TCP stands for Transmission Control Protocol, and main difference from UDP is that TCP establishes connection at transport layer of TCP/IP model. During this connection, some data is sent and received, and afterwards connection is closed. And here on this diagram you see process of establishment of the TCP connection. And this process is called three-way handshake. Why three? Because there are three different segments that are sent at the beginning of every TCP connection, TCP session. And here in this example we see that some computer with this IP address initializes TCP connection by sending initial TCP request with SYN flag set. SYN stands for synchronization. And it chooses, of course, any random source port that is greater than 1024, and destination port in this example is 443. It is HTTPS port. And here you see remote IP address of remote server. When a server receives such initial TCP segment, of course it needs to have corresponding socket opened. It creates a new socket, of course, for this particular pair of IP address and port, and sends back SYN-ACK segment. SYN-ACK means that there are now two different TCP flags set in TCP header. And those two flags mean that the server actually accepts incoming TCP connection. It has corresponding socket open, and the new socket was created, and now server is able to proceed. Afterwards, when client received this SYN-ACK segment from the server, it finally confirms finalization of TCP session establishment and sends back to the server segment with a single flag set, it is flag ACK, acknowledgement. That is a three-way handshake. Again, first the client sends one segment with one flag, SYN, server responds with two flags, SYN and ACK, and afterwards client sends the ACK flag, and that means that now session transitions to state established. And when you see established in output of the netstat command, it means that in the corresponding TCP session this three-way handshake process was already completed. Also, in similar way, connection teardown works in TCP, but there another flag is used, fin, finalize. Also, it is possible to perform so-called hard reset of TCP connection. For that you could use reset flag, RST. Great. Next, after the small pause, let's have a look at the structure of the TCP header. I'll see you next. Previously we discussed that every single TCP connection starts with three-way handshake, process that actually establishes new TCP connection between client and server. And now let's briefly discuss structure of the TCP header. Similarly to IP version 4 header, it has different fields, and the TCP header starts with source port that is 16 bits long, and next comes destination port. And I have told you before that the source port and destination port pair is present in every single transport layer segment. Next, after the ports comes 32 bits long sequence number, and after sequence number comes acknowledgement number. I have told you that TCP sends data reliably, and somehow we need to mark all pieces of the data that is sent in different TCP segments, and that's where sequence number is used. Every block of bytes that is sent in specific TCP segment is marked and has its own sequence number, and sequence number are incremented in every next TCP segment. Acknowledgement number is used when server or client wants to acknowledge that it has received specific amount of data from another side. And for example, when client sent to the server first 5 bytes of data, server may tell client that it received those 5 bytes and is ready to receive next portion of data. Sequence number and acknowledgement number are present on both sides of the TCP connection. It means that both client and server marks every single TCP segment with specific sequence number, and both client and server acknowledge recipient of the next portion of data. Also in TCP header there is a header length that actually contains length of the TCP header. This field is similar to IP version 4 length that is present in IP version 4 header. Next 4 bits are reserved. Afterwards there are 8 bits that contain different TCP flags, and you already know about such TCP flags as SYN, ACK, FIN and reset. Also, there are other flags that could be present here in this flags field. Afterwards comes window. Window is amount of bytes that are expected to be acknowledged by another side before transmission of the next portion. It means that when window size is very small, then small portions of data must be acknowledged by another side. If window is large, then large portions of data must be acknowledged. Next comes checksum, and remember that on data link layer, FCS field frame check sequence is calculated based on entire frame. Checksum in IP version 4 header is calculated only based on the header fields in the IP version 4 packet. Checksum here in TCP header is calculated based on TCP header, this header, plus TCP data, TCP segment data that is inside of the TCP segment, and plus ephemeral IP version 4 header that consists of source IP, destination IP, and link to protocol, TCP in this case. Remember that every socket for established TCP connections has source IP, source port, and destination IP and destination port. It means that when specific socket is chosen either on client or server to send or receive some TCP segments, we already know which IP addresses will be added after TCP segment. That's why TCP protocol on transport layer of TCP IP model actually adds ephemeral IP version 4 header and includes it in calculation of this checksum. And that is additional layer of security that allows us to send the TCP segments only between two different IP addresses that were used for establishment of TCP connection. Of course, checksum is verified on sender when it receives specific TCP segment, and if checksum in TCP header doesn't match, then such TCP segment will be simply discarded. Also, there is one more field, urgent pointer, that is 16 bits long, but this field is almost never used, but it could be used in order to signalize that a specific portion of data is very important and it must be processed before other segments. Afterwards, there are options that are optional and plus padding that is used to fill remaining part to 32 bits section. That is a TCP header, and most important parts here are source port, destination port, and the flags. Next, after the small pause, let's have a look at establishment of TCP session using Wireshark. I'll see you guys next. Now it's time to practice, and using Wireshark, let's analyze how TCP connection is established, how data is sent over this TCP connection, and how TCP connection is closed or teared down. And in order to find TCP segments related to this specific session, we need to avoid the creation of other TCP sessions in background. So please close your web browser and close any other applications. When you are ready, open up Wireshark and start capture. And now go to terminal, and here using curl command, it is available both on Mac and on Windows in PowerShell, type following: curl https:// and here will be 3 W's, google.com. Using this command, basically, we will download HTML page from google.com. And for that, of course, our computer will establish TCP connection to Google server. Alright, let's press enter. And I see a result. It is basically HTML page that was just downloaded from a remote server. Alright, let's go back to Wireshark and here stop capture. And now our goal is to find the TCP segments. Let's type here in filter field TCP, and we need to find a first TCP segment that has SYN flag set. Let me scroll a bit down, and in my case here is this segment that goes from IP address of my computer to remote IP address, in my case 172.217 and so on. That is the initial segment that has SYN flag set. And immediately after this first initial segment, you see another one that has SYN ACK flag set. And this segment actually comes from a remote server back to my IP address. But let's first analyze this initial TCP segment with SYN flag set. And let's start with Ethernet to header. In destination field, here I see MAC address of wireless router, and we have discussed it before. When you need to send some data to another network, not your local network, then as destination MAC address, your computer will place MAC address of your default gateway. Alright, let's expand also IP version 4 header, and here in IP version 4 header I see protocol TCP that tells us that inside of the IP version 4 packet there is TCP segment, and TCP has its own ID 6. Also I see source IP address that is equal to IP address of my computer and destination IP address that is equal to IP address of remote Google servers. And basically under the hood my computer has resolved this name 3wsgoogle.com to IP address of this server, and we will discuss DNS in greater details in one of the next sections. Let's go back to Wireshark, and here let's now have a look at TCP header. Here I see ports. Source port was chosen as this one, 53963 in my case. Destination port is 443, and the reason for that is that I have used HTTPS protocol here. It is a well-known protocol and its default port is 443. That's why here I see this port in destination port field. Below I see sequence number field, and there are actually two different fields: sequence number relative sequence number and sequence number row. And basically initial sequence number is generated randomly. And here in this field I see initial sequence number, shortly ISN, that was generated by my computer. But for simplicity, Wireshark shows here actually relative sequence number, and it starts always with 0 in first TCP segment that is sent with SYN flag. Alright, next to it below I see header length, it is 44 bytes. Next I see flags, and here in this flags field I see SYN flag set. Here it is. Also, you may observe some other flags like acknowledgement, push, reset, fin, congestion, reserved, and so on. But now there is just single flag set, that is SYN flag. This is first step in three-way handshake of establishment of TCP connection. Next, I see window size value that indicates quantity of bytes that could be sent from sender to receiver before waiting for acknowledgement from recipient. Also, there is checksum that is calculated based on TCP header, TCP data, and also ephemeral IP header. Here it is. Next, there are some options like maximum segment size, no operation, window scale, and so on. Some additional TCP options. And that's it. Inside, there is no data. This particular packet ends at this TCP header. And that is actually correctly, because at the moment of establishment of TCP connection, we don't send any end-user data. Alright, next segment that we will analyze is here, and it is response from remote server. And now this packet is sent from a remote IP address to my IP address of my computer. Here you see this information in IP version 4 header. And next in TCP header, I see source port 443, and that means that server responds from its port 443 to my port, destination port, that was chosen by my computer in this initial TCP connection segment. Next, below I see two flags set in flags field, and those flags are acknowledgement and SYN. It means that now server acknowledgements that it received my first TCP segment, and also it sets SYN flag set that stands for initialization of TCP connection. Also above, there is sequence number that was set by server. Basically, real sequence number is here, and it again has initial sequence number that was generated by server. And the relative sequence number is here, and it is shown by Wireshark for simplicity. Below also you see acknowledgement number, and it means that server acknowledges that it received our first byte of data, and now it is ready to receive next byte of data. Here is a relative acknowledgement number, and here is absolute acknowledgement number that is actually sent in TCP header. Great, that's how response from the server looks like. Below there are some options, and also there is a section called Sequence Acknowledgement Analysis that was added actually by Wireshark, and here you can read that this particular TCP segment is acknowledgement to the segment in frame 48. Here is frame with number 48. And also below you may find round trip time to get acknowledgement for a particular segment. For this segment with frame ID 48. It means that the time that was required to server to respond us back with this SYN ACK was around 26 milliseconds. Because here you see value in seconds. Great. Again, this section was added here by Wireshark. Also, here is additional section called timestamps, and here are two different values. Time since first frame in this particular TCP stream, and this time is equal to this value actually, because this TCP stream started from this TCP segment that was sent from our computer to remote server, and also there is one more value, time since previous frame in this TCP stream. And it is actually equal to this value in this particular TCP segment. Great. Let's proceed, and now let's try to find one more TCP segment that actually finalizes TCP three-way handshake. And it comes immediately after this SYN ACK. And now this TCP segment has only one flag set, it is acknowledgement flag. And this TCP segment goes from my computer to remote server. And here in TCP header, I can observe that there is just single flag set, and it is acknowledgement. All other flags are unset. Great. Also below you may find the same analysis data like sequence acknowledgement analysis and timestamps. Checksum is here, window size is here. And notice that window size was decreased from the initial value. And it means that during three-way handshake, client and server negotiate window size that will be used for further TCP segments. But please notice that this window size may be changed during TCP connection. When, for example, some TCP segments are lost on the way between client and server, then client and server may lower window size. And lower window size tells that acknowledgements will be sent more often. So, that's the end of TCP connection establishment, it is the end of TCP three-way handshake, and after it you may see client hello, that is actually TLS protocol, and the reason for that inside of this TCP connection we negotiate TLS settings, because for this particular connection we used HTTPS protocol that actually utilizes TLS protocol that helps us to encrypt all data that is sent from the client to server and back. That's why here again you see TLS negotiation of the session. By the way, we could do following. We could try to restart capture and request same page but via HTTP protocol, unencrypted version. Let me clear terminal here and perform same operation, but without S like that. Let's go back to Wireshark and restart quickly capture, continue without saving. And now let's press enter here. I got the same page as before. Let's go back to Wireshark, stop capture. And now I need to find the segments related to establishment of the new TCP connection, because in this case new TCP connection was established to remote server. Let's go back to Wireshark, and here let me scroll up. And it seems that here is this session, and yes, here it is. Here is first initial TCP segment with SYN flag set. Here is answer from remote server. Here is acknowledgement from my computer. And notice that now destination port in this particular connection is 80. It is a well-known default reserved port for HTTP protocol, because we have just used HTTP protocol instead of HTTPS. So, here is three-way handshake, and here where it ends. And immediately after establishment of TCP connection, my computer has requested actual HTML web page. And here is this request. And basically now there is IP version 4 header, there is TCP header. In TCP header in the flags section I see two different flags set, push and acknowledgement, and push tells other side that it should push this TCP segment to application layer as fast as possible. So that's are two flags that are set in this particular TCP header, and also inside there is HTTP section. And that means that there is a HTTP request that is sent from client to the server. And basically my computer requests a web page using get HTTP request, and it requests a web page that is located at www.google.com. Below you'll find user agent field, and this field contains information about user agent that has initiated HTTP request. And basically we used CURL utility, that's why you see it here in this string. If we were using, for example, Mozilla Firefox or Google Chrome, then we would see here Mozilla or Chrome or something else. Great, that is a request for data via HTTP protocol. And it means that now over established TCP connection, we exchange application layer data. And on application layer, there is HTTP protocol. Great. Let's now find response from the server. Basically, we could do following. We could click on particular TCP segment, like this one. Next, select follow and click here TCP stream. And now you'll see actually entire communication from the client to server. Here is request from the server, and here is response from the server. And now you see that entire web page was actually sent unencrypted. And here in Wireshark we are able to analyze entire response and request. And the reason for that is that we requested this HTML page using HTTP protocol that doesn't encrypt any data at all. Great, let's close this window and let's try to find actually response from the server. It seems that here is this response, and basically here in Wireshark we see that it has reassembled 12 different TCP segments into one window. And here in HTTP protocol section we see response with status code 200 OK, and also we see some additional fields like cache control, server, set cookie, and so on. And below we see actually HTTP chunk response that was sent in different TCP segments, and you may find here different chunks of data, like for example this piece of data. Great. Also you may again observe every separate TCP segment that was sent either from your computer to the server or back. For example, here I see multiple TCP segments that were sent from remote server to our local computer. And notice that when server responds with some data, it always sends data from source port 80 for this particular connection, because we use HTTP protocol. And destination port is always the same. In my case, it is equal to 54064, because that is a dead port that was used for initial connection, TCP connection, from my computer to remote server. And again, in every single TCP segment, there is sequence number and there is acknowledgement number. Acknowledgement number tells which byte we expect to receive from the server next. And that actually acknowledges that we received all previous bytes. If some bytes in some segments were not received, were lost, then server will actually retransmit lost segments again. And that's how TCP is able to recover from some errors. And during normal transmission of data, you will see usually only single flag set. It is acknowledgement flag. Here you see that on every line, and also you may observe that in flags section. Here it is, just single acknowledgement flag set. Great. Let's now try to find the segments related to finalization of this TCP connection. And here they are. When there is no need in additional data from the server or from the client, then both sides decide to tear down TCP connection. There are some actually timeouts for TCP connection, and in this example we see that my computer has initiated tear down of this TCP connection. This first TCP segment in this finalization three-way handshake comes from my IP to remote IP. And in this particular TCP segment we see now two flags set, fin and ag. Finalize and acknowledge. And except TCP header, there are no other sections, and it means that HTTP protocol already received all data, and in those final TCP requests and responses, there is no user data. So our computer sends FIN-ACK to remote server responds with FIN-ACK as well, 2 flags, and finally my computer has acknowledged finalization of this TCP connection. And now there is just single flag set acknowledgement. And of course there is no end user data. And after that, on both sides, corresponding sockets were removed, both on client side and on server side. So that's how TCP connection was established, how we sent actual data using HTTP protocol over this connection, and basically we were able to decode entire communication and see which data was sent from the server back to our client. And finally, TCP connection was closed using similar to handshake three-way finalization process, this one. Great, that's all for this practical activity. If you want, you can open up another TCP connections and analyze them, but now it's time to go on, and next I'll explain you how UDP protocol works. Now you have strong knowledge about TCP protocol. You know how TCP connection is established, you know how data is sent over established TCP connection, and also you know how TCP connection is finalized. For establishment and finalization of TCP connection, there is special process called three-way handshake or three-way teardown process. And now it's time to talk about UDP protocol. UDP is much more simpler than TCP protocol. It is connectionless and doesn't have any flow control or error detection. And it works, of course, same as TCP on transport layer of the TCP AP model. And also for UDP connections, sockets will be created both on client and server side. But there is no state for those sockets. Sockets are not in listen state or established. There are again no states for UDP sockets. And the sockets simply contain information about source IP, source port, and destination IP and destination port, and of course additionally protocol that is set to UDP. So in UDP, UDP segments are simply sent from the client to server, without any initialization of any connections. So simply we take UDP segment and, for example, from client with this IP, from port let's say 1240, we send UDP segment to remote server with IP address all 8s and to destination port 53. It is a well-known port, it is used by DNS protocol. And server, when it receives such UDP segment, it responds from source port 53 to remote port 1240. And of course, if this pair of hosts, this computer and this server, need to exchange some additional UDP segments, they will be sent between the same pair of ports. Client will send the data from this port to this port, and server will respond back from this port to this client's port. But usually DNS request-response process takes just 2 UDP segments, one UDP segment for request and another UDP segment for response from the server back to client. Now let's have a look at structure of the UDP header. It is simple as this. It contains only 4 fields. Source port 16 bits long, destination port 16 bits long, length and checksum. Source port and destination port are exactly the same fields as were used in TCP header. They represent source port that is located on client side and destination port that is located on server side. Next comes length, and it is length of entire UDP segment including header, so header plus data that is encapsulated inside, and checksum that is calculated in similar way as it is calculated for TCP header. In calculation of checksum, UDP actually uses this UDP header plus UDP data plus ephemeral IP header that will be added later at the network layer of TCP AP model. That is UDP header. It is 8 bytes long, very short, no other flags, no options, nothing. Just 4 simple fields. That is UDP. It is connectionless, it does not check connection for any errors, it doesn't recover from lost UDP segments, nothing. It is very fast and it is utilized for fast transmission of data between 2 different hosts. Now let's go back to Wireshark and analyze some UDP segments. Now you know that UDP is a very simple protocol and its header contains just 4 fields: source port, destination port, length and checksum. And basically UDP itself does not guarantee delivery of data on transport layer of TCP IP model. And it means that application layer should be responsible for retransmissions if, for example, some segments were lost on the way between two endpoints. But some applications, for example real-time applications, don't need to retransmit data, because if some part of the sentence that was said by one of the members of the conference was lost somewhere on the way, then there is no need to resend this word later, because conversation goes on and other people start talking. That's why in real-time applications UDP is the best choice, and it is better than TCP. So let's now, using Wireshark, find some UDP segments and analyze them. Let's start a new capture, and now I'll disable my network interface card like that and enable it back again. And now in display filter I'll enter UDP, and I should see some UDP segments. Let's stop capture, and basically instead of UDP, let's find here DHCP protocol packets, because DHCP basically works over UDP. And now I see here DHCP request, because now my computer has received the IP address from DHCP server, and let's observe structure of this DHCP request. Same as before, there is Ethernet 2 header, there is IP version 4 header, and inside of this IP version 4 header there is link to inner protocol, and it is UDP in this case. Let's have a look at UDP header, user datagram protocol. And there are just 4 fields: source port, that is 68, destination port is 67, length is the entire length of UDP header plus data, and here is checksum. And that's basically all fields that are included in header of UDP protocol. And inside of it there is some application data, and in this particular case application layer protocol is DHCP, and here inside you may find DHCP request. And again, please notice source port and destination port. Source port is 68 and destination port is 67. Let's now observe response from the server. Here is basically this response that is sent from source port 67 to destination port 68. Here is again length and checksum, and inside of it there is DHCP related data. DHCP acknowledgement in this particular example. That's how UDP protocol is used by DHCP. Why UDP is used here? Because there is no need to establish TCP connection between client and server just for one request for IP address. That's why UDP is better choice in this particular example. Also, UDP is used for DNS requests. Let's here instead of DHCP type DNS like that, and you should see some DNS queries. For example, let's click at any of them. I'll click on this one. And here again I see UDP protocol. In IP version 4 header I see link to UDP in protocol field. And next I see UDP protocol that again has just 4 fields. Source port is random port that was chosen in my case like this. Destination port is 53, it is DNS port. Length and checksum. And inside there is DNS related data, and DNS is application layer protocol. And response from remote DNS server goes from port 53 to my local port that I used in DNS request. And again, there is some application data inside. It is actual DNS response from DNS server. That's how UDP is used for DNS. Again, reason why it is used here is that for DNS we usually send one DNS request and receive DNS reply from the server. No need to establish TCP session, no need to tear down it. Because if we were using here TCP instead of UDP, then we would have at least 6 different TCP segments. 3 segments for establishment of the connection, and 3 segments for tear down of the TCP connection. And at least 1 segment would be needed for actual data that should be sent from the server back to client. So in total, 7 different TCP segments. That is a waste of network bandwidth and a waste of time, basically, because it takes more time than just send UDP request and receive response. Just 2 different UDP segments. That's why for some protocols it is better to use UDP instead of TCP. It is faster and it doesn't require any establishment of the connection. That's all for UDP, and next let's summarize what we discussed in this section. That's the end of the section dedicated to transport layer of TCP/IP model, and now let me briefly summarize what we discussed here. I explained you that the transport layer is used for transmission of actual data that comes from different applications. Because on every single host there may be multiple applications that are running in parallel. And that's why somehow we need to multiplex data that comes from multiple applications at transport layer and network layer and send them using same IP address of the same host. And the same applies to remote host, for example, server, that receives data on network layer and transport layer of TCP/IP model from multiple remote hosts, and it somehow needs to decide which process or application should process corresponding TCP segment or UDP segment. And there are multiple protocols such as HTTPS, HTTP, SSH, IMAP or others that work on application layer of TCP/IP model, and of course you could name those protocols applications because they work on application layer of TCP/IP model. But it's more common to name applications some graphical user interface applications that have some interaction with user, like web browser or mail client. But those applications may utilize different protocols that all work on application layer of TCP/IP model. For example, web browser could utilize HTTPS, HTTP, and DNS protocols. Again, all of them work on application layer of TCP/IP model, and all of them require transmission of segments on transport layer of TCP/IP model. Next, we discussed what is the difference between client and server, and actually single difference is that client initiates connection on transport layer of TCP/IP model. That's single difference. Server itself may also initialize other connections to other servers and act as client. When client initiates connection to remote server, it usually chooses a random source port greater than 1024. Also, we discussed that in every single transport layer connection must be source port and destination port. And communication in scope of the single connection happens between this pair of ports. Server sends data from this port to this port, and client sends its data from this port to this port. Also, we discussed what is the difference between application ports, because every single protocol that works on application layer of TCP/IP model has well-known port, such as 443 that is reserved by HTTPS protocol or 22 that is reserved by SSH protocol. Also, there are many custom applications that use not well-known port, instead they use ports from higher range. And if you create some custom application, you may also request some port from organization called IANA, and that's where different port ranges come in. Here is a well-known ports range, and in this range there are different well-known applications that have designated ports like 80, 443, 22, and so on. And usually when client initiates connection to remote server, it does not choose source port from this well-known range. Instead, it chooses port either from this range or from this range. But of course, corresponding port must be available on the client when it chooses it for particular TCP or UDP connection. Great, these are port ranges, and next we discussed what are network sockets. A network socket is actually endpoint on client or server that is used for communication with other host. And the network socket consists of 5 different sections: transport protocol, TCP or UDP, source IP address and source port, and you could name them also IP address of a foreign host and port of foreign host, remote host. Destination IP address and destination ports are local to the host where a socket is created, and you could name them either destination or local. Also, please notice that TCP network sockets also have additionally state, and state may be, for example, listen or established. And here are some examples of network sockets. Here is a dedicated socket for particular connection between specific IP address and the server, and this socket is created for specific pair of ports as well, and here is state established. Here is wildcard example of the network socket where foreign IP address and port may be any. And usually such kind of sockets are located in state listen, and they are waiting for some segments that come from remote clients. And when any request comes from particular client, then server creates such kind of socket for every specific TCP connection. Also, server may listen to requests to any of the IP addresses assigned to its network adapters, and in such case, network socket will look like this. Destination IP address or local IP address will be wildcard as well. And finally, here is an example of UDP network socket that doesn't have any state. And in this particular example, we are listening for UDP segments that come from any remote IP address and any remote port to local port 53 and to local IP address all 8. Of course, we could change this IP address to star and make it wildcard like that. In such case, we will listen to requests on any network interface card on the server. These are examples of network sockets. Also, I explained you that on single server, different sockets may exist with the same local port. And there may be wildcard sockets and specific sockets for every single connection that is established by any remote client, for example, this laptop or this laptop. In such case, there will be 2 wildcard sockets for every port, this one, and also additionally to that, there will be 3 dedicated sockets for those 3 clients that were connected to port 443, and additionally to that, there are 2 additional sockets, dedicated sockets for this connection and this connection that were made from this phone to destination port 993, this IMAP secure port. Also, I have told you that 2 different processors cannot create 2 exactly the same sockets. It is not possible. But it is possible to create such kind of sockets by different processors if protocols are different. It means that TCP and UDP ports belong to different sections of the sockets table, and it is possible to listen to exactly the same port by different protocols, TCP and UDP. And in this example, 2 different processors listen to the same port. But here port is listened by TCP protocol and here by UDP. Also, we discussed difference between TCP and UDP. TCP is a reliable protocol, it is connection-oriented. First of all, TCP establishes connection, and after transmission of data, TCP connection is closed, and there is also a 3-way process that actually closes TCP connection. UDP, on the other hand, is much faster than TCP. It doesn't require any establishment of the connection, and UDP segments are simply sent from one side to another. That's simple as that. And UDP is more convenient for such protocols as DNS and DHCP, and we explored that in Wireshark, because those protocols actually use just single request and single response, no need for establishment of TCP connection. But TCP again is more reliable, it allows to detect some errors and resend some segments that were lost on the way, and also it has much more additional options and fields. And now let's proceed to the next section, and in the next one we will return back to network layer of TCP/IP model and discuss how routers perform routing operations, how they build routing tables, and how they route packets from source to destination. I'll see you guys in the next section. In the previous section we have discussed transport layer of TCP/IP model, and now you know what is the purpose of transport layer and how it utilizes multiplexing and demultiplexing in order to deliver data of different applications. And now it's time to move back to network layer of TCP/IP model and discuss what is a router and what is the purpose of router. In this section, I'll tell you what is routing protocol and how routers perform their operations. Also, you'll learn what is CIDR, that stands for classless interdomain routing, and also I'll explain you what is route summarization or aggregation. Also, you'll learn what is the difference between IGP protocols and EGP protocols. IGP stands for Interior Gateway Protocol and EGP stands for Exterior Gateway Protocol. Also, I'll explain you in details how packet travels from one computer to another if those 2 computers are located in different networks and if there are routers on the way. Let's get right into it. Over the course of the previous sections, we discussed what is the difference between switches and routers, and you know that switches operate on data link layer of the TCP model, and their single responsibility is to switch frames as fast as possible, and the responsibility of routers is to forward IP packets from source to destination. And as you already know, IP protocol is connectionless protocol, and that means that every single IP packet or IP datagram is treated separately. And this means that multiple packets that are sent from one host to another host may travel via different paths in the computer network. And main devices that take decisions how to route this or that packet are routers. Routers operate on network layer of TCP model, and main responsibility of every router is to route packets from source to destination. And for that, routers need to have routing tables, because inside of the routing tables, routers may find paths to different destination networks. On this sample diagram, you see several routers that are interconnected with each other. For example, there are connections between R1 and R2, between R2 and R4 routers, but there is no connection between, for example, R2 and R3. And there are some local networks that are located behind every router, for example, this network here or this network here. And the idea here is that those routers must somehow exchange information about those networks that are located behind them in order to be able to route packets, for example, from this network to this network, or from this network to this network, and so on. And for that, those routers need somehow exchange information about their routes. For example, router R1 needs somehow inform R2, R4, and R3 about this network, and so on. And that could be done using dynamic routing protocols, or that could be done statically. For example, on router R3, you could add routes to this network, or this network manually, and those routes will be called static routes. And every single router here will have its own routing table. And this routing table will be utilized for making routing decisions. For every single IP packet, every router will look into this routing table and find corresponding route. If there is no matching route, then IP packet will be silently dropped. That is the responsibility of every router. First, build routing table, and second, route IP packets. That's all. Great. Next, let's have a look at the structure of routing table. Routers are very powerful network devices that could process millions of IP packets per single second. And every single router not just examines IP packet. Every router performs some operations with IP header. For example, it verifies header checksum. Also, when packet is sent to next router, router decrements TTL field in the IP header, and also it recalculates checksum. Every router makes routing decisions using routing table. This routing table is one, it is global, and it contains all routes that router has discovered. Here is an example of routing table. In the first column you see network and mask. It means that in routing table every single network prefix is added along with its mask. For example, we see such route as 10.2.10.0 with mask 24. It is basically a subnet of the class A network 10.0.0.0/8. Also, on next line, you see another subnet of the same network, but now network mask is 20. It means that 20 bits is network part and remaining 12 bits is host part. Another network is 172.16.0.0/12. And basically, it is aggregated route. We will talk about aggregated routes later in this section. Again, routing table has network and mask for every single record. Next comes type of specific network. And here you see such types as C, that stands for connected, O, that stands for OSPF, and S, that stands for static. It means that single routing table may have multiple routes of different types. Also, all networks except connected networks have next router, that is actually IP address of the next router that knows about this particular network. And basically, you could add routes either manually, like for example this static route, or dynamically via dynamic routing protocol, like this route, because here you see O, that stands for OSPF, that is Dynamic Routing Protocol. For connected routes, you will not find next router, because connected route is the route where a router has one of its interfaces. And also you'll find here interface of the router that should be used for routing of the outgoing IP packet. For example, for this particular route, interface is gigabit 0/1. For next route, outgoing interface is gigabit 0/3. And for last one, outgoing interface is gigabit 1/5. It means that when router will find matching route, for example this one, it will utilize this interface in order to send packet to next router. Also, please notice order of those routes. Order is very, very important. Less significant routes in the routing table are always placed below more significant routes. What does it mean? Please notice here network masks. First route here in routing table has mask 24. And this mask is larger than this mask 20. And this mask is larger than this mask 12. And this means that this route is more specific than this or this. Let me adjust this route and explain you difference. For example, let's say that here instead of this route will be route, let me add here 0 instead of 192, and here will be 2. But mask I'll keep 20. So what is the difference between this network and mask and this network and mask? Answer is very simple. This network is actually subnetwork of this network. This network is more specific than this one. And it means that if we place this route above this one and swap them, let me do that quickly like that, then this first route will be utilized for all destination IP packets that go to this network 10.2.0.0/20. And this route will be never used. Because again, all IP packets will be routed using this route that is less specific than this one. That's why we need to go back to this order in order to be able to utilize this destination route if IP packet goes, for example, to IP address 10.2.10.5, for example. But if destination IP address is, let's say, 10.2.7.1, then router will skip this route and will utilize next one that is more wide than this specific route. But order must be exactly like this. Alright, that is routing table. And please notice that routing tables may be very, very large, especially at the so-called backbone routers that are utilized by large internet service providers. And those routers may keep millions of routes in their routing tables. And again, every route consists of network and mask. Next comes type. Next comes next router, that is IP address of the next hop router, and interface, that is local interface of the router, which has specific routing record in routing table. Wonderful. Now let's have a look at this very simple scenario where we have only single router and when there are two different networks attached to this router. And I'll explain you how routing table looks like on this router and how this router performs actually its routing decisions. I'll see you guys in the next lecture. Now let's explore the most simple example when a router routes packet between two different networks. In this example, there is a router here and it has two different interfaces, gigabit 0/0 and gigabit 0/1. This interface is connected to network 172.16.3.0/24, and this interface is connected to another network 192.168.1.0/24. And what it means connected? It means that those interfaces have IP address and mask configured on each of them, and those interfaces are up. It means that they are physically functioning, and that means that this router and this switch are actually interconnected with each other, on this link and on this link with this switch. And also it means that Ethernet frames are able to travel between this switch and this router and between this switch and this router. It means that those interfaces are again up and operational. And in such case, in the routing table, you'll automatically see those two routes. route to this network, and route to this network. And those routes will be marked as connected routes or directly connected routes. And this means that directly connected routes are routes to the network where routers' own interfaces, like interface gigabit 0/0 or gigabit 0/1, are attached, have IP addresses, masks, and are up. It means that on gigabit 0/0, router may have following configuration setup. IP address is, for example, 172.16.3.1 with mask 24, because mask is mandatory part of configuration of any interface on the router. And also such interfaces as gigabit interface like here or here must have MAC addresses. And in this example, here is MAC address on gigabit 0/0 interface. Also here you may find information about the configuration of gigabit 0/1 interface on the router. Its IP address belongs to this network, and in this sample diagram it is 192.168.1.1. Mask is 24 in this example, and here is MAC address on this interface gigabit 0/1. And of course this MAC address and this MAC address are different, because those interfaces on the router are different. And again, in the routing table there will be two different routes, route to this network and route to this network. You don't need to do anything in order to add those routes to the routing table. They will be added automatically by router itself as soon as you bring up those interfaces. Great. Also here you may find switches, switch here in this network and switch here in this network, and also there are a couple of laptops here in this network and couple of laptops in this network. And of course these laptops have IP addresses from this network 172.16.3.0, and in this example this laptop has IP address that ends with .5, and this laptop has another IP that ends with .7. They have different MAC addresses, of course, and similar picture can be found here on this side, in this network. IP addresses are different, but belong to the same network. All hosts, this laptop, and this router on its interface gigabit 0/1 have a consistent mask. Mask is 24. Also, those hosts have default gateway that points to IP address of this router, of its IP address configured on gigabit 0/1 interface. This IP address. Similar picture is here. This laptop and this laptop in this network also have default gateway, and IP address of the default gateway is 172.16.3.1. It is IP address of the gigabit 0/0 interface on this router. Great. That is sample diagram in most simple case when a router has just two interfaces connected to different networks. And next, let's discuss in details what is done when specific host, for example this one, wants to send IP packet to the host in another network, let's suppose this host. And I'll explain you step by step what happens on host itself, what happens on switch, what happens on router, what happens on this switch, and how finally packet arrives to its destination host, for example this one. Let's start discussion next. Let's now have a look at this simplified diagram, and using this diagram I'll explain you how end-to-end communication between two different hosts in two different networks happens if there is a router in between. Here I left only one host, PC1, here in this network. Another PC2 is located in different network. IP address of PC1 is 172.16.3.7, and IP address of PC2 is 192.168.1.15. Mask is 24 for this network and 24 for this network. And let's assume that the host from this IP address wants to send IP packet to host with IP address from this network. So here is direction of flow of IP packet. Also there is still switch, it is switch 1, and here I added also interfaces. Fast Ethernet 0/3 interface is connected to this particular laptop. On other side, switch 1 has interface gigabit 1/1 that is connected to gigabit 0/0 interface on router side. And similar picture is here. Here is also switch 2, and its Fast Ethernet 0/5 interface is connected to PC2, Gigabit 1/2 interface is connected to gigabit 0/1 interface on router side, and the router still has the same IP addresses on both sides as before, and also here near every interface you may find MAC address of corresponding interface. MAC address of gigabit 0/0, MAC address of gigabit 0/1, here is MAC address of PC2, and here is MAC address of PC1. Also, here is routing table on this router. It has only two directly connected routes: route to this network and route to this network. And of course, this network is accessible via gigabit 0/0 interface. And this network is accessible via gigabit 0/1 interface of this router. And now let's discuss step by step what happens when this PC1 wants to send IP packet to PC2. And basically here are a bunch of different steps. I added 21 steps here, and let's actually break them down, and let's start from the very first one, but let's do that after the small pause. Okay, scope is defined, and our goal now is to explore in details what happens when PC1 sends IP packet to PC2. And let's start with the first step, and the first step is that when PC1 needs to determine whether destination IP address belongs to its local network or not. And we have discussed before how it is done actually. PC1 takes remote IP, this one, and applies to it its local network mask 24. And as a result, it will get the prefix 192.168.1.0. Next, it will perform the same action with its own IP address, and as a result, it will get the prefix 172.16.3.0/24. Next, it will compare those two prefixes. They are different. And that's how PC1 will understand that remote IP address, this one, belongs to different network. Next step. PC1 on network layer adds IP header. Source IP address will be its own IP address 172.16.3.7, and destination IP address will be 192.168.1.15. Also, it adds time to live, and let's suppose it adds initial TTL 64. Also, it calculates header checksum, and afterwards this PC1 needs to add header at data link layer, and that is the next step. Step number 3. Before adding data link header, PC1 checks whether MAC address of the default gateway is present there or not. But why it checks for MAC address of default gateway? Answer is very simple. When host, for example PC1, wants to send data to another network, it will always send it to its default gateway, to its MAC address. And we have discussed that before when we discussed ARP protocol in details. It means that now PC1 is looking for MAC address IP address binding for default gateway in its local ARP cache. If this record is absent there, PC1 needs to send ARP request. It is sent broadcast, and in this request, PC1 will ask for MAC address of the host that has IP address equal to IP address of the default gateway. Default gateway for this PC1 is equal to IP address of this router on its gigabit 0/0 interface, this 172.16.3.1. Okay, let's suppose that now this PC1 has ARP record, and it knows what is the MAC address of the default gateway. And here comes next step, step number 4. On data link layer, PC1 adds Ethernet header. Source MAC address will be equal to its own MAC address, this one, and destination MAC address will be equal to MAC address of the default gateway. And this destination MAC address it will take from the ARP cache table. And afterwards, PC1 sends Ethernet frame over physical media, over this physical link that connects PC1 and switch 1. Great. Next step. Switch 1 receives Ethernet frame on its local interface fast Ethernet 0/3 that connects switch 1 and PC1. Switch 1 at data link layer verifies frame check sequence that was added by PC1 at the end of the Ethernet frame. If it is correct, it accepts this Ethernet frame. Then it checks MAC address table in order to find where destination MAC address is located. Destination MAC address in this frame recap is MAC address of gigabit 0/0 interface on the router. And let's assume that switch 1 already knows about this MAC address, and this destination MAC address is mapped to gigabit 1/1 interface on switch 1. And in such case, switch 1 will send such Ethernet frame only to gigabit 1/1 interface, because it knows where destination MAC address is located. But before doing that, switch 1 needs to ensure that MAC address of the PC1, source MAC address, is present in the MAC address table of switch 1. That's why here is next step. Switch 1 adds MAC address of PC1 to its MAC address table. And let's assume that it is a first frame that is sent by this PC1. And switch 1 didn't know about MAC address of PC1 before. That's why switch 1 adds MAC address of PC1 and maps it to port fast Ethernet 0/3. And if PC2 or any other host will send some frames to this MAC address of PC1, then switch 1 will already know about location of this MAC address. It will know that it is located behind fast Ethernet 0/3 interface. Great, that was step number 6. Next step, step number 7. Switch 1 sends frame to its gigabit 1/1 interface towards this router. Switch 1 will not modify frame at all. It will keep same frame check sequence that was added by PC1, and also it will not modify frame header. That means that switch 1 will switch such frame very fast, and usually it happens on wire speed, hardware speed. Wonderful. Next step, step number 8. Router will receive such Ethernet frame on its gigabit 0/0 interface. On data link layer, it verifies frame check sequence. If it is correct, then router accepts this frame. If it is incorrect, frame will be discarded. Also, next, router verifies destination MAC address field in this Ethernet frame. And it sees their MAC address that is equal to MAC address of its own gigabit 0/0 interface. Interface where this router has received this frame from. And in such case, router will perform decapsulation of the Ethernet frame, remove this header, remove frame check sequence, and send inner IP version 4 packet to processing on the next layer of the TCP/IP model, on network layer. And on network layer, first it will verify header checksum in the IP version 4 header and verify TTL. If TTL is 0, then packet will be discarded. But in our case, TTL is equal to 64. That is initial TTL that was added in the IP version 4 header by PC1. That is step number 9. Now let's make a short break and proceed with step number 10 in the next lecture. So far, IP packet that travels from PC1 to PC2 has reached gigabit 0/0 interface on the router. And router has performed decapsulation of this packet on data link layer. And now it looks into network layer header, into IP version 4 header. And there it sees destination IP address 192.168.1.15. That is IP address of PC2. And this IP address doesn't match with any of the IP addresses configured on router itself. And in such case, router understands that it must resend this IP packet further. And in such case, router verifies routing table. And it checks all routes one by one. First, it checks this route. And how it checks it? It takes destination IP address, in our case 192.168.1.15, applies to it mask from routing table record. For this record, it is 24. It produces result 192.168.1.0. It verifies this result with this prefix in this routing table record, 172.16.3.0. Those prefixes are different. That's why this routing table record is skipped. And router goes to next one, to this one. It performs same action. It takes mask 24, applies to destination IP address. As a result, we get same prefix as you see here. And that means that router has found matching route in its routing table. It sees that this route is directly connected. And that means that router's interface belongs to this network. And that means that destination host must be in this directly connected network. This network is attached to gigabit 0/1 on the router. And it means that the outgoing interface for this particular IP packet will be gigabit 0/1. Great. Next step. Now router should determine destination MAC address of the host in this directly connected network. And let's assume that the router does not yet know about MAC address of PC2. Record with IP address 1.15 is absent in its local ARP cache. In this case, router sends broadcast ARP request via gigabit 0/1 interface, asking for MAC address of the host that has IP address that ends with .15. This ARP request will be sent at switch 2 to all destination ports except gigabit 1/2, because there's a broadcast Ethernet frame. And it means that PC2 will receive such ARP request. It will see that requested IP address matches with its own IP address, and it will respond back to the router unicast, saying that, hey, here is my MAC address. Alright, now router has in its ARP cache mapping MAC address to IP address of this PC2 host. Next step, step number 14. On the network layer, router decrements TTL field by 1. It was 64 when PC1 sent this initial IP packet, and now it will be 33. Afterwards, router needs to calculate new header checksum, because header was changed, there is new TTL. It adds new header checksum in the IP version 4 header, and afterwards router needs to encapsulate this IP version 4 packet further, and it means that it needs to add Ethernet header on the data link layer. And that is next step, step number 15. On data link layer, router adds new Ethernet header. Please note, router adds brand new Ethernet header. It differs from the header that was in this frame between PC1 and router's gigabit 0/0 interface. Here, source MAC address was MAC address of the PC1, and destination MAC address was MAC address of the gigabit 0/0 interface on the router. Here, after router has processed this IP version 4 packet, it will add brand new data link header. And their source MAC address will be equal to MAC address of the router's gigabit 0/1 interface, this outgoing interface that was found here in routing table. And destination MAC address will be MAC address of the PC2. And this MAC address we received at the router via ARP request. It is located in router's ARP cache. So again, source MAC address is MAC address of the router, this one, and destination MAC address is MAC address of the PC2. Next step, step number 16. Now router finally sends Ethernet frame via its gigabit 0/1 interface. And this interface was chosen based on routing table at the router. And now this IP packet has IP version 4 header, and also it has Ethernet header with source and destination MAC addresses. Next step will be processing of this frame at switch 2, but let's again make a small break and proceed after it. Alright, router has just processed the packet that goes from PC1 to PC2, and during this processing, router has stripped initial data link header, and afterwards, before sending it out via gigabit 0/1, it added brand new Ethernet header, and it has sent this frame via this interface towards switch 2. Next step, step number 17. Switch 2 receives this Ethernet frame from the router on its own gigabit 1/2 interface. Afterwards, as every switch does, it verifies frame check sequence. If it is correct, it accepts this frame, and now it looks into MAC address table in order to find destination MAC address. And let's assume that there were already some frames that were sent from PC2 towards switch, and switch 2 knows about location of destination MAC address, and it knows that it is located behind Fast Ethernet 0/5 interface. In such case, switch 2 will send this frame unicast to Fast Ethernet 0/5 interface. Next step. Switch 2 will add source MAC address that is equal to MAC address of the router's gigabit 0/1 interface to its MAC address table, if this MAC address is absent there at the moment. If it is absent, it will map it to port gigabit 1/2, where switch 2 has received frame from. Next step, step number 19. Switch 2 will send Ethernet frame to interface Fast Ethernet 0/5. That's where it has found destination MAC address. Again, it checked its MAC address table to find destination MAC address on one of the previous steps. So, switch 2 sends Ethernet frame to Fast Ethernet 0/5, and finally, after this action, PC2 receives Ethernet frame on its own physical interface. And that is step number 20. PC2 verifies on data link layer frame check sequence in Ethernet frame. If it is correct, it accepts this frame. Next, it verifies destination MAC address in this frame, and it sees that it is equal to its own MAC address, this one. And it means that PC2 needs to perform decapsulation. It removes Ethernet 2 header and sends packet for further processing to network layer of TCP/IP model. On network layer, PC2 first verifies header checksum. Also, it verifies TTL. It is 63. It is acceptable. And finally, PC2 looks into destination IP address field, and it sees there its own IP address. And in such case, it performs decapsulation on network layer of TCP/IP model. It removes IP version for header and sends transport layer segment to transport layer for further processing. And there could be either TCP or UDP segment, depending on which transport layer protocol PC1 used when it decided to send some data from PC1 to PC2. And notice that this inner transport layer header remained unchanged, and nobody touched it, neither switch 1, nor router, nor switch 2. And of course, inner data that is encapsulated inside of the transport layer segment was also remained untouched. Switch 1 and switch 2 examined only Ethernet headers, they didn't look into IP header. Router examined and changed data link layer header, and it also examined IP version 4 header. And it also changed this header because it needed to decrement TTL and therefore recalculate header checksum. That's what happens end-to-end when PC1 wants to send data to PC2. And in total, there are 21 steps. Of course, I have grouped some steps together in order to simplify it a bit, but that's an end-to-end process. And that's how router performed the routing table lookup in order to find matching route that was used in order to route packet to its destination. Answer from PC2 to PC1 will be sent in similar way, via switch 2, via router, via switch 1, until it reaches PC1. I hope you enjoyed this explanation, and next, let's quickly summarize what happens in this end-to-end transmission. I'll see you guys next. Let's now briefly summarize how transmission took place when PC1 decided to send IP packet to PC2. Generally speaking, switch 1 and switch 2 performed only lookups in their MAC addresses tables, without modification of Ethernet frame. Router has stripped initial Ethernet header. Afterwards, it looked into IP version 4 header. It found out that it should resend this IP version 4 packet to destination. It found corresponding route in its routing table, this one, and added brand new data link header before sending IP packet via its gigabit 0/1 interface. And finally, PC2 received this IP packet that comes from PC1. For returning IP packet that PC2 will potentially decide to send to PC1, network devices will perform similar actions as we just discussed. That's all for this example, and basically there could be multiple routers on the way between two different hosts. Here is the most simple example, just with one router. And next, let's start discussion of the routing when there are multiple routers. I'll see you guys next. We have just discussed the most simple scenario just with single router. Though in every single network, either local area network or wide area network, there are usually much more than single router. And let's have a look at example with three routers that are interconnected with each other. For simplicity, I have omitted switches here, and I didn't show also MAC addresses. Let's examine this picture. Here are sender and receiver, and there are three routers between them: R1, R2, and R3. And there are also four different networks. Here is first network 10.23.7.0/24. Here is one more network, it has mask 30, and this network is 10.5.1.0. Here is one more network 10.17.2.0/30, and one more network 10.9.2.0/24. And now in this example, every single router R1, R2, and R3 will have their own separate routing tables. And now every single IP packet that will go via every router will be handled by every separate router independently. And every router will make routing decisions on its own, using its own routing table. And of course now, for example, R2 needs somehow add into its routing table routes to this network and this network, because those networks are not directly connected to this R2 router. Same applies to R1 when we talk about this network and this network. Those networks are remote networks for R1. And again, somehow R1 needs to add those remote networks to its local routing table. And for R3, we need to insert routes this one and this one into its routing table as well. And only when all routers have complete routing tables, this laptop will be able to send IP packets to receiver, and receiver will be able to respond with some other IP packets. And basically, every router in this case will have four routes in their routing tables. If we are not talking about connection to internet, because now at the moment of this diagram we see actually local area network that contains several network devices and several computers, but this local area network is not connected to internet. Alright, let's proceed, and next I'll explain you what is the difference between static and dynamic routes. I'll see you next. Usually every router has multiple interfaces, and the routers are interconnected with each other. And routers need somehow exchange information about their directly connected routes between them. And after exchange, they will be able to route packets from one network to another via different routers. And for that, you could use either static or dynamic routes. Static route is a route that is added into routing table manually. It means that you access router, for example, using either web user interface or command line and add route manually. Or those routes could be obtained dynamically. For that, you need to set up corresponding dynamic routing protocol, and routers will automatically perform exchange of the routes and fill routing tables with dynamic routes. In this example, there are three different routes in routing table for some router. This first route is connected route, and you already know what is that. It means that this interface belongs to this particular network with this mask on this router. Next route has type S, that stands for static, and that means that the administrator of this router has manually added this route into the routing table, and manually he has defined that this particular network 172.16.00/12 is accessible via next hop router with IP address 10.7.6.2. It was done again manually. Another route, this one, has type O, that usually stands for OSPF. OSPF is Dynamic Routing Protocol, and using OSPF you could perform automatic exchange of the routes between different routers. And in this particular example, this route was received from one of the neighbors of this router, and this neighbor has this IP address via OSPF. That's why this route appeared actually in this routing table automatically using OSPF Dynamic Routing Protocol. It means that in the same routing table there could be both static routes and dynamic routes, and of course connected routes. And the reason for that is that routing table, as I have told you before, is located in the router's memory. It is global, and it is used for making all routing decisions. And you could fill routing table with different routes using different sources of those routes, either manually or dynamically or using connected routes. That is the difference between static and dynamic routes. Of course, OSPF is just one example of the dynamic routing protocols. We will discuss some other protocols a bit later in this section. For now, you need to keep in mind that there are static routes and dynamic routes. Static routes are added usually by administrator manually, using web user interface or command line at specific router, and dynamic routes are obtained dynamically via dynamic routing protocols. Wonderful. Next, let me explain you what is default route and how it looks like in the routing table. Now you know difference between static and dynamic routes. And now let me explain you what is default route and how it looks like. Let's examine this routing table. In this routing table there is one connected route, this one. There is one more static route to this network. And there is also one more static route, here you see type S. And in network prefix part, you see here all zeros. And mask is 0 as well. In this particular example, this route is available via next hop router with IP 10.1.5.3. And local interface is gigabit 0/3. And here you see actually default route. Route that looks like this, 4 zeros as network prefix and 0 as mask, is default route. And usually default routes are marked in the routing tables, for example, using asterisks. And one more important notice is that default routes are always located at the end of the routing tables. Always at the end. Usually there is just a single default route. But for example, if specific router has two different connections to two different providers, one is primary and another one is secondary, it is possible to have two different default routes in the routing table. But it is also possible to set up them in such a way that if first ISP provider is available, then only first route via this ISP will be in routing table. And if this ISP fails, then automatically another default route will appear in the routing table, and another ISP2, that is backup ISP, will be utilized for all outgoing traffic to internet. But what is the purpose actually of default route? Purpose is to catch all packets that didn't match to any of the previous routes in the routing table. For example, if destination IP address in specific IP packet is, let's say, 5.5.5.5, then this route will not match. This route will not match as well. And if router will finally compare destination IP address with this route, it will always match for any destination IP address. Why it is so, let's discuss after the small pause. We have just defined what is default route. And default route is very similar to default gateway setting on laptop or mobile phone or any other end-user device. But it actually points to specific next hop router. It means that any router could choose any neighbor router as default router for all outgoing packets that didn't match to any other routes in the routing table. And also please keep in mind that default route is always the last route in the routing table. Sometimes it is called also last resort route, and it means that it will be used only in case when no other previous routes matched. But now let me explain you how actually a router chooses this specific default route when it needs to route IP packet to a specific destination IP address. In this example, here is destination IP address 172.16.121.35. Here could be any other IP address. I have chosen this one for this particular example. And recap how router performs its routing decisions. It takes destination IP address, this one in this example, and applies network mask of specific route in the routing table. What does it mean applies? It means that router performs binary AND operation, bitwise binary AND operation, between destination IP address in IP packet and route mask. And it gets some prefix. And afterwards it compares this prefix with network prefix in the routing table. And if we take mask 0, then in binary format it will be represented as all zeros on all 32 places. And of course, bitwise AND operation will always produce all zeros here, independent of the destination IP address here in this field. And this means that we always will get 4 zeros as prefix as a result of this bitwise AND operation. And of course, when a router will compare this prefix 4 zeros and this prefix 4 zeros in the routing table, they will always match. That's how router actually chooses default route. And that's why this route must be located at the end of the routing table. If you place such a route, for example, at the beginning of the routing table, then all packets will be routed using this route, because it will always match for any destination IP address. And that's again an example how router performs decision whether this route matches or not. And again, it matches for all destination IP addresses. That is default route, and please keep in mind that it must be located at the end of the routing table. And usually this default route is added statically. Also, it is possible to inject this default route into routing table dynamically. For example, when a router obtains IP address on one of its interfaces via DHCP from neighbor router. In that case, you could say that you want that default route will be inserted automatically into the routing table. Great. Keeping this in mind, let's proceed, and next I'll explain you how different routers may utilize default routes. I'll see you guys next. Let's now get back to the diagram that we have discussed before, but now I've added routing tables at each of the routers, R1, R2 and R3, and basically all those routers are located in the same local area network. And also I've added the connection to internet, and there is just a single router R2 that is connected to internet. And for that it utilizes one of the routers of the internet service provider. And in this particular example, here you see connection that has public IP addresses on both ends, like 7.3.10.2 on R2 side and 7.3.10.1 on ISP router side. All other networks, this one, this one, this one, and this one, are located in the local area network. And we have discussed before that in local area networks, usually private IP address space are utilized. And basically all these networks, this one, this one, this one, and this one, are subnetworks of the class A network 10.0.0.0/8. And let's assume that now we have two different goals. First one, allow communication between different devices in the local area network. It means that routers R1, R2, and R3 should be able to route packets, for example, from this laptop to this laptop and back. And second goal is that we want to provide internet access to all devices in this local area network. And as outgoing point to internet, we should use R2 router. And for that, we could utilize default routes on all routers. And now let me explain you how routing tables on all three routers may look like if we want to achieve both goals. Again, first goal is to make all IP packets inside of the local area network routable on all routers. And second goal is to provide access to internet to all devices here in this local area network. Let's first explore routing table on R2, this router that stands in the middle of this local area network. And this R2 router has connection to internet. And basically this R2 router has now three different interfaces. And that means that it will have three different directly connected routes. And that's what we see here at the beginning of its routing table. Here is first network 10.5.1.0/30. It is directly connected network, because router's interface this one is located in this network. Here is another network 10.17.2.0/30. It is also directly connected. And here is one more directly connected route, this one. That's interface that connects R2 to ISP router. That's all for directly connected routes on this R2 router. And now this R2 router needs somehow get information about this network and this network that are located behind R2 and R3 correspondingly. And for example, we could add routes to those two networks statically on R2. I have omitted types of the routes in routing tables for simplicity, but let's assume that those two routes, this one and this one, to this network and to this network, were added statically on R2, and next hop routers are defined as 10.5.1.1 for this network. It is IP address of R1 on this side. And for this network, 10.9.2.0, this network, next hop router is R3, and its IP address 10.17.2.2, this one. And now we actually have all routes for local area network. Those two networks are directly attached to this R2 router, and those two networks were added, for example, statically. Of course, we could utilize dynamic routing protocol, but for this very simple case, we don't need it. We could simply utilize static routes. And finally, there is default route for 0/0 that points to IP address 7.3.10.1. It is IP address of the ISP router. And this means that R2, in such a way, will be capable of routing of all IP packets that don't go to any of inner local area network routes to internet via ISP's router, using this default route. And how default route is used, we have discussed in the previous lecture. That's picture of the routing table on R2 router. In summary, three directly connected routes, this one, and this one. Next, it has two static routes to this network and to this network. And finally, it has one more default route that points to internet ISP router. That's all for routing table on R2. Let's have a look now at the routing table on R1, for example. It is very simple. This router has just two directly connected routes, because it has just two interfaces with IP addresses, this one with this IP and this one with this IP. And that's why here we see those two routes as directly connected routes. And except that, we could simply add default route for all remaining destination IP addresses that will point us to this IP address, that is IP address of the R2 router. That's that simple. We don't need to add, for example, this network as separate static route on R2, because there is no need for that. R1 has only single connection to all other routes, to this route, and to all other routes in internet. That's why we could simply add just one default route that will point to next hop router, that is R2 in this case. Very, very simple. No need to launch any dynamic routing protocol, no need to add some other static routes, just single default static route. That's that simple. And in total, on R1, there will be just three different routes. Two directly connected routes, this one, and one default route that points to R2 router. And finally, here is routing table of R3. It is very similar to routing table of R1. It has just two directly connected routes to this network and to this network. And also it has default route, but now next hop in this default route is 10.17.2.1. It is IP address of the R2 on this interface that faces R3 router. But now question to you. What happens if, for example, instead of this next hop IP address, I will add this IP address that is configured on other side of the R2 router, on other interface? Answer is very simple. In such case, if you attempt to add such kind of static route on R3, it will not even appear in the routing table. The reason for that is that R3 does not know anything about network this IP address belongs to. First, before adding any route to the routing table, router verifies accessibility of the next hop IP address of the next hop router. And if next hop IP address will be 10.5.1.2, this IP address is not available using any other routes in the routing table, neither using this route nor using this route. That's why such static route with this next hop IP cannot be added to the routing table of R3. But if you add statically default route 40/0 and next hop IP address will be 10.17.2.1, router will find out that this IP address belongs to the directly connected network, this one, and there is already a route to this network. And it means that this next hop router is accessible from R3. And it means that this default route will be successfully added to the routing table. And now I slowly moved to the process of making routing decisions when routers already built their routing tables. And basically, different routes in the routing tables may be dependent on each other. And router may perform multiple routing table lookups while making a decision just on one single IP packet. But before moving on with this discussion, let's finalize what we discussed here in this lecture. On all those three routers, we use default routes in order to access different networks. On R1 and R3, it is enough to add the default routes that point to R2. That's that simple. On R2, we need to add the static routes to this network and to this network. Of course, we could obtain them also dynamically, but I have told you that in such scenario, there is no need to launch any dynamic routing protocol on R1 and R3, because they have only single uplink to all remaining networks. That's why on R2, we could simply add static routes to this network and to this network, except that on R2, we added the default route to all remaining networks in Internet. And all other networks are accessible via ISP router, this one. And that's why we see here this default route. Great. I hope you understand this picture. It is again very simple and it has just three different routers. And now let's proceed, and next, using same diagram, I explain you how routers make their routing decisions and how they perform routing table lookups. I'll see you guys just in a minute. We've successfully built routing tables on all three routers here in this local area network. And using those routing tables, all routes inside of the local area network are accessible, as well as all routes in Internet. And now, using several sample destination IP addresses, explore how routers perform their routing decisions. First example, let's assume that this sender with this IP sends IP packet to destination IP address 10.5.1.2, to IP address of R2 router. In this case, R1 will look up its routing table, and it will find first matching route, this one, because it will take destination IP address 10.5.1.2, apply this mask 30. As a result, it will get 10.5.1.0, compare this result with this prefix in routing table, and it will find match. And it sees that this route is directly connected, and there is also interface in routing table. I omitted them for simplicity here. But now R1 will choose this outgoing interface and will route packet to that outgoing interface. And in such case, R2 will finally receive this IP packet. It will see that destination IP address in IP header is equal to its own IP address 10.5.1.2. It will strip IP version for header, and afterwards it will process inner payload, depending on what is there, either TCP or UDP or something else. That's first example. Next example. Let's assume that now this laptop sends IP packet to IP address of this laptop. IP address is 10.9.2.10. First, R1 makes its routing decision. It takes this destination IP address 10.9.2.10, compares it to first route. It applies this mask 30 to destination IP address. By applying mask 30 to this destination IP address, it will get 10.9.2.8 if I'm right. It will compare this resulting prefix with 10.5.1.0. Of course, they're different. It means that this route is skipped. Similar action performed with second route, this one, but now router applies mask 24 to the same destination IP address, and now as a result it will get 10.9.2.0. It will compare this resulting prefix to 10.23.7.0. They are different. That's why this route is skipped as well. And now router looks into this default route, and it applies mask 0 to this destination IP address. As a result, it will get all zeros. All zeros will be compared to all zeros here, match, and it means that this route will be matched. And now router has found out that it should route this IP packet to next hop router 10.5.1.2. And now it performs one more lookup of the routing table, because now it must find out where this IP address is located, behind which of its interfaces. It now again looks into routing table and compares now this IP address to all routes. And it actually finds first match here, at the first line in routing table. It applies mask 30 to this destination IP address 10.5.1.2. It gets 10.5.1.0. It is the same as prefix here in this route, and it means that now router has found which route and which corresponding interface must be used in order to route IP packet to its destination. And in this example, R1 will choose this interface that connects it to R2 in order to route packet to this destination IP address. That's how R1 performed lookups of routing table. Again, it performed two different lookups. Next packet arrives to R2. It compares destination IP address with its own IP addresses. It will find out that this IP packet must be forwarded further to next router, and now R2 performs lookup of its own routing table. Step by step, it tries to find destination route from the routing table. This one will not be matched, this one also will not be matched, this one also is skipped, this one is skipped as well, and finally this route will be matched. Because now when R2 will apply mask 24 to this destination IP address 10.9.2.10, it will get 10.9.2.0, compare it to this prefix, and here is match. And it means that it should forward this IP packet to next hop router 10.17.2.2. And now it again looks into routing table in order to find out where this IP address is located. It takes now this IP address and looks into this route. It is skipped, looks into this route, and now it finds match. Because now when mask 30 is applied to this IP address, we will get 10.17.2.0, and it is the same as we see here in this prefix route. And it means that now R2 also found which of its own interfaces should be used in order to route packet to this destination IP address. And it is interface where this IP address is configured, this one. That's how R2 made its routing decision, and it performed also lookup of the table two times. One time in order to find out route for destination IP address, this one, and another one in order to find location of the next hop router IP address, this one. And finally, this IP packet arrives to R3, this router. It also performs lookup of the routing table, and it immediately finds match, this route, because it is directly connected to one of its own interfaces. And it means that now R3 is able to send this IP packet directly to this host. It sends ARP request if it doesn't know its MAC address of this receiver. If it knows, then it simply adds destination MAC address on data link layer and sends this frame directly to this laptop. That's how routers perform lookups of the routing tables when IP packet goes, for example, from this host to this host. And now one more example. Let's assume that now, for example, this host sends IP packet to destination IP address, let's say, for 8.8.8.8. And now this R3, when it receives such IP packet, it looks into its own routing table. This route is skipped, this one is skipped as well, they are not matched. And now finally default route is matched, because when we apply mask 0 to IP address all 8s, we get 4 zeros, and 4 zeros is the same as we see here in this network prefix in this route. That's why R3 should route this IP packet to next hop router with IP 10.17.2.1. It looks into routing table once again, it finds this matching route, it sees that it is connected, and it finds out outgoing interface for this IP packet, and sends IP packet from its interface here to R2. R2 receives this IP packet. It performs also lookup of the routing table in order to find matching route for destination IP all 8s. All these routes are skipped, they are not matched. And finally, it matches IP with this default route. And it sees that it should route this IP packet to next hop router 7.3.10.1. It again performs lookup of the routing table, finds corresponding route, this one, that is directly connected, and sends IP packet via its outgoing interface towards this ISP router. That was last example, and I hope that now you understand how routers perform lookups of the routing tables in order to make routing decisions. Wonderful. Next, after the small pause, let me explain you what is a dynamic routing protocol and which protocols actually exist and which are most popular. I'll see you guys next. In the sample network discussed before, there were just 3 different routers, and it was enough to add a couple of static routes on R2 and default routes on each of the routers in order to cover all possible cases of transmission of packets between different hosts, either inside of the local area network or between hosts in the local area network and some hosts in internet. However, that is not always the case, and local area networks may contain hundreds or even thousands of different routers. Also, there are much more routers if we talk about internet. And that's where dynamic routing protocols come in. Those protocols allow routers to automatically exchange information about their directly connected routes. And in such case, when exchange is performed, routers may automatically fill in routing tables and use dynamically received routes in order to make routing decisions. And main advantage of using dynamic routing protocols is that you need to configure every new router that is added to local area network only once. You don't need to add a bunch of static routes to all destination networks. All that will be done by dynamic routing protocol. There are several routing protocols available, and here are some of them. OSPF stands for Open Shortest Path First, BGP stands for Broader Gateway Protocol, RIP stands for Routing Information Protocol, and EIGRP that stands for Enhanced Inter-Gateway Routing Protocol. And notice that this last protocol, EIGRP, is Cisco proprietary protocol, and it means that it could be configured only on Cisco routers. All remaining protocols, this one, or this one, are open source and they are actually available on any routers. Notice that every single routing protocol has its own metric. Metric is utilized when routers need to compare different routes, because it's possible to receive same route via different neighbors, and routers need to decide somehow which route they should utilize, which route is the best. And there are different metrics in different routing protocols. For example, metric in RIP protocol is hop count, that represents quantity of the routers on the way to destination network. For example, metric could be 3 routers, or 5 routers, or 10 routers. And if specific router receives same route, same network via different neighbors with different metrics, with different hop counts, then it will choose a route where hop count is lower than in others. Other protocols, for example OSPF, utilize other metric. And metric in OSPF is primarily built on bandwidth between different routers. And if bandwidth is higher, then metric is better, it is lower. BGP utilizes compound metric, and there are different metrics that are compared when router makes selection of specific route before insertion of this route into routing table. Generally speaking, every routing protocol has its own metric that is based on specific criteria, and also there is preference between different routing protocols. What I mean? On the same router, you could launch, for example, OSPF and RIP protocol. And if specific route is received via both such protocols, via OSPF and via RIP, then router needs somehow decide which of these two routes is preferable and which should be inserted into the routing table. And that's where administrative distance comes in. Every routing protocol has its own administrative distance that makes some protocols more preferable than other protocols. And for example, static routes have administrative distance usually lower than any dynamic routing protocol routes. And it means that static routes are always more preferable than dynamic routes, and so on. I don't want to dive too deep here into this selection process. Just for now, you need to keep in mind that there are several dynamic routing protocols that could be utilized in order to automate exchange of the routes between different routers. And approach here is very simple. Configure and forget. When you take out new router out of the box and set up routing protocol there, for example OSPF or RIP, then you could forget about any other setup. You simply install this router to the network, and all the remaining exchange of the routing information between different routers will be performed automatically. Great, that's an overview of different routing protocols, and now you know that dynamic routing protocols are more preferable than static routes, because static routes must be added manually by administrator of the router. Dynamic will be added dynamically by routers themselves. And now let me explain you what is CIDR. I'll see you guys next. Now it's a good time to explain you what is classless interdomain routing, or shortly CIDR. This term is widely used when we talk about modern computer networks and modern routers. We discussed before that all IP addresses were split into different classes. I'm talking about IPv4 IP addresses. And there are such classes as A, B, C, D, and E. Classes A, B, and C have default mask. And any network of class A has default mask 8, for example network 10.0.0.0/8. Class B networks have default mask 16, and class C networks have default mask 24. But routers now are not bound to those default masks anymore. Initially it was idea to route only based on default masks, but now that is not the case. The reason for that is that some networks, like networks of class A, have many hosts in every single network. And this quantity of hosts is actually unusable quantity, and you couldn't find any local area network interface of the router that has millions of different hosts inside. That's why usually all networks are split into subnetworks, and we discussed how subnetting is performed in one of the previous sections. But the main idea behind the CIDR is that every single route in the routing table has network prefix and mask. So mask is not default one taken from the class A or B or C. Instead, mask is specific, and it is specific for every single route in the routing table. For example, in this routing table, we see such network as 10.2.10.0, and network mask is 24. And we could see that this specific network is actually subnetwork of the class A network 10.0.0.0/8, because we have borrowed additionally 16 bits from the host part in order to create this specific subnetwork. And now quantity of the hosts in this specific subnetwork is which? 254. And that is pretty acceptable quantity, and it allows you to add multiple devices in the same network like this. Type of this network is connected, for example, and it is available via interface gigabit 0/1. Let's now have a look at this route, and it is 193.1.5.64 with network mask 28. And this network actually belongs to class C that has default mask 24, but here we see mask 28. And it means that it is also subnetwork of the class C network. And the quantity of the hosts in this particular network is 2 to power of 4 minus 2, that is 14. And it means that there could be 14 different hosts in this particular subnetwork. Also, let's have a look at this network. It is 172.16.0.0, but mask is 12. Default mask of this class B network is actually 16, but now we see lower mask than 16. What does it mean? It means that you could find in routing tables not only masks that are greater than default mask, like in this route or this route, but you may also find such kind of routes that have masks that are shorter than default mask of the class, 16 in this particular example. And that is called route aggregation or route summarization. And instead of sending multiple routes to the neighbors, for example, via OSPF or RIP routing protocol, router could send just single route. And let's discuss what is route summarization next, but now let me summarize what we discussed here. You need to keep in mind such term as classless interdomain routing, shortly CIDR, that stands for approach to the routing on modern routers that utilizes not just prefix for every single route, but also mask. Every single route consists of prefix and mask, like in this example. Great, next let's discuss what is route summarization. Now you know that the routers actually don't care about the default masks for specific networks of different classes like class A, B or C, and now let me explain you what is route aggregation or summarization. And let me explain you using this example. Let's assume that there are two different routers, R1 and R2. And behind router 1 there are multiple networks like 172.16.0.0/16, 172.17.0.0/16, and so on till 172.31.0.0/16. Basically, if you remember private IP addresses ranges, I have shown here all 16 different networks of the class B network with default mask 16. And let's assume that now we need to transfer information about all those networks from R1 to R2, for example, using routing protocol RIP or OSPF. And we basically could transfer all separate routes, like this one, or this one, to R2, and in total there will be 16 different routes, and R2 will insert all those 16 routes into its routing table. And next hop for all those routes will be the same. It will be IP address of the R1 on this interface. It is basically waste of resources. We send multiple routes from the same router to another router, and this another router R2 will add multiple routes into its routing table. However, using routes aggregation or summarization, we could send only single route from R1 to R2. And this route is called aggregated route. Here it is in this particular example. It is 172.16.0.0 with mask 12, not 16, it is 12. And basically, if you carefully look at those networks and this network, then you could understand that all those 16 networks are actually subnetworks of this aggregated network with mask 12. Difference in quantity of the bits here in network part is 4, 16 minus 12. And using 4 different bits, host bits, we could create 2 to power of 4, that is equal to 16 different subnetworks. And that's what we see actually here, 16 different subnetworks. And using aggregation, again, we could send just single aggregated route from R1 to R2, and R2 will insert it into its routing table. And this record will look like this. 172.16.0.0/12 is accessible via R1. Here should be IP address of the R1 interface on this side, and corresponding local interface on R2. And it means that using routes aggregation approach, we could minimize the quantity of the information that is sent from one router to another using dynamic routing protocol, for example. And also we minimize the quantity of the records in the routing table. And we optimize lookups of the routing table, because now there is just single record in routing table on R2. Secondly, if specific route, for example this route, disappears, let's say that this interface goes down like that, then R1 will not send any update to R2, because it will still send only aggregated route. Of course, in such case, when R2 will decide to send IP packet to the network 172.17.0.0 that is actually not available at the moment, then this packet will be sent to R1 and R1 will drop it, because it will not find corresponding route in its routing table. But on the other hand, R1 will not send updates to R2 every time when specific route appears or disappears. But using this aggregated route approach, it says basically to all other routers, hey guys, this particular network and all subnetworks of this network are available via my interface. So please send all packets to this destination network to me, and I'll handle them correspondingly. Wonderful. That is a short description of route summarization, and notice that it is commonly used in modern routing, very often, when smaller networks are grouped into larger networks, and only aggregated routes are sent via routing protocols. Next, let's get back to private IP addresses space that we discussed before in previous sections, and I'll explain you how you could perform actually aggregation or summarization of private IP addresses spaces. I'll see you guys next. Now you know that thanks to classless interdomain routing, all routers keep all prefixes along with their masks. And it allows us to perform subnetting, and also it allows us to perform routes aggregation, combining several small routes into larger routes. And now let's get back to private IP addresses ranges that we discussed before. And basically, those IP addresses are defined in a document that is called RFC 1918. RFC stands for Request for Comments. And recap that there is just a single class A network. It is 10.0.0.0/8. 8 is default mask for class A network. Here is this network. Also, there are 16 class B networks, and here is a range of all IP addresses that are considered as private. And also there are 256 class C networks, and here is this range. And basically, using routes aggregation approach, we could combine 16 class B networks into one network like this. And we discussed this aggregated route in the previous lecture. It has now mask 12, but it includes all those 16 class B networks. Also, similar approach could be utilized here for aggregation of 256 class C networks. Class C network has default mask 24, but now when we combine all those 256 class C networks into one aggregated network, then mask will be 16. We take out 8 bits, 24 minus 8, and resulting mask will be 16. And using 8 bits, we could actually create 256 subnetworks. And it means that this aggregated network or aggregated route contains all these networks. And now it becomes much more easier to distinguish between private IP addresses and public IP addresses. And now you could simply apply such masks as 16 or 12 in order to determine whether specific IP address is private or public. But why we should have such aggregated routes? Why do we require them? Answer is following. I have told you that private IP addresses are not routable in global internet network. And it means that routers that are located, for example, at internet service provider premises should somehow filter IP packets and block IP packets where source IP or destination IP is from one of these ranges. And for that, these routers could utilize so-called access lists that will filter IP packets by source IP and destination IP. And using knowledge about these aggregated routes, we could add just 3 records into the access list in order to block all IP packets that go from private IP addresses or to private IP addresses. That's that simple. And also, those aggregated routes could be used in routing protocols. And you could tell a router not to insert into the routing table any routes to private IP addresses networks. And this approach is utilized in backbone routers that route internet traffic. Such routers must route only IP packets that have source IP and destination IP from public IP addresses ranges. IP address is public if it doesn't belong to any of these ranges or to any of these 3 networks with such masks, and it belongs to class A or B or C. And of course, you could utilize any of these 3 networks or their subnetworks in local area network, where you manage all routers yourself. But backbone routers in the internet route only public IP addresses. And next, let me explain you what is autonomous system, because this term is used when we talk about IGP and EGP protocols. That we will discuss also next as well. I'll see you guys just in a moment. In the previous lecture, I returned back to private IP addresses ranges, and I did that on purpose, because now it's time to think bigger and return back to the term internet, and now I'll explain you what is autonomous system. Autonomous system is a group of 1 or more network prefixes that are managed by the same organization. And very important notice here is that those network prefixes are from public IP addresses ranges. Here on this diagram you see example of the autonomous system that contains many different devices. Technically, it is very large computer network. There are routers, switches, computers, servers, laptops, and so on. And notice that inside of this autonomous system you see prefix A.A.A.0/24. And this means that the organization that owns this network prefix forms actually autonomous system. And different autonomous systems actually form internet. Autonomous systems are interconnected with each other. For example, when you connect to any internet service provider, you become part of the autonomous system of that internet provider. And here it is important to mention difference between local area network and autonomous system. Let me give you an example. When you buy a router and place it in your house and connect to internet, technically you create very small local area network that consists of router and all devices that you connect to this router. But when you connect to internet service provider, you connect to larger network. And usually every single internet provider has specific range of public IP addresses or multiple ranges. And it means that now entire service provider's network, including your small local area network, forms a large autonomous system. And different internet service providers are connected with each other. And next, let me explain you what is autonomous system number. Autonomous system is a set of network prefixes from public IP addresses ranges. And your small local area network at home is part of larger autonomous system. And you know probably that, for example, you could rent a public IP address and assign it to your router at home. And that's thanks to autonomous system, because provider you are connected to owns specific range or ranges of public IP addresses, and it is able to assign them to different devices like your home router. But how those autonomous systems are basically interconnected with each other? Every single AS, autonomous system, has its own unique autonomous system number, shortly ASN. And internet is basically a set of different autonomous systems that are connected with each other. And on this diagram you see how internet actually looks like. There are different AS with different ASNs, with different autonomous system numbers. And they have different connections between them. For example, this specific autonomous system has 2 connections to 2 other autonomous systems. This AS in the middle has 4 different connections to other autonomous systems. This IS has just single connection to this one, and such autonomous systems are called stub autonomous systems. This one has two connections to this, and so on. And there are many different autonomous systems in Internet, and they are connected with each other in different ways. And there is an organization called IANA that assigns those autonomous system numbers to different organizations, but that is performed via special regional Internet registrars, and there are 5 of them in the world. And examples are RIPE, that works in Europe, and ARIN, that works in USA. Every autonomous system number is unique number, and it is 32-bit number. And you could guess how many different autonomous system numbers could exist in the world. It is 2 to the power of 32. This number is very large. Before, there were shorter ASNs, and they were just 16 bits long, and later this number was extended to accumulate higher demand for those autonomous system numbers. And basically, every company that wants to be present in the Internet and wants to own specific range of public IP addresses is able to claim autonomous system number. But you're not able to get ASN if you don't have any public IP addresses range assigned to your organization. Alright, that is autonomous system number. And next, let's do quick demo, and basically you will be able to follow me along and verify which autonomous system numbers are assigned to different organizations. I'll see you guys next. Autonomous system number is a special number that is assigned to different autonomous systems. And every internet service provider, if it is a large provider, has its own autonomous system if it possesses special range or ranges of public IP addresses. And now let's verify which autonomous system numbers are assigned to our internet providers. And in order to start verification, you need to get your public IP address. And for that, you could simply open up any new tab in Google Chrome and simply type my IP, and here somewhere below you'll find your public IP address. Here is mine. I'll copy it from here and go to ultratools.com/iptools, and here I'll click ASN information. And in this field, I'll paste simply IP address that I have just grabbed on another tab. And now I'll click Go. And actually, as a result, I'll find which autonomous system number is assigned to internet provider I am connected currently to. And here is this number in my case, AS24685. It is 5 decimal numbers. And here below you see information about country, registration date, registrar and owner. And basically, registrar was responsible for registration of actual autonomous system number. And in my case, it is RIPE NCC. It is European registrar. Here is owner. It is a company that owns this specific autonomous system number and also this public IP address. Here is registration date. It is 2002. And here is country, Ukraine. Now you could verify another IP address. For example, we could verify Google's IP address. Let's enter here 8.8.8.8 like that, go. And here is information about another autonomous system. It is 15169, country is United States. Here is on the next line registration date. This registration happened long ago. Registrar here is ARIN, and it is different from registrar in previous case, because now this organization, owner of this autonomous system, is located in United States. That's why here we see different registrar. Let's verify one more IP address, and it is 1.1.1.1, like that. Let's click Go. And you'll see that owner of this public IP address is Cloudflare.net, and it is located in United States. And that's why registrar is the same as for Google. It is ARIN. Here is registration date, and country is US. And here is autonomous system number that is different from Google's autonomous system number, because all numbers for autonomous systems must be unique and different. Alright, now you know what is autonomous system, what is autonomous system number, and also you know that every autonomous system is managed by specific organization, and if specific ASN is assigned to this organization, then specific range of public IP addresses is also assigned to it. And now it's time to get back to routing and discuss how routing is performed inside of the autonomous system and between different autonomous systems. And there are basically two different groups of routing protocols. First group is called interior gateway protocols, shortly IGPs, that work inside of the autonomous system. And second group is called EGP, that stands for exterior gateway protocols. And there is just a single protocol that belongs to this group. And next, let's discuss differences between IGPs and EGPs. I'll see you guys next. Now you know that at the high level, Internet is a set of different autonomous systems. And every single autonomous system may contain hundreds or even thousands of different routers. And there are different routing protocols that work inside of the autonomous systems and between autonomous systems. And they are called IGP, that stands for Interior Gateway Protocol, and EGP, Exterior Gateway Protocol. It means that if specific routing protocol is used for exchange of the information about routes inside of the autonomous system, for example this one, then this routing protocol is called IGP, Interior Gateway Protocol. And examples of IGP protocols are here. You see here such titles as OSPF, that stands for Open Shortest Path First. Next one is EIGRP, that stands for Enhanced Interior Gateway Routing Protocol, and RIP, that stands for Routing Information Protocol. All these protocols are IGP protocols that are utilized inside of the autonomous system. But if we need to send some prefixes from one autonomous system to another, and this will be definitely public IP addresses prefixes, then we need to use EGP protocol, Exterior Gateway Protocol. And there is just single such kind of protocol that is used for global routing. And this protocol is called BGP, that stands for Border Gateway Protocol. And now let's talk about differences between IGP protocols and EGP protocols. IGP is used for exchange of routing information within autonomous system. And usually network prefixes that are exchanged via such protocols as OSPF, EIGRP or RIP are from private IP addresses ranges. EGP, on the other hand, is used for exchange of routing information between different autonomous systems. And if specific autonomous system has connections to multiple other autonomous systems, then exchange happens with every single another autonomous system. And all networks that are exchanged between different autonomous systems are always from public IP addresses ranges, always. EGP is never utilized for exchange of private networks. Never. So, example of EGP is BGP, and examples of IGP protocols are OSPF, EIGRP, and RIP. Different routing protocols work differently, and main difference is in approach to calculation of metric that is used for selection of the best path to destination network, because every single remote network may be received from different neighbors, and every router should select specific route that is the best route to destination. But except that, routing protocols are divided into two groups: link state routing protocols and distance vector routing protocols. And next, let me define difference between those two types. In the previous lecture, we discussed difference between IGP protocols and EGP protocols. And this difference actually answers where routing protocol operates, either within autonomous system or between autonomous systems. And now let's answer the question how routing protocol operates. And there are two different types of routing protocols: distance vector routing protocol and link state routing protocol. And here you see examples of routing protocols that are distance vector and link state. BGP, EIGRP, and RIP are distance vector routing protocols. OSPF and IS are examples of link state routing protocols. But what is the main difference between distance vector and link state routing protocols? Difference is in approach to exchange of the routing information and making decisions. Before looking at those points, let me give you the following example. Let's suppose that you are driving a car on the road, and you see a sign near the road that tells you that New York City is to the right, you need to turn right, and distance to New York is, let's say, 100 miles. In this case, you know distance, 100 miles, and you know vector. You know that you need to turn right in order to get to New York. And it is analogy to distance vector routing protocols. Every router knows distance and knows direction. That's it. When you drive a car and you see such sign, you don't know whether there are some traffic jams, what is the weather forecast, what are other cities on the way to New York. You don't know anything about that. You just know distance and you know vector. You need to turn right. That's all what you know. And now let's assume that you have a phone, and in the phone you entered a route to New York. And inside of the phone you see also traffic jams, you see all points on the way to New York, all villages, all small cities, everything. You know weather forecast, you know conditions, you know time, you know many different details. And this analogy applies to link state routing protocols. And it means that when you know more information, you could make decisions more wisely. And it means that you don't simply rely and trust sign and the road. Instead, you make decisions on your own. You select the best path to destination because you know more about all different alternative ways how to reach New York City. And now let's discuss characteristics of distance vector routing protocols and link state routing protocols. In distance vector routing protocol, routers send information about their directly connected networks to their neighbors, only to the neighbors. Let's suppose that a specific router has 3 different neighbors that are directly connected to it. It means that in distance vector routing protocol, this router will send information about its directly connected networks only to those 3 routers. That's it. Next, every router selects best routes from the perspective of the neighbor. It means that when a specific router receives information about some remote network from neighbor router, then it will rely on this information and it will simply know that this specific network is accessible via this neighbor. That's it. And that's how this router will make selection of the best route. It will rely on the information received from the neighbor. Similarly, as you rely on information that you see on the sign on the road. Next point. Distance vector routing protocols have slow convergence. What is convergence? Convergence happens when a specific network disappears or appears. For example, on specific router in some place in computer network, specific interface goes down. It means that corresponding directly connected route disappears from its routing table. And it means that if this route was advertised via any routing protocol to its neighbors, this router needs to send update and tell them that this specific network is no longer accessible. And when all other routers in the network in the autonomous system will receive this update, we could say that network has converged. It means that now all routers have consistent information. Similar example, when specific network appears, when for example specific interface on the router goes up. Then this router needs to send information about this network to other neighbors. Those neighbors must send information to other neighbors and so on and so forth, until network will be converged again. In distance vector routing protocols, convergence is slower than in link state routing protocols, because updates are sent from one neighbor to another, from another to another, and so on and so forth. Next point. In distance vector routing protocols, routers utilize less CPU and memory in comparison to link state routing protocols. They need to keep less information than in link state routing protocols. They actually get information only about routes and metrics from their neighbors, and after that they simply need to select best route, and that's it. Best routes are inserted into the routing table. And all routes actually are stored in the routing database, and routing database is usually larger than routing table itself. And also distance vector routing protocols are prone to errors and loops, for example. And this may happen when routing tables are inconsistent and when specific updates were not yet received by some routers, and they may still route packets to some destinations that are already inaccessible, that are down. And this may very easily happen in distance vector routing protocols. Alright, let's now discuss characteristics of link state routing protocols. Here, routers send information about their links to all routers in the autonomous system. That is the main difference from distance vector routing protocols. It means that specific router may tell all other routers in the autonomous system, hey, here are my 3 links. Here is IP address and mask for every link on my router. And this information is transmitted via all neighbors to all other routers in the autonomous system. And now when all routers receive information about all links in the autonomous system on other routers, they may make decisions on their own. They select best routes to every single destination network, keeping all information about all links in the autonomous system in their memory. And of course, in such case, convergence will be much faster, because when specific network goes down, specific router will quickly send small update to all neighbors, they will replicate this update to their neighbors and so on, and convergence will happen much faster. But of course, if routers keep all those details in their memories, they require higher CPU and memory resources. And of course, all computations are made in memory of the routers that also takes resources. But certainly, link state routing protocols are very reliable, and they are less prone to any routing errors in comparison to distance vector routing protocols. The most popular link state routing protocol is OSPF. It is open source and it is available on any routers of any vendors. Is really nice protocol, but unfortunately it didn't become popular. And also, very important notice, all those mentioned protocols here are capable of exchange of IP version 4 prefixes and IP version 6 prefixes. For some protocols, there are different versions of the protocol that actually work with different protocols on network layer, I mean IP version 4 or IP version 6. Alright, that is the difference between distance vector and link state routing protocols. Link state is more sophisticated, and most popular choice here is OSPF. OSPF is basically most popular protocol that is used inside of the autonomous system. It is IGP protocol. But of course, you could also utilize distance vector routing protocol, and the most popular protocol for EGP connections is basically BGP protocol. This is just single choice. And now my question to you. Why BGP is actually distance vector routing protocol? Why it is not link state? Answer is following. As you already know, there are many different autonomous systems in the world. Basically, every organization that has specific public IP addresses ranges assigned to it could claim and get ASN number. And now routing tables on core routers, BGP routers, are very large, and quantity of the routes, BGP routes, is close to 1 million. And this means that BGP routers need to utilize many memory resources in order to just keep this BGP routing table in memory. It is very hard. And if BGP was link state routing protocol, then all these BGP routers would keep in memory all information about all links of all BGP routers in the world. This information is very huge. And there is no such kind of router in the world that would be able to keep all this data in memory and make decisions on its own, make selections of best routes to destination networks. That's why BGP is distance vector protocol. And it means that in BGP, every router sends BGP prefixes with masks and metrics to all neighbors, and those neighbors make selections of best routes based on information received from neighbors. Alright, that's all for this lecture, where we compared distance vector and link state routing protocols. Most popular link state routing protocol is OSPF, it is IGP protocol, and most popular distance vector protocol is BGP. It is EGP protocol, and it is used in order to exchange routing information between autonomous systems. Great. Next, let me tell you which networks are blocked in BGP. I'll see you guys next. Now you know what is the difference between link state and distance vector routing protocols. You know that link state protocols converge faster and they are more sophisticated, and every router in link state routing protocol makes decisions on its own. And distance vector protocols actually rely on information received from their neighbors. And now let's discuss what are filtered routes in BGP, because BGP is single EGP protocol, it is distance vector routing protocol, and it is used in order to exchange information about routes in global network internet. And basically different routers, border routers that are located in different autonomous systems, work via BGP with different neighbors in other autonomous systems. And here are networks that are blocked in BGP, and they must be filtered by BGP routers. What does it mean? It means that if specific BGP-enabled router receives any of such networks or their subnetworks from specific neighbor, it must filter out those routes and don't insert them into BGP routing table. And of course, don't resend to other BGP neighbors. And for that, there is actually a special mechanism used in BGP that is called prefix routes. And next, after the small pause, let me give you an example of such prefix list that is very often used on BGP routers. I'll see you guys next. You already know that BGP-enabled routers exchange information about public routes in global network internet between different autonomous systems. And if specific BGP router receives all networks from its neighbors, then we could tell that it receives full view. And currently this full view is close to 1 million records. And according to RFC 1918, BGP routers must filter out any private routes and don't insert them into BGP table. And of course, BGP routers are not allowed to send such networks to their neighbors. But by default, in BGP routing protocol itself, there is no mechanism that blocks such routes from insertion into BGP tables. That's why BGP routers must enable such filtering on their own. On each separate BGP router, administrator must set up such filtering. And such filtering is performed on BGP routers using prefix lists. Here is an example of prefix list that blocks some routes from neighbors. And let me give you a quick overview of this prefix list. I will not focus on syntax like IP prefix list because this syntax is different on different routers produced by different manufacturers, but I'll give you just an idea how prefix list works. So let me first have a look at this line. On this line we see keyword deny, then we see network prefix 10.0.0.0/8, and then LE32. LE stands for less. You know that every route in routing table has network prefix and mask. And basically, via any routing protocol, routers send to their neighbors network prefixes along with masks. For example, specific router may send to its neighbor network prefix 10.0.1.0 with mask 24. And this is actually subnet of the network 10.0.0.0/8, right? And using such line of code, we are able to block from insertion into BGP table all networks that are subnetworks of the network 10.0.0.0/8. And basically here we define range of network masks. And range in this case is from 8 inclusive to 32 inclusive. Again, this single record will block from insertion into BGP table such networks as, for example, 10.0.0.0/8 or 10.1.0.0/16 or 10.15.10.0/24 and so on. Network 10.0.0.0/8 and all its subnetworks. Similar picture is here on this line. On this line, we block from insertion into BGP table network 172.16.0.0/12. It is actually aggregated route. We have discussed it here on this step. Here is this aggregated route. And also we deny all its subnetworks, because here we see less than 32. Masks range could be from 12 to 32. Same applies to this record. It is one record that actually blocks all class C private networks. And it is written like 192.168.0.0/16 and mask must be less than 32. So mask range is from 16 to 32. Also, there are some other records for networks that should not be inserted into BGP table. And here you see another example that actually blocks any local host or loopback IP addresses, because you know that 127.0.0.1 is considered as loopback or local host address, and basically entire range that has 127 in first octet must be blocked. Here is an example of the range that is used for assignment of the IP address to any host if it wasn't able to get IP address via DHCP. It is actually automated IP address range, and it is also must be blocked from insertion into BGP. Here is another range, and basically it is a range of reserved IP addresses that are also not allowed to be used in the public internet. On this line, you see addresses range that is already familiar to you, and it is basically class D network range, and this range is range for multicast IP addresses that have 1110 in the first octet, or in decimal 224. And network range mask must be from 3 to 32. Again, here we define all class D IP addresses, just using one record. Also, I didn't mention this record that blocks any ranges that have 0 in first octet. Here mask is from 8 to 32. And finally, we see record with keyword permit, all zeros, and network mask range is from 0 to 32. And basically all remaining networks with their masks match this last record. If specific network prefix with mask received from neighbor didn't match any of previous records with deny statement, then such record will match this permit statement, and such networks will be allowed to be inserted into BGP table. That is example of BGP prefix list that should be configured and applied on every BGP router. Alright, I wanted to give you some small insights into BGP routing protocol in order to make you understand that this protocol is very sophisticated, and also it has many different kinds of metrics that are used in process of choose of different routes to destinations. But I don't want to dive deeper here in this course, and now it's time to get back to routing protocols in general, and I'll explain you how different metrics could impact route selection process. I'll see you guys next. Now you have some basic knowledge about the global routing protocol BGP, and you know differences between EGP and IGP routing protocols. Also, you know difference between distance vector and link state routing protocols. And now in this lecture, let me talk about different alternative routes to remote networks. On this diagram, you see several routers like R1, R2, R3, and R4. And notice that there are different connections between different routers. For example, R1 is directly connected to R2, R2 is directly connected to R4. Also, R1 has direct connection to R4. Similarly, R3 is connected to R1 and R4. And this means that when R1 wants to choose route to this remote network, it could select it via R2, via R4, or via R3, because it has different alternative ways to this remote network. Similarly, another routers, for example, router R2, could select different ways to, for example, this network. It could go directly via R1 router, or it could go via R4, R3, and then R1 and reach this destination network. And different routing protocols basically will choose different ways to remote destination network depending on different metrics of specific routes. And please recap that when router receives a specific network from any of its neighbors, it first inserts it into routing database. And afterwards, from routing database, every router selects best routes and inserts them into the routing table. And next, let me talk about metrics, and I'll explain you that different routing protocols select the best routes to remote networks differently, and that depends on the approach to calculation of the metric. I'll see you guys in the next lecture. It It is a very rare case when specific router has just a single connection to another router. Of course, if you have small local area network at home, you usually have a single connection to single internet provider. But if this ISP fails, then you won't be able to get to internet. That's why in large organizations and in large internet service providers, there are multiple connections between different routers. And there are redundant alternative paths to different remote networks. And now let me explain you what is routing protocol metric or cost. Different routing protocols have different metrics. And let me explain you difference in metrics using this diagram. On this diagram you see several routers and there are several connections between them. And also you see bandwidth of every link. For example, this connection is 1 gigabit per second. This connection between R2 and R5 is 100 megabits per second. This connection between R3 and R4 is 1 gigabit, this one is also 1 gigabit, and the connection between R1 and R3 has bandwidth 10 gigabits per second. And let's assume that now router R1 needs to select the best path to remote network 10.5.1.0/24. And let's assume that those routers exchange information about their directly connected networks using routing protocols. So, question is which path R1 will select to get to this remote network? Will it select path via R2 and R5? Or it will select path via R3, R4 and R5? Answer depends on the routing protocol in use. For example, routing protocol RIP will select path via R2 router. Why? Because its metric is based on hop count, and hop count for this route will be smaller than hop count for this path. Because here you see 3 different routers on the way, and here you see just 2 different routers on the way. It means that this path is better for RIP. But notice that this link here is just 100 megabits per second. And smallest bandwidth for this path, for any of those links, is 1 gigabit per second. And it seems that this route is better, it has more bandwidth, and it is capable of transmission of larger amount of IP packets. And that's why OSPF will choose this path as a best path to this remote network. And R1 will send packets towards R3, then packets will go via R4 and then to R5. The reason for that is that in OSPF, metric calculation is based on the bandwidth of the links. And if a specific link has higher bandwidth, then its cost will be smaller than cost of the link that has lower bandwidth. For example, if we compare this link and this link, then in terms of OSPF, this link will be better. But for RIP, it doesn't matter which bandwidth is available on those links, because again, its single metric is based on hop count. OSPF metric is based on bandwidth of different links. But of course, OSPF sums different metrics for every single link. And if, as in this example, there are multiple links towards destination network, then OSPF will sum up costs of every single link, this one, and this one. But this cost will be smaller than cumulative cost of this route with those 2 links. That's OSPF's approach. I will not explain you how other protocols calculate metric, but I hope you get an idea. Different routing protocols may select best routes differently, and it depends on the metric for every single route. Great. Next, let me explain you whether routers are able to insert several same routes to remote destination or not. I'll see you guys next. Now you know that different routing protocols may select the best routes differently, and that depends on the metric or cost of every single route. And in different routing protocols, this cost is calculated differently. Now let's talk about equal cost path balancing. What is that? Let's have a look at diagram that we have seen before, and let's assume that R1 wants to select the best route to remote network 10.23.2.0/24. And let's assume that we use, let's say, RIP routing protocol here, and its metric is hop count. And let's assume that R2 will send this route to R1, and R3 will also send this remote route to R1. And on R1, this route will have same metric, that is hop count in RIP, and it will be equal to 2. And in this case, R1 may insert into the routing table two exactly the same routes, except the difference in next hop router. And here is routing table of R1, and you see two exactly the same prefixes with masks. They are equal to this prefix with mask, it is a remote network for R1. But next hops are different. Here for this route you see IP address of R1, this one as a next hop. And in this route you see this IP address of R3 as next hop for this second route. And metric here is again the same. Metric is equal. And this approach is called equal cost load balancing. And this happens when specific router simply inserts several routes to the same remote network into its routing table. And afterwards, this router, in our example R1, may balance packets across different routes. For example, one packet will be routed towards R2, another packet will be routed towards R3. Next packet will go again via R2 using this route, and so on. Router simply balances load using different routes. And basically with such approach we could optimize resources of the routers and use them equally. Instead of sending all packets to one of these routers, either R2 or R3, we balance traffic between two different routers, and they get less load. And also we use those two links equally. We don't overload one while another is simply empty. And that's thanks to equal cost load balancing. And routers may insert not just two different routes to the same remote network, they may insert even more, for example 4 or 6. Great, that's how routers may utilize different alternative links to remote networks. And next, let's get back to example when specific packet is sent from one network to another, and in that example we discussed that there is just a single router in between. But we will add a couple of additional routers, and I'll explain you how end-to-end transmission happens in such case. I'll see you guys in the next lecture. Do you remember this diagram where I explained you how end-to-end transmission happens when there are switches and a single router on the way between two different computers? And here in this example there were around 21 different steps. And in this example there was just single router and it had two different directly connected networks, and this example was relatively easy. And now let me try to summarize what happens step by step if there is not just a single router, but if there are multiple routers on the way between two different computers. And here is another diagram. I will not show all detailed steps, I will just explain you difference from the previous case. And let's assume that R1 already received the IP packet that goes from PC1 to PC2, and it received it on its gigabit 0/0 interface. And destination MAC address in this packet, in this frame, was this MAC address of gigabit 0/0 interface on R1 router. And now R1 needs to send this IP packet further. And please remember that when a router receives a specific frame, and when this frame has destination MAC address equal to MAC address of the router's interface, then this data link layer header is stripped, removed, and router processes header of the IP packet. And when a router has selected outgoing interface, it again adds data link header, and in that header, source MAC address and destination MAC address will be completely new. So, let's assume that packet is at R1 router, and now it needs to look into its routing table and find outgoing interface. Recap that destination IP address in this packet is equal to 192.168.1.15. Here is part of R1 routing table. In fact, it has much more routes than shown here. But for simplicity on this diagram, I've added only relevant routes. And here in routing table of R1, we could find such a route as this one. Please recap that when a router makes routing decision, it takes destination IP address, this one in our case, and applies masks from the routes in its routing table. So first it will take this prefix and mask and apply this mask to destination IP address, and resulting prefixes will be compared, and of course those prefixes will not be equal. This route will be skipped and the next router will look into this route. It will take mask 24, apply it to destination IP address, and as a result we will get prefix 192.168.1.0, and this prefix is exactly the same as we see here in routing table. And this means that router R1 has selected best route for a remote destination. And next hop here is 5.1.2.1. It is IP address of gigabit 0/0 interface on R2 router, this router, because this network prefix has received, let's suppose, via specific routing protocol, RIP or OSPF, from R2 to R1. And that's why now R1 needs to look into its routing table once again and find where this next hop IP is located. And it finds this route that is directly connected, and of course every directly connected route has specific outgoing interface. And in this example, this outgoing interface on R1 will be gigabit 0/1. And when outgoing interface was chosen, then router R1 needs to add data link layer header. And in this header, source MAC address will be equal to MAC address of the gigabit 0/1 interface, outgoing interface on R1, and destination MAC address must be MAC address of the IP address 5.1.2.1, that is next hop router in this case, for this specific route. And if R1 does not have in ARP table mapping of this IP 5.1.2.1 to MAC address, then R1 will send ARP request on this gigabit 0/1 interface, and router R2 will receive this ARP request and will answer with its own MAC address. And after this action, R1 will have mapping of IP to MAC of R2 gigabit 0/0 interface in its ARP cache table. And now it is able to add the data link layer header, where again source MAC will be equal to this MAC address and destination MAC address will be equal to this MAC address that is configured on gigabit 0/0 interface on R2. And afterwards R1 will send this frame via its gigabit 0/1 interface. If there are some switches between R1 and R2, then they will switch this frame towards R2. And finally R2 will receive this frame. It will compare destination MAC address to its MAC address on this interface, they are equal. It means it will strip data link layer header and process IP version 4 header. It will see that destination IP address is equal to this IP address, and it means that this R2 router needs to route this IP packet further. It will again look into its routing table, here it is, and here it will find matching route to destination. And now next hop is equal to 20.1.8.2. It is IP address on gigabit 0/0 interface on next hop R3 router. And again, let's assume that this network was received via specific routing protocol from R3 to R2, and R2 sent this route to R1. So, needed route was selected. Now R2 will look into its routing table once again in order to find out outgoing interface. It finds out that this is matching route for this next hop IP address, and here is directly connected route, and it will find matching outgoing interface, in this example gigabit 0/1, this one. Again, it needs to add new data link layer header with source MAC and destination MAC. If it does not know destination MAC address for next hop IP address, this one, then again R2 will send ARP request asking for MAC address of IP address 20.1.8.2 R2 and R3 will answer with its MAC address, and when ARP table is complete on R2, then it will add new data link layer header, where source MAC address will be this one and destination MAC address will be this one. And after switching on the switches between R2 and R3, if any, R3 will receive this frame. It will compare destination MAC address with its own MAC address on this interface. If they match, it will strip a data link layer header and process IP version 4 header. And in this header, it will find destination IP address, this one, and it will look into its routing table. And on R3, this route is directly connected. Here you see that. And it means that now R3 needs simply send ARP request asking for MAC address of destination host, this one, this computer, if of course it does not know yet about this destination MAC address, and afterwards send IP packet directly towards PC2. And on data link layer, it will add source MAC address equal to MAC address of its gigabit 0/1 interface, and destination MAC address will be MAC address of this PC2. And finally, PC2 received this IP packet from PC1. And main idea that every router on the way between PC1 and PC2 removes data link layer header for incoming packet and adds brand new data link layer header on outgoing packet. And certainly every single router decrements TTL, time to leave, and recalculates header checksum on network layer for every single IP packet. Great, that's how picture looks like when there are multiple routers on the way, and in reality when you make any request to remote web server or mail server, routers on the way between you and remote server perform exactly the same actions. And usually there are not more than 10 routers on the way to any remote server. And you could verify that using, for example, traceroute utility that utilizes ICMP protocol. And next, after the small pause, let's quickly do this test. I'll see you guys in the next lecture. I have just explained you how end-to-end transmission between two different hosts happens if there are multiple routers between them. And routers perform the lookups of their routing tables that were built before. And of course, routers look into their ARP tables in order to find the matching MAC address for next hop routers. And the switches look into their MAC addresses table in order to switch specific frame just to one outgoing interface. That's what happens in reality when specific host transmits any frame or IP packet to remote host. And now let's, using tracert or traceroute utility, verify which routers are located between our computers and remote specific server. On Mac and Unix-like systems, name of this utility is traceroute, and you could simply open up terminal and type here traceroute like this. And here as argument, let's pass IP address of the Google's DNS server 8.8.8.8 and simply press enter. And I see basically different routers on the way between my computer and remote server. In this example, remote server's IP address is 8.8.8.8. And in my case, I see 12 different hops towards a remote router. And let's examine them from the very first one, this one. In my case, I see IP address of my wireless router, and this IP address is from private IP addresses range. Next to IP address of specific router, you may find timers that demonstrate how much time it took for IP packet to travel to router and back. Next on this line, I see next hop router that goes after this router with this IP address, and IP address of the router in my case is this one. It is also from private IP addresses range. And next hop router, router with ID 3, has already IP address from public IP addressing space. And it means that here we see IP address, I see in my case, you'll see completely different IP addresses. It is IP address of one of the backbone routers that are located on Internet Service Provider side. Next hop is here, it is one more router that is located behind this router with this IP, and so on. All these routers have public IP addresses, till destination router, this one, 4/8. Again, all these IP addresses, this one, are public IP addresses. Great, that's how you could verify which routers with which IP addresses are located between your computer and remote server. Similar utility is available on Windows. Let me switch to Windows, and here title of this utility is tracert, like that. Let's tracert the path to, for example, IP 1.1.1.1. It is Cloudflare IP address. On Windows, this utility works a bit slower, I don't know why. But basically, here I'll see similar picture. Let me pause video now and get back to you when tracert will be completed. Alright, tracert was completed, and for this particular request I see that there are 9 hops between this computer, Windows computer, and remote IP address all once. And I see actually similar picture, but first IP address of the first router differs from the IP address in this output on Mac computer, and the reason for that is that this Windows computer is basically virtual machine running on my macOS computer. And that's why default gateway for this Windows computer is this one, .2.2 at the end. And it is actually first router on the way to remote destinations. Next IP address of the next hop router is equal to IP address of my wireless router, and it matches with this IP address that I see here in this output at the first place. Next router is here, and this IP address is equal to this IP address. It means that packets from this Windows computer towards this IP address and towards this IP address travel via the same routers. Next IP is here, .34 at the end, same IP is here. Next 3 start with 100, and again all these IP addresses are public IP addresses. And notice this IP address that ends with .78, let's find the same here. And it seems that here where paths actually differ, and here on step number 6 I see IP that ends with 82, and here I see IP that ends with 78. And it means that on this specific router, actually this specific router with IP that ends with 110, these routes to this IP and to IP for once go via different next hop routers, because next hop IP addresses are different, this one and this one. Great, and finally after this one there is one more hop router with this IP address, and finally after this one we get to destination with this IP all fours. And basically you may notice that this tracert utility also tries to resolve IP address of specific router to its domain name. And resolve process was successful for this IP and this IP in my case. So here DNS name for this specific host is 1.1.1.1, and the host name of this specific IP address is here, detail-ix.cloudflare.com. Similarly, you may notice that Mac also tried to resolve IP addresses, and the resolve process was successful just for this IP. So here is DNS name of this remote server. Great, that's how using a traceroute or tracert utility on Windows you could find which routers are located between you and remote destination host. That's all for this demo lecture, and next let's summarize what we discussed in this routing section. I'll see you guys next. Section dedicated to routing is over, and now let me quickly summarize key points about routers and routing. Routers are most popular devices that work in internet, and they work on network layer of TCP/IP model, and every single router builds its own routing table. And this routing table may contain different types of routes, like connected, static, RIP, OSPF, BGP, ERGRP, and so on. And every single route in the routing table has network and mask, it has type, it has next router, and it also has outgoing interface. And for every single IP packet, router examines its routing table, and each router makes routing decisions independently from other routers. Great. Also, we discussed how routing happens between two different networks, like this network and this network, if there was just single router in between. And I have explained you step by step what happens on every single device, starting from PC1. And here different actions actually happen. Switches look into their MAC addresses tables. Routers and computers look into their ARP tables. Routers perform lookup of routing tables. Also, routers remove data link layer headers and add new data link layer headers. Also, every device like switch or router verify checksum. For example, switch verifies frame check sequence for every single frame. Router verifies this FCS as well, and also it verifies header checksum in IP header. Also, every router decrements TTL and recalculates header checksum before sending IP packet to next hop or to destination host. Great. Also, we discussed what happens if there are multiple routers between two different hosts, and in such case, every single router performs lookup of the routing table on its own. And in this particular example, there are three different routers between this sender and this receiver, and every single router will perform lookup of its routing table. Also, every single router will remove data link layer header and add new one when it will send IP packet to next hop router. We discussed what is the difference between static and dynamic routes. Static routes are routes that are added to the routing table manually by network administrator. But usually, dynamic protocols and dynamic routes are used instead. You need just to set up specific routing protocol, and afterwards routers will perform exchange of their directly connected routes and fill their routing tables, and of course they will keep routing tables updated. It means that if specific route goes down on one of routers, then it will notify other routers and they will update their routing tables correspondingly. Next, we discussed what is default route, and sometimes this route is called last resort route, and it is located at the end of the routing table, and if no matching routes were found before this route, then this route will match any destination IP address. Because when you apply such mask 0 to any IP address, you'll get prefix all zeros that is always equal to this prefix in default route. Also, we discussed how default routes could be utilized, and for this particular example, when R1 and R2 have only single uplink connection to other router, you could easily use default routes for R1 and R3, and they will point to IP address of R2. And in total, on R1 there will be 3 different routes for this particular example, and on R3 there will be also 3 routes, but this default route will point to this IP address that is configured on this side of R2, on this interface. And on R2 there are 3 directly connected routes in this example, this one, and this one. Also there are, let's assume, 2 different static routes to this network and to this network. And also this R2 router has a default route that points to ISP's router, and this route is utilized for routing of the packets to internet. And next, we discussed what are dynamic routing protocols and which protocols exist. Most popular are OSPF and BGP. Also, we discussed what is classless interdomain routing, and with CIDR, routers don't stick to default masks of different classes of the networks, like class A, class B, or class C. And that's why every single route in the routing table has network prefix and mask. And in this example, you see that in the first route, this one, network mask is 24, but default mask for this range is 8, this class A network. Also, you may notice such routes in the routing tables when mask is less than default mask for specific class, because here you see class B network that has default class mask 16, but in this routing table you see mask 12, that is less than 16. And this route is called aggregated route or summarized route. And you could easily perform aggregation or summarization of smaller routes into larger routes in order to reduce amount of updates and also reduce quantity of the routes in other routers' memories. And in this example, you see that all these routes are summarized into just single route that is sent, for example, via RIP or OSPF routing protocol from R1 to R2, and R2 inserts just single route into the routing table that covers all these routes. Next, we discussed what are private IP addresses. We discussed them a lot before, and they are defined in RFC 1918, the special document. And also I explained you that it is possible to aggregate or summarize all private networks of Class B and Class C ranges. And here is aggregated route that includes all these 16 Class B networks. And here is aggregated route that includes all 256 Class C networks that belong to private range. Wonderful. Next, I explained you what is autonomous system, and it is actually a very large network. And actually every single autonomous system is set of public prefixes, one or multiple prefixes. And when a specific organization has requested specific public IP addresses range, it also can request specific autonomous system number. That is a unique number in the world, and it is 32-bit number. And actually, in internet, different autonomous systems are connected using their numbers. And every single autonomous system may have either one or multiple connections to other autonomous systems. For example, this autonomous system has just single connection to another one, and it is called in such case stub autonomous system. Next, we discussed difference between IGP and EGP protocols. And IGP protocols are protocols that work inside of the autonomous system. And such protocols usually exchange routes from private ranges that we have just discussed and that are defined in RFC 1918. EGP protocol works for exchange of the routes between autonomous systems, and there was just single EGP protocol. It is BGP, Border Gateway Protocol, and BGP is utilized for exchange of the public routes, always public. No private routes are exchanged via BGP. And BGP has special mechanisms that actually allow to block specific networks that belong to private ranges. Also, I explained you what is the difference between distance vector and link state routing protocols. Link state are more sophisticated but require more memory and CPU resources. And examples of link state protocols are OSPF and ISIS. And distance vector routing protocols like BGP and RIP require less memory and CPU resources, and they actually rely on information received from the neighbor. Next, I have dived a bit deeper into BGP, and I explained you that BGP routers must filter out private networks that are subnetworks from any of these three networks. And for that, BGP routers utilize so-called prefix lists. And here is an example of prefix list that could be configured on any BGP router. Of course, syntax is different for different routers of different manufacturers. Next, we discussed that routers may have multiple alternative ways to remote networks, because routers usually have redundant connections between them. And in this example, every router, for example R1, may choose different routes to this remote network, either via R2 or directly via R4 or via R3. Those are three different alternative routes to this remote network. Same applies to other routers like R2, R4 or R3. In this sample network, there are 1, 2, 3, 4, 5, 6, 7 different networks. And basically, in routing table of every router, there will be 7 different routes. But in the routing database, there will be much more routes, because router selects best routes from the routing database and inserts them into the routing table. Next, we discussed what is routing protocol metric or cost, and it is different for different routing protocols like OSPF and RIP. And I gave you an example that metric in RIP is based on hop count, and RIP will choose this specific route towards this remote network because it has less hops than this route via R3 and R4. But OSPF, on the other hand, will choose this route because it is more faster than this one. So speed of those links is better than speed of those links, because here we see slow link that is slower than this or this or this link. That's how different routing protocols approach selection of best routes before insertion them into the routing table. Also, I explained you that it is possible to insert the same routes into the routing table if metric is the same. And in this particular example, R1 could insert two different routes into its routing table to this remote network via R2 and R3. And this R1 router will balance load between R2 and R3. And all these links will be utilized for transmission of data to this destination network. That's how we could equally utilize resources of all routers in this example and all links. And finally, I explained you how end-to-end transmission happens between two different hosts if there are multiple routers on the way. Every single router performs lookup of its routing table, makes routing decisions, and also every single router removes data link layer header when it receives specific packet. And when it has made decision and the outgoing interface is selected, it adds brand new data link layer header. And in this example, here between PC1 and R1 will be one data link layer header, with source MAC this one and destination MAC this one. Between R1 and R2, source MAC on data link layer will be this one and destination will be this one. Between R2 and R3, source MAC will be equal to MAC of gigabit 0/1 interface on R2, and destination MAC address will be equal to MAC address of gigabit 0/0 on R3. And finally, R3 will send the frame directly to MAC address of PC2. Also, every router will decrement TTL and recalculate header checksum in IP packet. That's what happens when specific device wants to send IP packet to remote host that is located behind multiple routers. And finally, using traceroute utility, we determined which routers with which IP addresses are located between our computer and remote server. And on Mac and Linux-like computers, you could use traceroute utility, and on Windows, you could use tracer utility that is available, for example, in PowerShell. That's all, guys, for this routing section. I hope you enjoyed it. Please notice that we didn't dive into great details and I didn't explain you, for example, details of OSPF protocol or how BGP works and which metrics are utilized in BGP. But I hope that you learned a lot and I hope that you enjoyed this routing section. Now let's make a pause and I'll see you guys in the next section.